Hi everyone, in AI art generation course. Did you ask yourself previously how artificial intelligence is able to generate all these amazing images? The answer is stable diffusion models. In this course, we will learn how these models work and how can we use them to generate amazing images. We will learn how to use stable diffusion models to add a new style to our own images. And we will also learn in this course how to do portrait image animation. And we will also learn how to convert our generated image into real picture by using CNC machine. And we will learn how to divide our image that we want to generate into regions and how to put what we want inside each region. We will also train our stable diffusion model on our personal images to make it able to generate our faces but with different styles. And we will learn how to talk to our stable diffusion model to generate these amazing images. Hi everyone. In this course we will talk about stable diffusion model and we will learn how to create these amazing images using artificial intelligence. Firstly, what is stable diffusion model? It is just a machine that converts any text into amazing images. As you can see here, we have this text oil painting Naruto robot. We will pass this text through our machine, which is our stable diffusion model, and our stable diffusion model will create this amazing image. This image will have the characteristics of the robot and Naruto. That's amazing, right? In this course, we will learn how to implement this machine and how can we train it to create these amazing images. But before talking about how to create them from scratch and how to train them, let's use a pre-trained stable diffusion model, which is a model that trained previously on very large number of images. Here we will use Colab notebook to write and run our code. So if you have a Gmail account, you can open Colab easily. We will press on this link here, and here we will click on new notebook like this. So now we have this notebook, Colab notebook. Here in this course we will use diffusers library, which makes it easy for us to work with the stable diffusion model. So firstly we need to download this library and all its requirements. To do that, we will use this pip command. This command will download any package that we want. So we will write pip install, and here we should write the name of the packages that we want. So here we will download diffusers package, datasets package, transformers package, accelerate package, ftfy package, and finally Pyro version 9.0.0. We will use all these packages through our course. So now let's run this cell to download all these packages. We just need to click on this symbol here. Now all the packages have been downloaded. To create a new cell, you should go in this place here and click on this place here. You will get this new cell and you can write your code in this cell. Now, as we said previously, diffusers package makes it easy for us to use any pre-trained stable diffusion model to generate artificial images. To do that, we should import diffusers package. So we will type import, and here we will type diffusers package. Okay, and we will click here. Now that we have imported diffusers package, we can use it in any cell. Let's use it in this cell here. As we said previously, here we need to use a pre-trained stable diffusion model, and we want to generate artificial images from it. So firstly, we need to download this pre-trained model. Actually, there are many pre-trained stable diffusion models in Hugging Face community. We will take this pre-trained model. We will copy the checkpoint of this model. To do that, we should click on this place here. Okay. Now from diffusers package, we will import stable diffusion pipeline, like this. Okay, we will use this stable diffusion pipeline to download our pre-trained stable diffusion model and use it to generate images. Now we will create this variable, model ID variable, which is equal to the path or the name of our pre-trained stable diffusion model that we copied previously, which is this ID here. Okay, so we will put it here. So now model ID will be equal to the checkpoint name. We will pass this ID to stable diffusion pipeline so that we can download this pre-trained stable diffusion model. So now we will create another variable, which is model variable. This variable will be equal to stable diffusion pipeline dot from pre-trained. We will use from pre-trained method to download our pre-trained stable diffusion model from Hugging Face community, like this. And here we will pass model ID. And we can also change the precision of our model. Here we reduced the precision to float 16. By doing this, we will speed up our model. We will talk about this in depth in later lectures. And now, what we will do actually, we will send this model to our GPU. Colab Notebook will give you free GPU. When you send your model, your stable diffusion model to GPU, by doing this, your stable diffusion model will be very fast. In other words, it will create the images quickly. How can we do that? We will type .2, and here you will pass the device that you want to put your model in, which is Coda. Okay, Coda 0. This is the name of our GPU. And here actually we also need to import torch. Import torch. Stable diffusion pipeline will use this library internally to create our stable diffusion model. We will use this torch package through this course. We will talk about it in depth in later lectures. Okay? So let's run this. Okay, now we will download our pre-trained stable diffusion model from Hugging Face community, Actually, it will take some time to do this. Let's see the error message here. He said that no CUDA GPUs are available. So here we should change the runtime of our Colab notebook. How can we do that? We should click on this place here and we should click on change runtime type. We should click this place and click on GPU. Okay, after that we will click on save. Now we should run all these cells again and see if it will work or not. It works fine. Now let's create artificial images using Stable Diffusion model. Firstly, we need to write the text that we want to create our image based on. So we will type text and here we will write the text. So let's say oil painting Naruto, like this. And now we will create our image based on this text. So we will type model, which is our Stable Diffusion model, and we will pass the text, this text here. And there are many other parameters that we will talk about them in details during the course. The first one is number inference steps. We can make it any number, let's say 200. And the second one is guidance scale. Let's say it is equal to 7.5. During the course, we will talk about each one of these parameters and how to find the value for each one of them. So now you don't need to worry about them. And finally, we will type .images like this. And our Stable Diffusion model will create an image based on this text, and we will put it in this image variable. So now we will run this cell and see the result. This image was generated completely using artificial intelligence, and you will not find it on the internet. So now, if you are interested in Stable Diffusion models, come and join us. Hi, in this lecture we will learn where to find the notebooks that are related with our course. Firstly, you should go to Introduction, and here in Introduction you will see this lecture, What is Stable Diffusion lecture. Inside this lecture you should go to the resources and you will find the notebook that are related with all these sections except this section here. Okay, let's do it. Let's firstly click on this course content and we should go to introduction section and we should click on what is Stable Diffusion lecture. Inside this lecture you will see these resources. We just need to click on them. So now we downloaded our notebook. Okay, now we should go to Colab and click on upload, and we should drag and drop our notebook. We just need to drag and drop this notebook here. Okay, and here's our notebook. Here's our code. Now let's talk about the second notebook that related with section 3, which is this one here. We just need to go to this section, or it is section 4. We just need to go to this section and we should go to the first lecture here, and you will find the resources. We just need to click on them and we should go to Colab, click again on upload, And let's open the location of this folder, and we should just drag and drop it here, and that's it. Thanks for watching. Hi, in this lecture we will answer this question: how does a stable diffusion model work? Let's say that we have this clear image, and now we will add a noise to each pixel in this image, so we will get noisy image 1. Let's now add another noise to each pixel in our noisy image 1, so we will get noisy image 2. So now our stable diffusion model will try to reverse this process, so it will try to figure out what is noise 2, and we will remove this noise from our noisy image 2, and we will get noisy image 1, and our stable diffusion model will try to predict noise 1. After that, we will remove this noise 1 from our noisy image 1 to get our clear image again. So in easy words, our stable diffusion model will try to remove the noise from our image. Hi, in this lecture we will talk about Gaussian distribution. Here we have two axes in this distribution. Here, this y-axis will represent the probability density for each value in x-axis. The area under this distribution will equal to 1, which means the probability of getting any value from this range will be equal to 100%. In other words, it is impossible to get a value from another range. So here, the area under the curve represents the probability of any specific range of values. And we can say that the probability of this range, it is greater than the probability of this range of values, because the area under the curve here, it is larger than this range here. And by probability I mean the chance that a value will be selected from a given range. So now, why we need to use this Gaussian distribution? We need to use this Gaussian distribution to take random values from x-axis based on the probability density on y-axis. And why we need to do that? Because we need to add a noise to our original information. Let's say that we have this pipe number and we want to add a noise to it, so we will get random value based on our Gaussian distribution like +2, and we will add it to our original information, which is 5, so we will get 7. Now we added this noise to our original information. You should know that it is important to learn how to add a noise in stable diffusion models. Now you should know that there is a special case of Gaussian distribution, which is standard Gaussian distribution, or we call it normal distribution. In this distribution, the standard deviation of this distribution will be equal to 1, while the mean equal to 0. Firstly, let's talk about this standard deviation. This thing here will control the width of our Gaussian distribution. When we reduce the value of this parameter, the width of our distribution, our Gaussian distribution, will reduce, while when we increase the value of this parameter, the width of our Gaussian distribution will increase. And the mean here, we will use it to shift our distribution based on our original data. As you know, we will add the noise on our original data. And this normal distribution will not have any data, so the value of this mean will be equal to 0. Now, let's say that we have very simple image, which has 4 pixels. Okay, the value of pixel 0, it is equal to I0. The value of pixel 1, it is equal to I1. The value of pixel 2, it is I2. And the value of pixel 3, it is I3. Now we will learn how to add a Gaussian noise to each one of these pixels. We will multiply our original information, let's say I0 here, with the square root of 1 minus the standard deviation squared. Or we can also call it the variance. A plus and 0, which is a noise that we took from the standard normal distribution, where the standard deviation equal to 1 and the mean equal to 0, times the standard deviation. So here, why we multiplied our noise that we took from our normal distribution with the standard deviation. Here, this is standard deviation. It is not equal to 1. It is something different. It will control the amount of noise that we will add to our original information, which is I0 in this case. So, when we increase the standard deviation, actually its value should be between 0 and 1. When we increase the value of this standard deviation, so in this case, the value of n0 times the standard deviation will be larger. So we will add large noise to our I0, to our original information. But what is this term here? The square root of 1 minus the variance or the standard deviation squared. When we increase the standard deviation, which means we will increase the variance, in this case we will reduce the value of this term. So in this case, I0 times the square root of 1 minus the variance will be smaller. So when we increase the noise, we will reduce the value of the original information. So why we need to do that? The idea behind this term here is when we want to increase the level of our noise, when we want to increase the amount of our noise, we should reduce the value of our original information. By doing this, if we want to convert the value in our pixel into just some noise, we can remove our original information by making the standard deviation something closer to 1. So the square root of 1 minus the variance will be something close to 0. When we multiply this thing with our original information, the result will be something close to 0, which means that we removed most of our original information and replaced it with noise. And if we want to reduce the value of the noise, so we need to reduce the value of the standard deviation. And if we make the value of the standard deviation something closer to 0, so in this case, the square root of 1 minus the variance will be close to 1. So we will multiply our original information with something very close to 1. In this case, we will lose very small amount of our original information and we will replace them with a small amount of noise. The same thing we will apply with the other pixels, okay, in our image, our simple image. So now we learned how to add a noise to our original image. Thanks for watching. Hi, in this video we'll talk about Markov chain. Let's say that we have clear image and let's call it x0, which is our image at time step 0. And now we will add a Gaussian noise to each pixel in our image. So we will get x1, and now we are at time step 1. And here this output x1, it is not constant because the noise that we will add to each pixel in our x-nodes, we will take it randomly from our Gaussian distribution. So here we will get a distribution for all possible values for this x1 variable. Or in other words, a distribution for all possible noisy images that we can get after adding Gaussian noise to x0. Each possible noisy image will have probability density in this probability distribution. Unlike what we said in Gaussian distribution, here the range of values with large area will have high probability to be selected. And this probability distribution will just depend on x naught. So when we change the value of x naught, this distribution will change also. Or in other words, this distribution will depend on the previous time step only. And that is the idea behind Markov chain. The next step will just depend on the previous step. We will call this distribution a Q distribution. And this distribution, as we said previously, will just depend on x0. So we will call it Q of x1 given x0, which means the probability distribution of x1 variable given the value of x0 variable. And as we said previously, we will use this distribution to get the value of x1 variable. And now we have x1 and we are at time step 1. We will add another Gaussian noise to each pixel in our x1 image. And we will get x2 image. And now we are at time step 2. And this x2 image, we will take it from this distribution. And this distribution will just depend on the previous variable, which is x1. So by knowing the value of x1, we will be able to create this distribution that we will use to get the value of x2 variable. And we will call this distribution Q of x2 given x1, which means the probability distribution of x2 by knowing the value of x1 variable. We will use this distribution to get the value of x2 variable. The range of x2 values with large area in this distribution will have high probability to be selected when we want to pick x2 value from this distribution. We will do the same thing again and again until time step T capital. So, in simple words, Markov chain means that the next step will just depend on the previous step. Hi, in this lecture we will talk about forward diffusion. Let's say that we have clear image x0 at time step 0. And here we will add Gaussian noise to this image. And we will get this Gaussian distribution. The mean of this Gaussian distribution will be equal to x0 times the square root of 1 minus the variance. And the variance here, it is the variance of the noise, of the Gaussian noise that we added to x0. And we will use this distribution to get the value of x1 variable at time step 1. And we can represent this distribution by Q of x1 given x0. Now let's say that we took the value of x1 variable from this distribution. Now we will add Gaussian noise to this value and we will get this distribution here. The mean of this distribution will be equal to x1 times 1 minus the variance of the noise that we added to x1. We will use this distribution to get the value of x2 variable at time step 2. We will represent this distribution by Q of x2 given x1. And we will do the same thing again and again until time step t capital. So in general, a q of xt given xt minus 1, it is equal to this Gaussian distribution that we will use to get the value of xt variable, where the mean of this distribution is xt minus 1 times the square root of 1 minus the variance at time step t. And here is the variance of this Gaussian distribution. This simple here, it is just another way to represent any Gaussian distribution, and there are many other ways. Here in this way, we just need to put the name of the variable and the mean and the variance of this Gaussian distribution. So now, this distribution q of x1 given x0, it is equal to the Gaussian distribution that we will use to get the value of x1 variable, where the mean of this distribution will be equal to the square root of 1 minus the variance at time step 1 times x0. And here we will put the variance of this Gaussian distribution, which is the variance at time step 1. The value of the variance will specify the amount of the noise that we will add to x0. And this I capital here tell us that we will apply the same variance for each pixel in our image. As you know, each variable here represents an image. We talked about this previously in Gaussian distribution lecture. Here is the most important thing. Let's say that we want to find the distribution of all possible sequences of x1 and x2 variables given x0. We call this distribution joint distribution, and this distribution will describe multiple variables. Here in this case, two variables, x1 and x2. This distribution will have the probability density for each possible combination of x1 and x2 variables, or in other words, all possible sequences of x1 and x2. It is equal to the distribution of x1 variable given x0, which is q of x1 given x0, times the distribution of x2 variable given x1. So q of x2 given x1. This is forward diffusion. So now, forward diffusion, it means finding the joint distribution for all the variables from x1 to xt capital given x0. Or in other words, in forward diffusion, we are trying to find the distribution that will give us all possible sequences from x1 to xt capital given x0. And we can use this pi symbol to represent this multiplication process. So here we will write pi from time step 1 to 2 of q of xt given xt minus 1, which is equal to this multiplication here. In general, if we want to find the joint distribution of x1 to xt capital, we just need to multiply all the intermediate conditional distributions of each xt given xt minus 1. Let's say that we want the joint distribution for all the variables from x1 to x10 given x0. Or in other words, the joint distribution for all variables in the first 10 time steps given x0. So here we need to multiply 10 distributions together to get this distribution, which is something difficult. So we need to find another way to solve this problem, to move us directly from x0 to any time step and avoid using this joint distribution. Actually, what we really need is to find the value of xt directly in this case x10. Here we can extract x10 from this joint distribution, but this thing will be difficult. Actually, it is computationally expensive, and we need to do integration to remove all the other variables from x1 to xt minus 1. Here in this case, we need to apply 9 integrals to remove the variables from x1 to x9. By doing this, we will be able to find the distribution that we will use to get the value of x10 variable given x0. So in other words, when we increase the number of time steps, things will become more difficult. In the next lecture, we will talk about reparameterization trick that we will use to solve this problem and finding q of x10 given x0 directly. Hi, in this lecture we will talk about reparameterization trick. Previously, we said that if we want to find the joint distribution for all variables from x1 to xt capital, in this case x10, so we need to multiply the distribution of x1 variable given x0 and the distribution of x2 variable given x1 and the distribution of x3 variable given x2, and we will do the same thing again and again until the distribution of x10 variable given x9. So now the question is how to avoid multiplying the distributions. Or in other words, we need to avoid finding the joint distribution and use another way to find q of x10 given x0. Because as we said previously, using the joint distribution to find q of x10 given x0, it is something difficult. So reparameterization trick will solve this problem. Firstly, you should know that we will use this symbol here to represent the noise that we will pick from the standard Gaussian distribution, where here epsilon 0, it means the noise that we took from the standard Gaussian distribution at time step 0. Epsilon 1, it means the noise that we took from the standard Gaussian distribution at time step 1, etc. As we said in the previous lectures, the mean of the standard Gaussian distribution is 0 and the variance is 1. And we put it I capital here to say that we will pick a noise from the standard Gaussian distribution to each pixel in our variable. And here, let's say that alpha t symbol, it is equal to 1 minus the variance at time step t. So now, xt, this variable, it is equal to the Gaussian distribution, where the mean, it is equal to the square root of 1 minus the variance at time step t times xt minus 1. And the variance of this distribution, this Gaussian distribution, it is the variance of the noise at time step t times I capital, which means we will use this distribution for all pixels of our variable xt. And we can write this Gaussian distribution this way that we used previously, which is xt minus 1 times the square root of 1 minus the variance at time step t plus the standard deviation at time step t times epsilon t, which represents random noise that we took from the standard Gaussian distribution at time step t. So when we take this noise, we will multiply it with this standard deviation at time step t. So we will control the level of this noise. After that, we will add it to the weighted xt minus 1. By doing this, we will get the value of xt variable. So now let's use alpha t rather than the variance. So let's write it again. Xt, x at time step t, it is equal to xt minus 1 times the square root of alpha t plus the square root of 1 minus alpha t times epsilon t, where the standard deviation at time step t it is equal to the square root of 1 minus alpha t. You can find that from this formula. Now we can do the same thing for xt minus 1. It is also Gaussian distribution. The mean of this Gaussian distribution is xt minus 1 times the square root of alpha t minus 1 plus the square root of 1 minus alpha t minus 1 times epsilon t minus 1, which represents the noise that we took from the standard Gaussian distribution at time step t minus 1. And here we will multiply all these things by the square root of alpha t plus the square root of 1 minus alpha t times epsilon t, which is, as we said previously, the noise that we took from the standard Gaussian distribution at time step t. Now we will multiply xt minus 2 times the square root of alpha t minus 1 by the square root of alpha t, and we will multiply the square root of 1 minus alpha t minus 1 times epsilon t minus 1 by the square root of alpha t. And here is the result. Xt it is equal to the square root of alpha t times the square root of alpha t minus 1 times xt minus 1 plus the square root of alpha t times the square root of 1 minus alpha at time step t minus 1 times epsilon t minus 1 plus the square root of 1 minus alpha t times epsilon t. Now this thing here, we can say it is just a Gaussian distribution with mean equal to 0. And the variance of this distribution, it is just alpha at time step t times 1 minus alpha at time step t minus 1, which is the standard deviation squared. And the standard deviation for this Gaussian distribution, it is this thing here, which is the square root of alpha at time step t times 1 minus alpha at time step t minus 1. We will call this Gaussian distribution k. And this thing here, it is also a Gaussian distribution, and we will call it y. The standard deviation for this distribution is the square root of 1 minus alpha at time step t. So the variance will be equal to 1 minus alpha at time step t, while the mean of this distribution will be equal 0. You should know that if you want to add two Gaussian distributions, you can directly add their means and their variances directly. So k plus y equal to this Gaussian distribution, where the mean equal to 0, because 0 plus 0 it is equal to 0, comma, and the variance it is equal to the variance of k plus the variance of y. So alpha t times 1 minus alpha t minus 1 plus 1 minus alpha t. We will multiply alpha t by 1, and we will multiply alpha t by alpha t minus 1. Finally, the variance of this Gaussian distribution will be 1 minus alpha at time step t times alpha at time step t minus 1, which is equal to the square root of 1 minus alpha at time step t times alpha at time step t minus 1 times epsilon at time step t minus 1. This distribution represents k plus y, and we can write it in this way. Here the mean equal to 0, and if we want to write it, so we need just to put the standard deviation, which is the square root of the variance. So we will write the square root of 1 minus alpha t times alpha t minus 1 times epsilon t minus 1. So now xt will be equal to the square root of alpha at time step t times alpha at time step t minus 1 times x t minus 2 plus the square root of 1 minus alpha at time step t times alpha at time step t minus 1 times epsilon at time step t minus 1. And this thing here, it is just k plus y distribution. And we will do the same thing again and again. We will open this xt minus 2 variable and do the same procedure. And we will get xt minus 3. We will open it. And we will do the same thing until reaching x0. So here finally, the variable xt is equal to the square root of alpha t times alpha t minus 1 times alpha t minus 2 times alpha t minus 3 until alpha 0 times x0, which is our original image, plus the square root of 1 minus alpha t times alpha t minus 1 times alpha t minus 2 times alpha t minus 3 until alpha 0 times epsilon 0, which is the noise that we will get from the standard Gaussian distribution with mean 0 and standard deviation 1. So now we can say that we can get the value of xt directly from this Gaussian distribution if we just have the value of our clear image x0. So this distribution, it is just q of xt given x0. And here we will make alpha t times alpha t minus 1 times alpha t minus 2 times alpha t minus 3 until alpha 0 equal to alpha bar t. So now we can write our final distribution like this. Xt it is equal to the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon 0. So now we don't need the joint distribution anymore. We could reach q of xt given x0 by using reparameterization trick, and we can use this distribution to give us xt directly. Thanks for watching. Hi, in this video we'll talk about variance schedule. Let's say that we have x0, which is our clear image. We will add noise to this image. Let's call it noise 1. Here, the level of this noise will be very small. And as we said previously, we will use the standard deviation of the Gaussian noise to control the level of the noise that we will add. In other words, the variance of this noise, it is very small. Let's say that the variance of this noise, it is equal to 0.0001. So now we have this distribution that we will use to pick the value of x1 variable. Now we are at time step 1. We will add noise 2 to our x1 image. And here the level of noise 2, it is greater than noise 1. Or in other words, the variance of noise 2, it is greater than the variance of noise 1. And the value of the variance of noise 2 will be equal to the value of the variance of noise 1 plus the step size. We will talk about how to compute the step size or variance difference later. So now we have this Gaussian distribution that we will use to get the value of x2 variable. We will get x2 at time step 2, and we will add noise 3 to this image. And here we will again increase the variance of this noise, or we will increase the level of the noise that we will add to x2. Now the variance of noise 3, it is equal to the variance of noise 2 plus the variance difference. So here the variance of noise 3, it is greater than the noise 2, and the variance of noise 2, it is greater than noise 1. Let's say firstly, the variance of noise 1, it is very small value, which is, let's say, 0.0001. And let's say that the maximum variance that we want is 0.02, and the minimum variance is 0.0001. So we will compute the difference between these two things, and we will divide the results by the number of steps, which is 3. The result will be 0.0099. This is the amount that we will add to the variance of the previous noise to get the variance of the noise that we will add at the current time step. We will call this amount the step size. Okay, so firstly, the standard deviation is equal to the minimum standard deviation. So here the variance of noise 1 will be equal to the minimum variance, which is equal to 0.0001. And now we are at time step 1. We will add the step size to the previous variance. So we will get 0.0001 plus 0.0099. And now we are at time step 2. So again, we will increase the level of the noise. So here the variance of noise 3, it is equal to 0.0001 plus 0.0099 plus 0.0099, which is equal to the variance maximum value. Let's say that we want to make the maximum variance equal to 1. At this case, x3 will be just standard Gaussian distribution or normal distribution, where the mean equal to 0 and the standard deviation equal to 1. At this case, we will lose all the information about x2 value. Our x3 variable here, it is just a pure noise without any information. We call this variance schedule linear variance schedule, because here we are increasing the variance of the previous step by fixed amount in the current step, which is the step size. So here we are increasing the value of the variance linearly. We said previously that we will use alpha rather than the variance. So here, let's say that we want to compute alpha bar 1. Alpha bar at time step 1. It is equal to alpha 1, which is equal to 1 minus the variance at time step 1. Now, let's say that we want to compute alpha bar 2. Alpha bar at time step 2. It is equal to alpha 1 times alpha 2, which is equal to 1 minus the variance at time step 1 times 1 minus the variance at time step 2. And let's say that we want to compute alpha bar at time step 3, which is equal to alpha 1 times alpha 2 times alpha 3, which is equal to 1 minus the variance at time step 1 times 1 minus the variance at time step 2 times 1 minus the variance at time step 3. So now we learned how to compute the value of the variance at each time step and how to compute the value of alpha bar at each time step. Finally, we can use this formula to get the value of xt variable at any specific time step. This is the Gaussian distribution that we will use to get the value of xt. We can compute the value of alpha bar, and we have the value of x0. It is our clear image, and we can pick the value of epsilon 0 from the standard Gaussian distribution. So we can get the value of xt variable. Hi, previously we talked about linear variance schedule, and we could compute the value of alpha bar at each time step. In other words, now we are able to find the value of xt directly from x0. As we said previously, when we move forward from one time step to another, we will increase the variance or we will reduce the value of alpha. bar. To make things more clear, let's say that we will move just 3 time steps forward. And let's say the step size equal to 0.1. As we said previously, alpha at time step t, it is equal to 1 minus the variance at time step t. So when we increase the variance, we will reduce alpha. Let's say firstly that alpha at time step 1, it is equal to 0.9. So alpha bar at time step 1 will be equal to 0.9 also. Now let's say that we are at time step 2. Here we will increase the variance by 0.1 by the step size. So we will reduce alpha by 0.1. So alpha at time step 2 will be equal to 0.8. Now let's compute alpha bar at time step 2, which is equal to alpha at time step 1 times alpha at time step 2, which is equal to 0.9 times 0.8, and the results will be equal to 0.72. So as you can see here, alpha bar at time step 2, it is smaller than alpha bar at time step 1. Now we are at time step 3. So alpha at time step 3 is equal to the previous alpha, which is alpha at time step 2 minus 0.1, or the step size. The results will be equal to 0.7. Now let's compute alpha bar at time step 3, which is equal to alpha at time step 1 times alpha at time step 2 times alpha at time step 3, which is equal to 0.9 times 0.8 times 0.7, and the results will be equal to 0.5. So here alpha bar at time step 3, it is smaller than the previous alpha bar, which is alpha bar at time step 2. But the problem here actually, as you can see here, the value of alpha bar will reach 0 quickly. Its value will be very close to 0 at time step 600. And when alpha bar it is very small, it means that we will lose most of the information from our original image. In other words, all the time steps after 600 time step, they will be useless. All of them will be the same, just noise without information. As we can see here, we will lose the information of our original image quickly when we use linear variance schedule. And here we lost actually almost all the information from our original image in time step 8. The rest of the time steps, they will be just noise. So to solve this problem, we will use cosine based variance schedule. As you can see here in this schedule, the value of alpha bar will not decrease quickly, so we will not lose the original information quickly. And this thing, it is good for training our stable diffusion model, where most of the time steps they will have some information about the original image. So now we have two variance schedules, linear variance schedule and cosine based variance schedule. And as you can see here, cosine based variance schedule is better than linear variance schedule. Thanks for watching. Hi, in this lecture we will talk about reverse diffusion. Previously we learned how to move forward from one step to another and how to add Gaussian noise at each time step. Now let's say that we have x3, which is noisy image. Now we want to remove the noise that we added to x2 to get x3, or in other words, we want to remove the noise that we took from this Gaussian noise 3 distribution and move back to x2. Or in other words, we need to find the distribution that we can use to get the value of x2 given the value of x3 variable. We call this distribution the target distribution. It is our target. This distribution will have all the possible values of x2 given the value of x3 variable. Now we will take the value of x2 variable and we will do the same thing again. We will try to find the distribution, the target distribution of x1 variable given the value of x2 variable. Now we will take the value of x1 variable from this distribution, and now we have the value of x1 variable. We will try to find the distribution of x0 variable given the value of x1 variable. We will pick the value of x0 variable from this distribution. The value of x0 variable that we took from this distribution will be something similar to our original image, to our clear image, x0. And here you should know that we should use very small step size. Or in other words, we should make the number of time steps very large. As you know, the step size, it is related to the number of time steps. When you increase the number of time steps, you will decrease the value of step size. So why we need to do that? Why we need to make the step size very small? To make things more clear, let's say that the number of time steps equal to 1000, which is a very large number. So the step size will be very small. By doing this, we will make sure that we will add very small level of noise in the first steps. By doing this, we will make sure that the target distributions for these time steps, they will be very good distributions. And that's what we will see later. As you know, firstly, we will add very small level of noise to our x0 variable. Now, the variance of noise 2 will be also very small, because here the step size, it is very small, and the variance of noise 2, it is equal to the variance of noise 1 plus the step size. And because that the step size, it is very small value, because the number of time steps, it is very large, and because that the previous variance, it is very small, so the variance of noise 2 will be also very small value, which is the previous variance plus the step size. So when we increase the number of time steps, so we will increase the number of these good target distributions. Another thing that can increase the number of good target distributions is to make the maximum variance equal to small value. Like in this case, we will make it equal to 0.02. The maximum variance, it is the variance at time step t capital, and at this case t capital, it is equal to 1000. So the maximum variance, it is the variance of noise 1000, which is the last time step. By reducing the value of maximum variance, we will reduce the step size also. So by doing this, we will increase the target distributions. And even the last target distribution, which is the distribution of variable x999 given x1000, we can say it is also good, because the level of the noise that we added here, it is not very large. The level of the noise, or the variance of the noise, it is just small value, 0.02. But of course, the previous target distributions will be better than this distribution. Now we will explain what is the meaning of good target distribution. Now let's say that we have the distribution of xt minus 1. We call this distribution prior distribution. We can use this distribution to get the value of xt minus 1 variable. Now let's say that we took xt minus 1, the value of xt minus 1 variable. Now we will add a noise to this xt minus 1. We can add a noise with large variance or a noise with small variance. A noise with large variance will remove large amount of information from xt minus 1. In other words, when we will take the value of xt variable from this distribution, this value will have very small information about the value of xt minus 1 variable. And the noise with the small variance will remove small amount of the information from xt minus 1. In other words, when we take the value of xt variable from this distribution, this value will have large amount of information about the value of xt minus 1 variable. Now, let's say that we added a noise with large variance. And here's the distribution that we will use to pick the value of xt. Now let's say that we took the value of xt variable from this distribution q of xt given xt minus 1. here we will use this value xt to update this distribution based on this value, and we will call this the posterior distribution. As you can see here, this distribution isn't that good because we added large level of noise and we lost most of the information in xt value about xt minus 1 value. So the range of possible values for xt minus 1 variable will be large. It is like knowing the value of xt variable didn't make us certain about the value of xt minus 1 variable. So you can see this is very bad distribution. Now we will try to make this posterior distribution or target distribution better. Or in other words, we will try to reduce the range of possible values of xt minus 1 variable given the value of xt variable. Now we took the value of xt minus 1 variable from this prior distribution. Okay. Now we will add a Gaussian noise with small variance. So now we have this distribution that we will use to get the value of xt variable. Now let's say that we took the value of xt variable from this distribution and we will update our prior distribution based on this value, based on the value of xt variable, and we will get this posterior distribution. You can see now that the range of possible values inside this posterior distribution, it is smaller than what it was before, which means that we are more certain about the value of xt minus 1 given the value of the variable xt, because the value of xt variable has large amount of information about the value of xt minus 1 variable. And as you can see here, the shape of this target distribution or this posterior distribution, it is very similar to the shape of any Gaussian distribution. In other words, when we decrease the variance of the Gaussian noise that we want to add at any time step, we are trying here to make the target distribution something similar to any Gaussian distribution. So from now on, we will treat any target distribution as Gaussian distribution. So here we didn't just decrease the range of possible values, but we also made the shape of the target distribution similar to the Gaussian distribution, which is very simple distribution. And that is what we meant by good target distribution. So now we can say that q of xt minus 1 given xt, it is just Gaussian distribution with the specific mean and variance. The mean and the variance of this distribution will depend on the value of xt variable. And now we will approximate this distribution. We will learn this distribution using a neural network. Okay? So here we will write p subscript theta of xt minus 1 given xt. It is just a Gaussian distribution. Here we will update the parameters of this neural network to find the best value for the mean and the standard deviation, that it will make this predicted distribution similar to the target distribution. Here we will pass the value of xt variable and the time step that we are in right now to our neural network, and our neural network will try to predict a mean and the standard deviation. In the next video, we will learn how to find the target mean and the target standard deviation, and we will realize that we can make things more easier than this. Thanks for watching. Hi, in this lecture we will answer this question: how can we train our neural network? Previously we said that we will train our neural network to predict the target distribution, which is the distribution that will move us from xt to xt minus 1. As you can see here, this is the distribution that our neural network will predict, which is p sub theta of xt minus 1 given xt. This distribution, it is just Gaussian distribution. We have two hyperparameters for this distribution. The first one is the mean of the distribution. We will try to make this mean closer to the mean in the target distribution. we will try to learn what is the best value for this parameter based on xt and the time step that we are in right now. We will try to tune the parameters of our neural network to predict the best mean for the target distribution. We call these parameters theta. We will try to tune them to find the best mean, and we will do the same thing for the variance. We will pass xt and the step that we are in right now through our neural network, and our neural network will try to predict the best value for the mean and the variance. And here we passed the time step to our neural network to make our neural network able to realize the level of the noise that we added at this time step. This will help our neural network to realize the noise that we want to remove at this time step. Let's say that if the time step equal to 10, the level of the noise that we added in this time step, it is higher than the level of the noise that we added in time step 1. And the second thing that we will pass it through our neural network, it is x sub t. And our neural network will return the predicted mean and variance. We will use this mean and variance to create the predicted distribution. If the predicted mean and variance are very similar to the mean and variance of the target distribution, so this predicted distribution will be very close to the target distribution. And you should know that if t capital, which is the last time step, it is equal to infinity, at this case the distribution of xt, it will be equal to the standard Gaussian distribution, where the mean equal to 0 and the standard deviation equal to 1. But actually we will make t capital equal to 1000, which is the best value, and we will make the maximum variance equal to 0.02. They did a lot of experiments to realize that. In general, the target distribution for any time step, it is just the distribution of xt minus 1 given xt. So now, why we put it x0 here? Here we will not give the value of xt variable only, but we will give the value of x0 variable, or in other words, our clear image. By doing this, we will be able to find the mean and the variance of the target distribution easily. And actually during a training, we have our clear images. We will take them from our data set. We will call this clear image our reference image. But here we will have another problem. The mean of our target distribution will depend on xt and x0. And because that the mean will depend on the value of xt variable and the value of x0 variable, so we should pass the value of xt variable and the value of x0 variable and the current time step to our neural network. We can do that during a training because we have the value of x0, but during inference, or when we want to use our neural network to generate images, we will not have the value of x0 because we want to create new images. In the previous lecture, we said that we will just pass the value of xt variable and the number of the current time step. So we will learn how to solve this problem and remove the value of x0 variable in the mean of the target distribution. Here we will use Bayes' theorem to get the posterior distribution, or q of xt minus 1 given xt and x0. Previously we said that we will give the value of x0 to find the posterior distribution easily. So why it is difficult to find the posterior distribution without the value of x0? To know that, let's apply Bayes' theorem. The distribution xt minus 1 given xt and x0, it is equal to the distribution of xt given xt minus 1 and x0 times the distribution of xt minus 1 given x0 divided by the distribution of xt given x0. We put it x0 here because it is difficult to find the distribution of xt if we don't have the value of x0. And it's difficult to find the distribution of xt minus 1 if you don't have the value of x0. But when we have the value of x0 here, we learned previously how to move directly from x0 to any time step. We talked about that in reparameterization trick lecture. We said that it is just Gaussian distribution. The mean of this distribution, it is just the square root of alpha bar t minus 1 times x0. Here we have x0, and the variance, it is 1 minus alpha bar t minus 1. And here also the mean of this distribution, it is just the square root of alpha bar t times x0. Here we have x0 also, and the variance, it is just 1 minus alpha bar t. And here this distribution q of xt given xt minus 1 and x0, it is similar to the distributions that we got in the forward diffusion, but we didn't have the value of x0. But as we said previously in Markov chain lecture, xt will just depend on xt minus 1. The current step will just depend on the previous step. So we can remove the value of x0. And this thing, it is just Gaussian distribution. The mean of this distribution, it is just the square root of alpha t times xt minus 1. And the variance, it is 1 minus alpha t, which is also beta t. By using this Bayes theorem, we will get the posterior distribution or the target distribution. This Bayes theorem will update our prior knowledge, our prior distribution, which is q of xt minus 1 given x0 based on the value of xt. This equation here represents any Gaussian distribution. So if we have a Gaussian distribution with a specific mean and a specific variance, it is equal to 1 divided by the standard deviation of this Gaussian distribution times the square root of 2 times pi times exponential raised to power minus 1 divided by 2 times x minus the mean of this distribution squared divided by the variance of this Gaussian distribution. Here x represents the variable that we will get its value from this distribution. For example, we will use this Gaussian distribution to get the value of the variable xt minus 1. So we will put xt minus 1 here. Now we will represent all these distributions, all these Gaussian distributions using this way. The mean of this distribution, it is the square root of alpha t times xt minus 1. We will put this mean in our equation. And the variance of this distribution, it is just 1 minus alpha t, or we can say it is beta t. We will also put it in our equation and we will get this thing here. And as you can see here, we will use this distribution to get the value of xt variable. So we will put xt in this place here. Now we have this Gaussian distribution. The mean of this distribution is the square root of alpha bar t minus 1 times x0, and the variance is 1 minus alpha bar t minus 1. We will put all these things in this equation and we will get this thing here. And we will do the same thing with this Gaussian distribution. The mean of this Gaussian distribution is the square root of alpha bar t times x0, and the variance is 1 minus alpha bar t. We will put all these things in this equation here and we will get this thing here. Here you might ask yourself why we didn't put 1 divided by the standard deviation times the square root of 2 times pi here in this place. The answer is easy. Here we will convert all these things into just one exponential and we will extract the mean and the variance of the target distribution from the power of this exponential. As you can see here in this equation, this thing here, we will not use it to find the mean and the variance of the target distribution. It is actually available in this place here. But as we said previously, we will convert all these exponentials into just one exponential. Here we will compare the power of this exponential with this equation, with the power of the exponential in this equation to compute the value of the mean and the variance of the target distribution. Finally, you will get the variance of the target distribution, which is equal to 1 minus alpha bar t minus 1 divided by 1 minus alpha bar t times beta t. And the mean of the target distribution, which is equal to the square root of alpha t times 1 minus alpha bar t minus 1 divided by 1 minus alpha bar t times xt plus the square root of alpha bar t minus 1 times beta t divided by 1 minus alpha bar t times x0. As you can see here, the mean of the target distribution depends on the value of xt and the value of x0. But we want to make the mean just depend on the value of xt. So what we should do? As you know, we have simple formula that will make us move directly from x0 to xt. We talked about this formula in reparameterization trick lecture. Xt is equal to the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon. So now we will extract x0 from this formula. x0, which is equal to 1 divided by the square root of alpha bar t times xt minus the square root of 1 minus alpha bar t times epsilon t. Now we will put this thing here in this place. So finally, the target mean will just depend on the value of xt variable. The target mean will be equal to 1 divided by the square root of alpha t times xt minus 1 minus alpha t divided by the square root of 1 minus alpha bar t times epsilon t. So now we just need to pass the value of xt variable and the number of the current step through our neural network, and our neural network will try to predict the mean of our target distribution. As we can see here, we don't need to use our neural network to predict the variance of our target distribution because we know how to compute the value of alpha bar at any time step and also how to compute the variance beta sub t at any time step. So we know how to compute the target variance or the variance of the target distribution at any time step. So we will make our neural network just try to predict the target mean or the mean of the target distribution. And because that we know how to compute the value of alpha t and alpha bar t, and we have the value of xt variable, so we will make our neural network just try to predict what is epsilon t. And that's what we will see in the next lecture. Now we learned how to find all the parameters of the target distribution. So now we will use the neural network to predict the noise that we will get from the standard Gaussian distribution where the mean equal to 0 and the variance equal to 1. So our neural network will get two values here, xt and the time step number, to make our neural network able to realize the level of the noise that we added here. So, as you know, the mean of the target distribution is equal to 1 divided by the square root of alpha t times xt minus 1 minus alpha t divided by the square root of 1 minus alpha bar t times epsilon t. This thing is our target. We want from our neural network to predict this noise here. So here our objective or our loss function, it is equal to the difference between the target noise and the predicted noise from our neural network squared. We will try to tune the parameters of our neural network to reduce the difference between the predicted noise and the target noise. Or in other words, we will try to train the parameters of our neural network to reduce the value of this loss function. By doing this, we will make the predicted noise similar to the target noise. in the mean of our target distribution. PyTorch package will do all these things for us. It will tune the parameters of our neural network to reduce the value of the loss function and making the predicted noise get closer and closer to the target noise. Thanks for watching. Let's now visualize the training process. Firstly, what is the meaning of epoch? The number of epochs means the number of times that we will pass it through our dataset. Or in other words, the number of times that we will pass it through all images. Here in this case, we will pass through our dataset a number of times. Inside each epoch, firstly, we will take a specific image and take a random time step, and we will add the noise to this image based on the time step. After that, we will pass our noisy image and the time step of this image through our network, and our network will try to predict the epsilon or the noise, and we have the target noise that we added actually to our image. We will compute the difference. We will use PyTorch to tune the parameters of our network to reduce that difference. We will do the same thing for all images in our dataset. After passing through all the images, we will complete one epoch, and we will start with a new epoch. So here, at each epoch, we will pass it through all our images, and we will do the same thing again. We will specify specific time step for each image in our dataset, and we will add the noise to each image in our dataset based on its time step. As you know, we learned previously how to move directly from the original image x0 to x at time step t by using this formula here. And previously we learned how to compute the value of alpha t and alpha bar t. And as you know, we will take epsilon from the standard Gaussian distribution. So now we will pass these noisy images and their time steps through our U-network to predict the epsilon for each image, and we have the target epsilon for each image, so we can compute the loss, and we will try to reduce the value of the loss by tuning the parameters of the network. We will do the same thing again and again until ending epoch n. And here we will train our U-network for many number of epochs to reduce the loss values from the loss function as much as possible, because one epoch will not be enough, especially when your data set is difficult. Hi, in this video we'll talk about inference, and we will learn how to use our stable diffusion model. Let's say that we trained our stable diffusion model previously, and now we want to use it. So how can we do that? Previously we said that we will use our stable diffusion model to predict the target distribution, or in other words, it will try to predict the mean and the variance of the target distribution. And we found that we just need to compute the mean, and more specific, the epsilon inside the mean. Let's say firstly the xt, it is just a pure noise that we took from the standard Gaussian distribution. As you know, during inference time we don't have any data set, and we will start with a pure noise to generate artificial images. So when we will try to remove the noise using our network, we will not able to know what the clear image that we will end up with. Here we will predict the target distribution of xt-1 variable, and we will use it to take the value of xt-1 variable. Now we have the value of xt-1 variable. We will do the same thing again. We will try to predict the target distribution of xt-2 variable based on the value of xt-1 variable. We can repeat this process for any number of time steps, but it should be less than 1000 time steps. Let's visualize what we talked about earlier. Firstly, we will sample a Gaussian noise from the standard Gaussian distribution, let's say. And let's say here T capital equal to 1000. Now we have X 1000. We will pass X 1000, our noisy image, through our U network. We will pass the embedding for the time step through our U-net also. And we will predict epsilon. We will use this formula here to compute xt minus 1. We will put the predicted noise here, and here we will put our noisy image x1000, and here we will predict x999. We will use this predicted distribution to get the value of x999. We will do the same thing again and again until reaching x0, and we will get good image. Let's say that we did the same thing again and again until reaching x2. Our noisy image now it is x2. We will do the same thing. We will also pass it through our unit, and the embedding for this time step we will predict the noise, and we will use this formula to compute xt minus 1, or in other words to find the distribution of x1 variable, and we will get the value of x1 from this distribution. And we will do the same thing to get the distribution of x0 variable, and we will take the value of x0 variable from this distribution. Here we will use the value of x1 variable that we will take from this distribution. We will pass it through our U network, and we will pass the embedding of time step 1, and we will get this noise. We will put the value of x1 variable and the predicted noise inside this formula to get the distribution of x0 variable. We will take the value of x0 variable from this distribution, which is this image here. Thanks for watching. Hi, in this video we'll talk about simple U network. Here they used this U network for segmentation task. Now, what is segmentation task? Let's say that we have this image. Now let's say that we want to classify each pixel on this image to a specific class. So we will pass this image to our U network. This network trained previously to do this task, and we will get the output from this U network. As you can see here, we classified each pixel in our original image to a specific class. These pixels here represents the road, and these pixels here represents these trees, and these pixels represents these buildings, etc. Here they used many different layers to create this simple U network. Now let's say that we resized our image and made its height and width equal to 572. Now we will pass this image through our U network. Firstly, we will pass our image through a convolution layer with a 3x3 kernel. What is convolution layer? Let's say that we have this image and we want to pass it through a convolution layer. Here is the kernel of our convolution layer. This kernel has trainable parameters. They trained these parameters previously to solve this task. As you can see here, we will firstly multiply this kernel with this part here. After that, we will multiply it with this part here. And what we will actually do here, we will multiply each parameter inside our kernel with the corresponding pixel in our image. After that, we will add all the results to obtain just one single value in the output. For example, let's multiply this part here in our image by our kernel. So 70 times 0 plus 129 times minus 1 plus 127 times 0 plus 115 times minus 1 plus 69 times 5 plus 134 times minus 1 plus 123 times 0 plus 95 times minus 1 plus 130 times 0, which is equal to minus 128. And as you can see here, we will slide our kernel from top left to bottom right of our image. And here's the output, which is the feature map. This feature map will have just the important thing in our image. And by important things, I mean the things that our kernel, our filter, says are important. And you should know that we will use more than one filter inside each convolutional layer. Here we took just one filter or one kernel for simplicity. Another thing that you should focus on is the width and the height of the output will be smaller than the width and the height of the input image. That's good, but all what we did previously, it is just multiplication and addition. So we will not be able to model nonlinear relationships by doing just this thing. So we need to use an activation function to handle nonlinear relationships. Here we will use ReLU activation function. We will pass our feature map through this activation function. This activation function will make anything less than 0 in our feature map equal to 0, and it will keep anything greater than 0 in our feature map as it is. As you can see here, this activation layer, it is very simple and doesn't have any trainable parameters. And it will make our neural network able to handle very complex data set. As you can see here, the width and height of the outputs reduced because of the convolutional layers. Now we will pass the output feature map through max pooling layer. This layer will condense the features in the feature map that our filter said they are important. And it will also reduce the width and the height of the feature map. The idea here, it is very simple. Like what we did previously, we will slide over our image, our feature map, and at each time we will take the highest number. So here we removed the features that our filter said they are not important. And as you can see here, the width and the height of the output, it is smaller than the width and the height of the input. So here we also reduced the width and the height of the feature map, but without using any convolutional layer. We just used max pooling layer. This layer doesn't have any trainable parameters, which means it will not increase the size of our network compared to the convolutional layer. And you should know that the convolutional layers inside this simple U network has many kernels or has many filters. Like in this case here, we have 128 feature maps, which means that the previous convolutional layer has 128 filters or 128 kernels. Each one will create its own feature map. We will do the same thing here until reaching this place. Here we will use a special layer, which is transpose convolution layer. Previously we said that the width and height of the output from any convolutional layer is smaller than the width and height of the input to the convolutional layer. Here in the transpose convolutional layer, the width and height of the output will be larger than the width and height of the input. For example, let's say that we have this very simple feature map. It is the input to our transpose convolution layer. And we have this filter, this kernel, 3 times 3 kernel. The first thing that we should do is to put the output. Here we want the output to be 4 times 4, 4 rows and 4 columns, while the input is 2 times 2. And here we put it padding around our output, because if we don't put it, we will end up again with 2 times 2. Here we will slide our kernel through the output, and each time we will multiply the kernel with the specific value from the input. You should know that we will remove all these paddings because they are not important. We just put them to make sure that the output shape will be 4 times 4. By doing this, we will get bigger feature map. We will do this thing again and again, and the width and height of our feature maps get bigger and bigger until reaching this place here. And as you can see here, these arrows, we call them skip connections. We will use them to join the low-level features with the high-level features. They found that doing this will make the training of our unit faster, and the results will become better. The last layer here, it is just convolutional layer, and the size of each kernel in this layer is 1 times 1. I know this layer, it is convolutional layer, but here the shape of the output will not be smaller than the shape of the input, but it will be the same as the shape of the input. This case will happen just when the size of the kernel equal to 1 times 1. Most of the time we use this layer with 1 times 1 kernel size to control the depth or the number of feature maps in the output. So we will apply each filter on each pixel in the feature map to make predictions for each pixel. We will use these predictions to decide the class that related with each pixel. Here in this course, we will not use U-network for segmentation, but we will use it to predict the noise, the epsilon, in our noisy image. To do that, we need just to change the output layer, the final layer in our U-network, and we will learn that later. Thanks for watching. Hi! In this lecture, we will talk about unconditional U-network for noise prediction. By unconditional, it means that we will not be able to control what our stable diffusion model will generate. We will use this U-network to predict the epsilon or the noise. And as you know, we have beta t, alpha bar t, so we can create the target distribution that we will use to get the value of xt-1 variable. Let's say that we have this image which represents the value of x1 variable. Now you should know that any colorful image has 3 channels: red channel, green channel, and blue channel. These channels will create the colors in our image. In other words, we will represent each pixel in our image by 3 values. So when we want to add a noise to our pixel, we need to add a noise to each one of these values, which means that we want from our U-network to find the noise for each one of these 3 values for each pixel. In other words, the epsilon will also have 3 channels, and the width and height of the epsilon should be equal to the width and height of the input image also, to make sure that we will predict the noise for each one of these pixels in our input image. But in the case of grayscale images, these images will have just 1 channel. In other words, we will represent each pixel in our image by just 1 value. So when we want to add a noise to a specific pixel, we will add a noise to its single value. In this case, the predicted epsilon will have also just 1 channel, and the width and height of epsilon will be equal to the width and height of the input image. Previously, we said that we need to make our neural network, our U-network, able to realize where we are right now, at which time step we are now. To do that, we will pass the time step that we are in right now to our U-network. How can we do that? Firstly, you should know that it's not a good idea to pass the number of time step that you are in right now directly to your U-network, because it will affect on the training. You should convert this number into a vector of values using positional encoding function. This function will create a unique vector of values for each time step. Each positional embedding vector will have the information about the position of its time step. We will join this positional embedding vector with the output from each layer in our U network. By doing this, we will make sure that our neural network is able to know where we are right now and the level of noise that we added here, and we want to remove it. Here in this case, x1, it is at time step 1, so we will pass the positional embedding vector of time step 1 to our neural network, and our neural network will predict the epsilon. We have beta t, alpha t. Now we have epsilon, beta t, alpha bar t. We can use them to create the target distribution of variable x0, and we will take the value of x0 variable from that distribution. The last thing that we should talk about is how to control the number of feature maps of the output from our U network. If we want to make our epsilon has just one feature map, one channel, in this case, we should make the number of filters of the last layer in our U network equal to one filter. This one filter will create one feature map or one channel, which represents our epsilon. If we are dealing with colorful image and we want epsilon to have 3 channels, so we should make the number of filters of the output layer equal to 3. Each filter will create one channel or one feature map, so we will get finally 3 feature maps or 3 channels. In the next video, we will talk about positional encoding and how it works. Thanks for watching. What is positional encoding? Firstly, you should know that this wave here, it is sine wave. The highest value in this wave is 1, and the lowest value in this wave is -1. This axis here, it is time step axis. Here we have all the time steps from time step 1 to time step 1000. For each time step, let's say this time step here, t, we have specific value in this sine wave, which is this value here in this y-axis. But the problem here actually, this value will not be unique. Let's say that this time step, it is time step 10. And let's say that this time step here, it is time step 400. This time step will have the same value of time step 10. As you can see here, the value of this time step, it is similar to the value of time step 10, like this, in this y-axis, in our sine wave. So how can we solve this problem? How can we make unique value for each time step using this sine wave? To do that, we will make just this part here from our sine wave cover all these time steps. Okay? We can do that by reducing the frequency of this sine wave. Now this part here covers all this region from 1 to 1000 time step. And we can say that we will get a unique value for each time step from 0 to 1000. Let's say that, for example, time step 1 will be equal to 0.001 in the y-axis. Time step 2 will be equal to 0.0011 in the y-axis. The last time step, which is time step 1000, will be equal to 1. As you can see here, 1000 will be equal to 1 on y-axis, like this. Now we have a unique value for each time step. As we said previously, we want to make our U network able to know where we are, at which time step we are right now. Let's say that we passed this time step, the value of time step 1, which is 0.001, to our neural network. It will be difficult for our neural network to understand that we are at time step 1. Actually, here we reduced the range of possible time steps. So now our neural network is focusing on a specific region of possible time steps. Let's say this region here. Okay? And let's say that this region has two time steps, T1 and T2. But our neural network is uncertain about which is the real time step that we are in right now, because the difference between these two time steps is very small. So now we can say that just one unique value for each time step will not give us the precise time step that we are in right now. Now we will use this cosine wave. The highest value in this wave is 1, the lowest value in this wave is -1. We will reduce the frequency of this wave like what we did previously to make this part here cover all the range between 0 and 1000. And this is, and as you can see here, this yellow curve cover all the range between 1 and 1000 time steps. Now we will do the same. Here time step 1 will be very close to 1 in the y-axis. We can say that time step 1 it is something in this place here. So in y-axis it will be very close to 1 value. And as you can see here, let's say that the value of time step 1 it is 0.999. Now we will do the same thing for time step 2. Time step 2 on y-axis will be equal to 0.998. Here we didn't solve our problem because the difference between these two values in this positional embedding vector is very small, like in the previous case, So our neural network will not be certain about the real time step that we are in right now. Why? Because the difference between these two things that we added here, it is very small. So now what we will do here, actually, we will increase the frequency of this yellow curve. Actually, this yellow curve, it is just cosine wave. If we want to complete this curve, it is just cosine wave, okay? But with very low frequency. Now, what we will do, we will increase the frequency of this yellow cosine wave. By doing this, it will get closer to this cosine wave. The frequency of this cosine wave will get closer to the frequency of this cosine wave. As you can see here, in other words, it will complete one cycle quickly compared to the previous one. As you can see here in this pink cosine wave, it will move down quickly compared to the yellow cosine wave, like this, and it will move up quickly compared to the yellow cosine wave. So now if we want to check the value of time step 1 for this pink curve, pink cosine wave, the value of T1 will be 0.9, let's say 0.9. So now let's check the value of time step 2, and it will be equal to 0.8. You can see the difference between the value of time step 1 and time step 2. It is greater than the difference in the previous case, okay, because we increased the frequency of this yellow wave. So when our neural network sees this positional embedding vector, firstly it will see this value 0.001. So our neural network will be sure that our real time step is within a specific range, let's say this range, within this specific range that has time step 1 and time step 2. And now when our neural network sees this value 0.9, it will be certain that it is time step 1, because now the difference between time step 1 and time step 2, it is more clear for our neural network. Okay, that's it. Okay, that's the main idea behind positional embedding vector. Actually, we can add many other values to this positional embedding vector by doing the same procedure. We used previously cosine wave, so now we will use sine wave, and the frequency of this sine wave will be higher than the frequency of this cosine wave, so it will move faster than this cosine wave, pink cosine wave, like this. As you can see here, we have this green sine wave, and it is faster than this pink cosine wave. We will use this sine wave to add another unique value for these positional embedding vectors to make our neural network more certain about each time step. Thanks for watching. Hi, in this lecture we will talk about conditional U-network. Here in this stable diffusion model, we will be able to control what our stable diffusion model will generate. So how can we do that? There are many different things that we can use for conditioning, like semantic map, text, representations, and images. Let's say that we want to create an image using our stable diffusion model based on a specific text. So how can we do that? Firstly, we will pass this text through language model. This model will convert this text into a vector representation, or we can call it text embedding, which is a vector with many numbers that represents what our language model thinks about this text. Now we want to fuse this vector representation of our text with our U-network. How can we do that? One way to do that is by using cross-attention blocks. We will put these blocks inside our U-network. These blocks will make our U-network able to focus on a specific region in the feature map and based on our text. Let's say that we passed this text here, the dog on the car. Now we will convert this text into text embedding, and we will fuse this embedding with our U network. Now we will do reverse diffusion to create an image based on this text. Let's say that our stable diffusion model generated this image, a dog on the car image. Now let's change one word in this text. Let's change dog to cat. We will convert this text into text embedding, and we will pass it through our U network, and we will do reverse diffusion to create an image based on this text. As you can see here, this image, it is not different from the previous image. Here our stable diffusion model just changed this dog to cat. And this thing happened because of the cross attention blocks that we added to our U network, which made our neural network able to know the region that we should change based on our text. Now you might ask yourself, how can we control the importance of the guidance or the condition in the generated image from our stable diffusion model? To do that, during training, we will not just predict the epsilon based on the input image and the time step, but also with the condition. Let's say that this condition is y. It might be text, image, etc. Here we will train our stable diffusion model in two states, conditional and unconditional, and we will decide that randomly during training. In other words, sometimes we will pass the condition to predict the epsilon, and sometimes we will not pass the condition to predict epsilon. Why we did that? We did that just to control the importance of the condition during the inference time. Now let's talk about the inference. How can we control the importance of the condition during the inference time when we want to use our stable diffusion to generate images after training? We will balance between the condition and the randomness by using guidance scale parameter. Firstly, we will pass xt, the time step that we are in right now, and the condition, and we will get epsilon value. And we will do the same thing, but now without condition. We will pass the value of xt and the time step that we are in, but we will not pass any condition to our neural network, and we will get the predicted epsilon. Now we have this parameter here, S, which is guidance scale parameter. We will use it to control the importance of the condition in the generated image. When we increase the value of this parameter, the weight of the epsilon that created based on our condition will increase, and the weight of the epsilon that created without any condition will decrease, which means that our generated image will follow our condition strongly. Actually, this graph here represents the forward diffusion and reverse diffusion. But what are these two things here? E and D. This thing here we call it encoder, and this thing here we call it decoder. Both of them will create variational autoencoder. What is the advantage of this variational autoencoder model? This model, we will not train it during training our U network. It is a pre-trained model. They trained this model previously to do the following task. Firstly, the encoder will compress our input image. Let's say that our image, it is very high resolution image. Let's say that the width of the image is 1000 and the height of the image is 1000. Which means if we want to pass this image directly through our U network, our training process will take long time. And the inference time will be very long because, as you know, we will take many time steps in reverse diffusion to generate high resolution image, and at each time step we will use our U network. So we will reduce the size of this image by using the encoder of our variational autoencoder. This Z here, it is our compressed image. We used this encoder to convert our input image to this new representation, which has the most important thing in our input image. And the size of this new representation, it is very small compared to our input image. In other words, the width and height of this image are very small compared to our input image. So when we pass this new representation through the decoder of the variational autoencoder, this decoder will be able to reconstruct our original image from this new representation. So now we reduced the size of our input image using this encoder. We will do the forward diffusion and we will get Z, capital T, or you can get Z at any time step that you want. In other words, we added noise to this new representation of the input image. Now, what we will do actually, we will use our stable diffusion model to remove the noise from this Z capital T. We will remove the noise from this Z capital T gradually in a reverse diffusion process to get Z, which is the compressed representation of our input image, our clear image. And we will use the decoder from the variational autoencoder to convert this predicted compressed representation to high resolution image. So now, by making our stable diffusion model trying to generate compressed representation with small width and height, we will make the training time and the inference time very small. Thanks for watching. Hi, in this lecture we will learn how to build unconditional diffusion model. Firstly, we will download the necessary packages. So we will type !pip install diffusers package, datasets package, transformers package, accelerate package, ftfy package, pyro package, version 9.0.0. And here in this code we will use the GPU to make the training faster. So we will click on this runtime, we will click on change runtime type, and we will choose GPU. After that we will click on save. We will click on this symbol here. We will run this cell. Now let's import the packages that we want to use in this code. Firstly, we will import numpy package as MP. We will use this package to create arrays. And here we will import torch package. As we said previously, we will use PyTorch to build and train our network. And here we will import torch.nn.functional as f. We will use it to decide the loss function that we will use during training. And from matplotlib we will import pyplot as plt. We can use this library to visualize anything that we want. And finally, from pil we will import image. Okay, we will run this cell, so we will import all these things. Now we will learn how to download our dataset that we will use to train our neural network. Firstly, from datasets package we will import load dataset. Okay, and we will use this load dataset class to download our dataset. Here we will download the dataset from Hugging Face community. And here we will use Smithsonian's butterflies subset. And as its name suggests, it has images for butterflies. And here we made this split argument equal to train, because this load data set will return two data sets, training data set and testing data set. And here we want just the training data set. Okay, so we will take just the training data set. Now let's run this cell. And here is our data set. In this data set, we have 1000 images. And for each image, we have many different things, as you can see here, like the name, the gender, the region, etc. And of course, the image itself is also available here. So now, if we want to display just one image, how can we do that? Actually, the images are available in this image feature. Okay, so we will type dataset and we will specify the feature that we want from our dataset, which is image. This one here. So this feature has all the images in our dataset. We will select one of these images. Let's say we want to display the image 100. Okay, so let's run this cell. And that's it. As you can see here, here is our image. It is butterfly image. Now you should know that 1000 images, they are not enough to train our neural network. So we should increase the number of images. How can we do that? We will do something called data augmentation. To do that, we will import a transforms class from Torch Vision package. Okay? Now, firstly, we should resize our images to a smaller size, like 128 times 128. Here we will make the width and height for all images in our data set equal to 128 times 128. Why? Because we need all the images to be the same size before passing them through your neural network. When you decrease the value of image size, you will make the training faster. Why? Because the size of the images that you will pass through your neural network will be smaller. As we said previously, we will use transforms class to do data augmentation. The first thing we will do, like what we said previously, we will do resizing. So we will type transforms.resize, and here we will pass the new size of our images, which is image size. So the size of the height will be 128 and the width will be 128 also. And here we will apply another transformation on our data. Here we will flip our images randomly along a horizontal axis. By doing this, we will increase the training images. So we will type transforms.random horizontal flip. And you can also rotate your data randomly, but I didn't use this augmentation. And here we will convert our images into PyTorch tensors. As you know, PyTorch will create our model, so we need to pass PyTorch tensors through our model. It is not possible to pass NumPy arrays through our model because our model is created using PyTorch library. Finally, we will do normalization. As you know, each pixel can take a value between 0 and 255. And it is not good to pass an input with very large numbers. So we need to normalize our images, our pixels, and we will do that by normalization. We will make the value of each pixel between -1 and 1. And how can we do that? We need to use transforms.normalize, and here we firstly should pass 0.5, and here we should pass also 0.5. It is something good for training our neural network. Now, how can we apply all these transformations on our dataset? To do that, firstly we should create this function, transform function. This function will take the examples, or in other words our dataset itself, before doing any transformation. Here we will take the images from our dataset. We will pass it through each image, okay? And we will do the following. We will convert the order of the color channels for each image to be something like this: red, green, and blue. Why we need to do that? Because it is the correct order of these channels. But when they store them, the order will be BGR, which is not correct actually. And here we will do this thing for each image in examples. And after changing the order of the color channels for each image, we will pass each image through all these transformations that we talked about previously, and we will store each image after applying all this transformation on it in this list. Actually, this examples variable, it is just a small version of our data set, and we also call it a batch of samples. This transform function will apply automatically when we want to create a batch of samples, and we will talk about that later. Finally, this list that will have all the new images after applying all these transformations, we will put it in this dictionary. To make things more clear, let's say that we have a batch of samples, and let's say this batch has around 3 samples. Inside each sample we have an image, and here we will extract the images from these 3 samples. We will change the order of the color channels for each image, and we will apply all the transformations on each one of these images, and we will put the results in a list, and we will create a dictionary. The key of this dictionary is images. We will use this dictionary to get the images after applying all the transformations. PyTorch will use this transform function automatically when we want to get a batch to train our neural network on. And by using it, we will be able to increase the images that our neural network will see, because here we will apply data augmentation during training. And now we will type dataset.setTransform, and here we will pass this function. By doing this, we will make sure that we will apply this transform function on our batch before passing it through our neural network. But why we need to pass a batch of samples rather than just one sample at each training step? The answer is easy. As we said previously, PyTorch will compute the values that we will use to update the weights of our neural network. And when PyTorch uses many samples, or in other words, a batch of samples at each time to compute these values, so these values will be more accurate than using just one sample to compute them. And by doing this, we will make the training faster. Now we will create our data loader. This data loader will convert your data set into batches. Each batch will have many images. Okay, so we should specify the batch size. Let's say that the batch size equal to 16. Okay, which means that each batch will have 16 images or 16 samples. And here we will create our data loader. Train data loader equal to torch.utils.data.data loader, and here we will pass our dataset, and we will specify the batch size, which is this one here, and here we will make shuffle equal to true, which is also important for training. Now we will create our neural network. Firstly, we will import unit2D model from diffusers package. Here we will specify the device that we will use, and as we said before, we will use our GPU, so we should type CODA here. Now let's create our model. This unit2D model class from diffusers will make things very easy for us to create our neural network, our U-network. So firstly, we should type model equal to unit2D model, and here we will open these parentheses. And here firstly, we should pass the size of our image or sample size. It is equal to image size, which is equal to 128. And here we should specify the number of channels in the input, which is a 3. Our image, it is colorful image with 3 channels, red, green, and blue. And the number of output channels, or the number of channels in the output from this U-network, it is also 3. And we talked about this thing previously. The number of the feature maps in the predicted noise should be 3. And here we will specify the number of ResNet layers inside each block in our network. So now, what is ResNet layer? As you can see here, this is ResNet layer, which has convolution layer and ReLU activation function. And it will also have skip connection, that it will add the input and the output from ReLU layer. What is the advantage from this ResNet layer? This ResNet layer will solve the problem of gradient vanishing. What is gradient vanishing? When you increase the number of layers of your neural network, or in other words, make your neural network deeper. By doing this, when you want to update the weights of our neural network, you will start with the final layer or the output layer, and you will move backward. The values that you will use to update the weights of the layers of your neural network will get smaller and smaller during moving backward, which means that we will not be able to update the weights of the earlier layers of our neural network, because the values that we will use to update the weights of these layers will be very small values. ResNet layer will solve this problem by using these skip connections, which will create a direct path between the input and the output. We will use this ResNet layer inside our U-network to solve the problem of gradient vanishing. We will specify the number of layers per block, which is 2 in this case. Here we will specify the number of the feature maps that we will get from each block in our U-network. The first block will return 128 feature maps. The second block will return 128 feature maps. The third block will return 256 feature maps. The fourth block will return 256 feature maps. The fifth block will return 512 feature maps, the last block will return 512 feature maps. You should know that these out channels just for this part here, while this part here will just be the reverse order of these out channels. So the number of channels of the first block in this part here will be 512, the second block will be 512, the third block will be 256, the fourth block will be 256, the fifth block will be 128, and the sixth block will be 128. And of course the last layer in our U network will return 3 channels. Now we have 2 things that we should specify here. We have down blocks and up blocks. Here we have all these down blocks. The first down block, it is just down block 2D, which is regular ResNet downsampling block, which has a convolution layer, activation layer, pooling layer, and it also has a skip connection. And we will use them to create ResNet downsampling block. And the same thing in the second block, the third block, the fourth block, and here the fifth block, it is attention down block 2D. This block will also have special improvements. This block will do spatial self-attention. This self-attention mechanism will give our neural network the ability to focus on the most important regions inside our input image. The number of parameters inside this attention down block 2D will be very large if the width and height of the feature map that you want to pass it through this block are very large. For this reason, we put this attention down block 2D in this place here, where the width and height of the feature map that we want to pass it through this attention down block 2D will be very small. Because here we passed our input image previously through many down block 2D before passing it through our attention down block 2D. And after each down block 2D, the width and height of the feature map, of the input feature map, will get smaller and smaller. And here we have down block 2D also. Now we have up block types. Okay, here we have up block 2D, which will have transpose convolution layer, and also skip connections, activation functions, etc. And here we will use attention up block 2D. This block will also do spatial self-attention mechanism, and we put this block here for the same reason that we said previously when we talked about attention down block 2D, because the width and height of the input feature map will be very small here, so the number of parameters inside this block will be also very small, and the time that we need to apply this block on our input feature map will be very small. And we have all these up blocks 2D. Now that is our model. It is very simple. Diffusers package makes it easy for us to create it easily. Now we will send our model to our device, which is our GPU. By doing this, we will be able to train our model on our GPU, which will make the training faster. Now we will specify the noise scheduler. Firstly, we will import DTPM scheduler from diffusers package. Okay, and now we will use this scheduler. Firstly, we should specify the number of training time steps, and we will make it equal to 1000. and here we should specify beta scheduler, and we will make it squared cosine CAPV2. Okay. Now we have the noise scheduler that we will use it to add the noise to our image or input image. Here we will create the optimizer. This optimizer will be responsible about updating the weights of our neural network, and based on the values that our PyTorch give it to us. It will give these values to the optimizer, and the optimizer will update the weights of our neural network based on these values and on the learning rate. So optimizer equal to torch.optimizer.AdamW. There are many different types of optimizers, and here we use this one. Here we will pass the parameters, the trainable parameters of our model to this optimizer, and we will specify the learning rate, and we will make it something small, let's say 0.0004. Here we will create this losses list, okay, and here we will create this loop. We will activate this loop 100 times, which means we will train our neural network on 100 epochs. And for each epoch, we will pass it through each batch in our train data loader. Our train data loader will give us the batch, okay, and we will extract the images from this batch, and we will send them to our device, our GPU. Now we have our clean images. That's good. Now we will create our epsilon, which is the noise that we will get from the standard Gaussian distribution. Noise is equal to torch.random, and here we will pass the shape of our clean images. So the shape of the noise will be similar to the shape of our clean images, and we will send this noise to our GPU. The first dimension of our clean images, it is the number of images. How can we extract it? Clean images.shape, and here we will take the first dimension. So now we have the batch size, or the number of images in the batch. Now what we will do actually, we will take random time steps. Time steps equal to torch.randInteger. As you know, the time steps, they are integers, integer numbers. The range of the values between 0 and 1000. We made number of training time steps equal to 1000. And here we will pass the batch size. For each image in our batch, we should have time step. We will create time step for each image in our batch, and finally we will send our time steps to our GPU. Okay. Now we will create our noisy images. Noisy images equal to noise scheduler.add noise, and here we will pass our clean images and the noise and the time steps. Okay, now we have our noisy images. We will pass them through our model. We will pass the noisy images, the time steps, and we will get the predicted epsilon. Okay, like what we said previously. Here we will use mean squared loss function to compute the loss, the difference between noise prediction and noise, and we will get the result loss. We will do back propagation to compute the values that we want to use to update the weights of our neural network to reduce the difference between the predicted noise and the real noise. And we will add the value of the loss to our losses list. Okay, now the optimizer will use these values to update the weights of our neural network. So how can we do that? We should type optimizer.step. So now we updated all the weights. We will delete all these values inside the optimizer by doing the following: optimizer.zeroGradient. Let's run this code. Now the training finished. Let's use our stable diffusion model that we trained. Firstly, we should import DDPM pipeline from diffusers package. This pipeline will make it easy for us to use our unconditional diffusion model. So now we will type image pipe equal to DDPM pipeline, and here we will pass our model, our U network. So unit argument equal to our model, comma, and here we will pass our noise scheduler. So scheduler equal to our noise scheduler. Now we will use this pipeline to generate new images. So we will type image pipeline, and here we will pass the number of inference steps. We will start with the x1000 times step 1000, and we will move backward to x0. We call this process reverse diffusion process. Finally, we will get pipeline output, and here we will type pipeline output dot images, open these square brackets, and here we will put 0. By doing this, we will get our new image. Let's do it. And here's our image. This image is not available in our dataset. This image created completely using our diffusion model. If you want to generate another image, you can run this cell again and see another image. Here is another image created by our diffusion model that we trained previously. You can also reduce the number of reverse diffusion time steps. Let's make it 400, which means that we will move 400 time steps from time step 1000 to time step 600. By doing this, we will make the diffusion process faster, but you might get low quality image. Now let's say that you want to save your unconditional diffusion model. How can we do that? We will type torch.save, and here we will type model.state dictionary like this, and here we will pass the name of the file that will represent our model. We will run this cell. Now we saved our stable diffusion model. You can find it here in this place. We will click here, and here is our stable diffusion model. If you want to download this model, you just need to click on download. Okay? Thanks for watching. Hi everyone, in this video we will learn how to use any pre-trained model from Hugging Face community. Firstly, you should know that there are many different models in the Hugging Face community, and you can use any one of them, but you should have an account in Hugging Face community to do that. Firstly, like what we did in the previous lecture, we should change the runtime of our notebook, and we will use our GPU like this. Now we will download diffusers package and datasets package like this. Now we should log in to our Hugging Face account. How can we do that? Firstly, we should import notebook login from Hugging Face hub. After that, we will type notebook login like this, and we will run this cell. Here you should put your token. How can you create your own token? So to do that, we should go to our account, and we should generate our own token. click on this place here and click on edit profile, access token, and here you should copy your token and put it here in this place. After that you should click on login. That's it. Now you can download any pre-trained model from Hugging Face community. These pre-trained models are trained previously on specific tasks. Let's firstly import the packages that we want to use. We will import NumPy, Torch, and we will import torch.nn.functional as f and Torch Vision, and we will import load dataset from datasets, and we will import DDIM scheduler and DDMP pipeline from diffusers package, and we will import pyplot from matplotlib as plt, and we will import image from pil, and we will import transforms from Torch Vision. We will run this cell. Here we will use our GPU if it is available, otherwise we will use the CPU, which is much slower than our GPU. Okay. In this lecture we will take this pre-trained model, DDPM bedroom 256 model. Okay. So we will copy this model, and here we will download this model from Hugging Face community. So we will type DDPM pipeline from pre-trained, and here we will pass the name of the model, of our pre-trained model. After that we will send this pipeline to our device that we want to use. As you can see here, we will download this model. This model will generate images for bedrooms. Now you should know that they found it's not important to move 1000 time steps in reverse diffusion to get a good image. You can do that with just a few steps. How can we do that? Firstly, we will download the scheduler that they used to train this model, DDPM bedroom model. To do that, we will type scheduler equal to DDIM scheduler.from pre-trained, and here we should pass the name of our model that we want to use. By doing this, we will get the scheduler that they used to train this model, this diffusion model. Let's run this. Now we will set the time steps. So we will type scheduler.set time steps, and here we will make number of inference steps equal to 40. So we need 40 time steps to do reverse diffusion, to move from time step 1000 to time step 0. So let's see the time steps that we have right now. As you can see here we will jump directly from time step 1000 to time step 975, and we will jump from 975 to 950 time step, and we will jump from 950 time step to 925 time step. So now the number of time steps that we need to move from 1000 time step to 0 time step, it is very small, and the results will be good also. So now how can we use this scheduler? Firstly, we will create our image, which is, firstly, it is just pure noise. We will send it to our device, and the width and height of this image is 256. Why? Because our pre-trained model This pre-trained model trained previously on images with 256 width and height. So here we should make it 256 width and height. Okay. And this pre-trained model trained on colorful images. So each image will have 3 channels. This one here, we will make it equal to 1, okay, like this, which represents the number of images in the batch. As you know, if we want to use our model, if we want to pass anything to our model, we should pass it in form of batch. So we have a batch with just one image, which is this image. Okay. Here we will not use our simple pipeline to generate the image. Here we will use a more flexible way, but you can use our previous way by using our simple pipeline to generate the image. Now we will create this loop here. We will pass it through the time steps that we have. We will start from this time step, and we will move in reverse order like this to reach time step 0. Okay. Now we will prepare the input to our model. How can we do that? We will type scheduler.scale model input, and here we will pass the input, which is this pure noise, and the time step. Now we don't need to train our model, so we should use it inside this context manager. So we don't need to compute any values to update the weights of our model. Okay, now, as you know, we have this image pipeline, and our pre-trained model inside it, inside this pipeline. We will use our pre-trained U network, which is inside this image pipeline. We will pass the model input and the time step that we are in right now to this U network, and we will take the output from this U network, this pre-trained U network, which is our noise prediction, or our predicted epsilon. Now we will do reverse diffusion. So we will type scheduler.step, and here we will pass the predicted epsilon, the current time step, and the noise. Okay, so we will remove this predicted noise, predicted epsilon, from our noisy image to generate new image. Now we will make the noise equal to the output from our scheduler, or scheduler output. Okay, so now we reduced the noise inside our input a little bit, and we will do the same thing again and again until reaching time step 0. Okay, now we will run this loop, and now we will take x0, our clear image, from our scheduler by doing this. x0 equal to scheduler output dot predicted original sample. Here we will get a batch with just one generated image. We will take this image, so we will open square brackets and we will put 0. Okay, like this. So we have our clear image. We will reshape this clear image so we can visualize it. Here we will change the order of the dimensions. Previously it was the channel dimension or the color dimension, after that the height dimension, and finally the width dimension. Here we will make it like this. the height dimension, after that the width dimension, and finally the channel or the color dimension. We will do that by using permute method. And here we will type the order of the dimensions that we want. Here 1 represents the height dimension, and 2 represents the width dimension, and 0 represents the channel dimension. Firstly, we want to put the height dimension, so we should type 1, comma. After that, we want the width dimension, so we will put 2, comma. And finally, we want to put the channel dimension here, so we will type 0. As you know, we normalized our image, so we should change the values of the pixels to make them between 0 and 255 again. How can we do that? Here we will make any value greater than 1 in our image equal to 1, and any value lower than -1 in our image equal to -1 by using clip method. We will multiply all the pixels in our x0 image with 0.5, and we will add 0.5. So now all the pixels, the values of all pixels between 0 and 1, we can now multiply them with 255. Just something similar to bedroom. The quality is good with just around I think 40 steps. Thanks for watching. Hi, in this lecture we will talk about repaint algorithm. Let's say that we have a pre-trained diffusion model. This diffusion model will generate images for faces. Of course, we will start with a pure noise from the standard Gaussian distribution. We will start from time step 1000, and we will do reverse diffusion process to generate x0. Firstly, as you know, we will pass xt and the current time step through our U network, and our U network will return the predicted epsilon. We will use this predicted epsilon inside this Gaussian distribution to get the value of xt minus 1 variable, and we will reduce the value of time step by 1, and we will pass them again through our U network. So now we moved one step backward. We will do this again and again until reaching x0, our clear image. So now we have this generated image x0. Now let's say that you don't like the right part of your generated image. So firstly, we will remove this right part. Now this repaint algorithm will try to complete this part by using our diffusion model, our pre-trained diffusion model. But how can we do that? How this repaint algorithm works? Now we have x0 known, the known region, and x0 unknown, which is the unknown region of our image that we want to complete. And we will call this image x0 with mask. Okay? Now we will use this x0 with mask to move to time step t. We will use this Gaussian distribution to do that, and we will use it to get the value of xt variable. Now what we will do, we will pass the value of xt variable through our U network, and of course we will pass also the current time step. We will get the predicted epsilon, the predicted noise. We will use the predicted noise beta t, alpha bar t, alpha t, xt, and epsilon t to generate a Gaussian distribution that we will use to get the value of xt minus 1 variable. Now we will take just the unknown part from xt minus 1 variable. Here our diffusion model will automatically try to harmonize the unknown part of xt minus 1 variable with the known part. Our diffusion model will do this inherently during finding and removing the noise from xt variable. So now we can say that the unknown part of xt minus 1 variable, it is better than the unknown part of xt variable. And as you know, we have x0 with mask, which is this image here. We will use it with epsilon 0 that we will get from the standard Gaussian distribution, and the time step t minus 1 and alpha bar t minus 1 to create this distribution that will move us directly from x0 with mask to xt minus 1 with mask. We will take just the known part of xt minus 1, which is this area here, but after adding a noise to move to time step t minus 1. And as we said before, we will take just the known part of xt minus 1. But why we didn't took xt minus 1 known from this distribution from our diffusion model? We know this region, so why we need to use our diffusion model to predict this region in the first place? We just need to use our diffusion model to find the unknown area based on the known area. We will combine this known part with the unknown part of xt minus 1 that we got from this distribution and based on our U network. And as we said previously, this unknown part that we got based on our U network will be better than the unknown part in the xt minus 1 with mask variable that we will get from this distribution. As you know, the unknown part of xt minus 1 with mask variable, it is just a noise. But on the other side, this xt minus 1 unknown that we got from this distribution, and by using our diffusion model, it is better because our diffusion model will try to harmonize this region with the known region that we have in xt variable. So now this xt minus 1 unknown that we got from this distribution and based on our diffusion model, it is better than xt minus 1 unknown that we got from this distribution, and it is better than the unknown region inside xt variable. We will combine them together to get the value of xt minus 1 variable. But here in this xt minus 1 variable, the unknown part, it is better. It is more harmonized with the known region. Here we will check if we did a number of harmonization steps or not. Let's say that the number of harmonization steps equal to 10. So now we didn't complete 10 number of harmonization steps. So we will move here, and we will create this distribution based on the value of xt minus 1 variable, beta t minus 1, epsilon t minus 1 that we will get from the standard Gaussian distribution. This distribution, we will use it to move from xt minus 1 to xt. Now this xt, it is better than the previous xt because here the unknown region is more harmonized with the known region, like what we said previously. We will pass this xt through our U-network, and here we will not change the time step that we are in right now. We will stay on the same time step until finishing 10 number of harmonization steps. So we will pass the same time step again. Through our U-network, we will compute the predicted epsilon. We will generate the distribution that we will use to get the value of xt minus 1 variable. We will take just the unknown part of xt minus 1 variable, which is better than the previous xt minus 1 unknown part, because it is now more harmonized, because we did 2 harmonization steps now. And we will do the same thing. We will use x0 with mask and epsilon 0 and t minus 1 and alpha bar t minus 1 to generate this distribution that we will use to move from x0 to xt minus 1. We will take just the known part of xt minus 1, okay, and we will combine the known part with the unknown part here, and here we will check if we finished 10 harmonization steps or not. Let's say that the number of harmonization steps is 2. So we will activate this branch, and here what we will do actually, we will take the value of xt minus 1 and we will make xt equal to xt minus 1, and we will reduce the time step by 1. So in other words, it means that we moved 1 time step backward, which is our reverse diffusion process. And they found that it is better to not use repaint algorithm after each time step, but after a number of time steps. Let's say that after 10 time steps, we will apply this algorithm, this operation, this harmonization process. Let's say that we are at time step 1000, okay? And we will do the normal reverse diffusion. We will move 10 time steps backward, so we will reach 990 time step, and here we will do repaint algorithm. We will apply 10 harmonization steps during time step 990, and after finishing these harmonization steps, we will move 10 time steps backward and we will reach 980 time step, and we will apply harmonization steps again to harmonize the unknown part with the known part. So now, why we need to move 10 time steps before applying this operation? Because that they found that by doing this, we will make sure that the semantic information in our unknown part will match the semantic information in our known part in our x0 variable after moving 10,000 time steps backward. Now we will learn how to apply all these things practically. Hi, in this lecture we will learn how to implement repaint algorithm. Firstly, we will specify the device that we will use, which is our GPU. We will use it to make the inference faster, or in other words, we will use it to make the reverse diffusion faster. Okay, and here we will install diffusers package, datasets package, and transformers package. Here we will import DDPM pipeline from diffusers package, and here we will create this variable, model ID variable, which represents the path of the model that we want to use. Here, the diffusion model that we want to use. Here we will load pre-trained model. This model, it is able to generate images for bedrooms. The width and height of the images that we will get from this model equal to 256. As you can see here, we will take the path of model ID from Hugging Face community like this. And as you can see here, this pre-trained diffusion model will generate images for bedrooms. Okay. Now we have the model ID. We will download this model. We will type pipeline object equal to ddpm pipeline dot from pre-trained, and here we will pass the model ID. And here we will send our pipeline to our device that we want to use, which is our GPU. By doing this, we will make our model, our diffusion model inside our GPU, so we can get the results from our U network or our diffusion model faster. And now we can use our pipeline, our diffusion model, to generate the images like this, pipeline.images. And here we will get the image, and we can save it here in this place. Okay. And here we will pass the name of the file that will represent our image. So we will type image.save, and here is the file name of our image, which is clearimage.png. Now we have our clear image. I previously used the diffusion model to generate this image, and I created a mask for this image, which is this one here. Also, we will keep the information in our clear image that corresponds to the white regions in the mask, while we will delete the information in our image that corresponds to the black regions in our mask. Okay. And now we should know that each pixel inside these white regions equal to 255, while each pixel inside these black regions equal to 0. If you want to know how I created this mask, it's easy. Let's say I have this image in my desktop, and now I will create a copy for this image. Let's change the name of this copy like this. I will call it mask. Okay. Now I will open it using Paint program. I will zoom in like this. And now what I will do, I will make the regions that I want to keep. I will make them white regions. So how can I do that? I will click on this place here. Let's say that I want to keep this window as it is. So I will click here and drag this, and that's it. Now I will click on delete. So now this place, it is white, which means we will keep this part of this image. Let's say that we want to keep this thing also. We will do the same thing. We will click here and we will surround this area here, and we will click here and select delete. So now we will keep this region also because it is white. Let's say that we want to keep this region also, so we will click here and we will surround this region. After that, we will click here, right click, and we will click on delete like this. It is white region, so we will keep it also. Now we will mask the regions that we want to change in our image. So like this region, we don't want this region. Okay, how can we do that? How can we replace this region with a black? It's easy. We just need to click here and we will select black like this. Now we will click on delete. Okay, so now we mask this region, or we removed this region. Our diffusion model will try to complete this region with something new. We will do the same thing here. We don't want all these things here, so we will click on delete like this, and the same thing here, delete, and the same thing here. We will mask this region also like this, and we will mask this region also like this. Okay, now we have our mask. We also need to remove this part here. Okay, that's it. We will save this new image, this mask. We will click on Control S like this. So now we have our mask. We can put it here and we can use it in our code like this. Okay, so now we have our mask and we have our clear image. So now what we should do here, let's go ahead and see. As we said previously, we have two images. Our clear image, which is this. We will load this clear image. How can we do that? Firstly, we will import cv2 OpenCV library, and we will import transformers from Torch Vision, and we will import PyTorch and NumPy as MP, and we will import TQDM notebook as TQDM from TQDM. Okay, now we will download our image from here. So we should copy the path like this. We should click on these points here, and we should click on copy path like this, and we should put it here in this place like this. Okay, and here we should use image read method from cv2 to read this image, and between these two parentheses we will put the path of our image. So now we have our clear image. We will change the order of the color channels from BGR to RGB. We will use this method CVT color from CV2 library, and here we will pass our image, and here we should pass the old order and the new order of the color channels, which is CV2 dot color BGR to RGB. Now we have our image, and now we will load the mask. So we will use cv2 dot image read, and here we will pass the path of the mask like this. We will click here and we will click on copy path, and we will put it here between these two parentheses like this, and here we will get the mask, and we can also change the order of the color channels. Now what we will do, we will normalize our image. Our diffusion model, our U-network, our pre-trained diffusion model expects that the input image to it should be between -1 and 1. The values of the pixels inside our input image should be between -1 and 1. So firstly, we will divide our image by 255, which means that the highest value that our image can take, it is 1, because as you know, the highest value for any pixel, it is 255. So the highest value now equal to 1 after dividing by 255. So now the values of the pixels inside our image between 0 and 1, we will multiply these values by 2. So now the highest possible value for any pixel in our image will be 2. So the values of the pixels now between 0 and 2. We will subtract all these values by 1. Okay? Which means now the range of possible values for each pixel in our image will be between -1 and 1. So the highest possible value for any pixel in our image will be 1, while the lowest possible value for any pixel in our image will be -1. If the value of any pixel previously equal to 0, now it is equal to -1. While if the value of any pixel, if it is previously equal to 255, now it is equal to 1. So now we have our normalized image, which is NumPy array. We will convert it into PyTorch tensor using this method, torch.tensor, and here we will pass our image, and we will pass the data type of this tensor, which is float32. As you know, the value is here of the pixels between -1 and 1, which means that the values of the pixels are fraction numbers. And we can use this data type float32 for these numbers. Now we will change the order of the dimensions. As you know, the first dimension in our image, it is the height dimension, and the second dimension, it is the width dimension, and the last dimension will be the color dimension. We will make the last dimension, the color dimension, we will make it at the first, and we will make the height dimension after the color dimension, and finally we will put the width dimension. And we can do that using this method, permute method. Now, as you know, our U network expects that the input to it is just a batch of samples. So here we need to add the dimension that represents the batch size. How can we do that? Image.nSequence, and here we will put the place that we want to add this dimension in, which is 0. So now we can say that we have the following. So now our image has the following dimensions. Firstly, the batch dimension. After that, we have the color dimension like this, and after that we have the height dimension, and finally we have the width dimension like this. This batch dimension, it is equal to 1. By using nSequence method, we will add a new dimension with length 1. This new dimension, it is this batch dimension, and the length of it is 1. And we put this dimension here because we put it 0 in this place here. And our U network expects that the first dimension, it is the batch dimension. While previously, the order of the channels was the following: the color dimension, height, and width. And before that, the order of the dimensions was as the following: height dimension, width dimension like this, and finally color dimension. Okay, so now we will send our batch or our image. It is just a batch with one sample, one image. We will send it to our CUDA, our GPU. Now we will work on the mask. Okay, now as you know, the pixels that represent the white regions equal to 255, while the pixels that represent the black regions equal to 0. So now we will make the pixels that represent the white region equal to 1. So we will divide our mask by 255. So now the white pixels equal to 1 while the black pixels equal to 0. We don't need to put the values of the pixels between -1 and 1 here. That's what we should do with the mask. We just need to make the pixels that represent the white region equal to 1 and the pixels that represent the black region equal to 0. And we will also create PyTorch tensor from this NumPy array by doing this torch.tensor, and here we will pass the mask and the data type of the tensor that we want to create, and here we will change the order of the dimensions. We will put the color dimension at the first, after that we will put the height, and finally we will put the width. Okay, and here we will add the batch dimension at the first, and now we have our mask. We will send it to our CUDA, our GPU. Here what we will do, we will multiply our image, our clear image, with the mask, and we will get x0 with mask, like what we said previously in the previous lecture. Now we have x0 with mask. Now what we will do, we will create these variables. The first variable is harmonize steps, which is equal to 10, which means at any specific time step, we will do 10 harmonization steps. And here we have this variable, semantic steps variable, which is equal to 10, which means that we should move 10 time steps before doing repaint algorithm. And here we will get the scheduler from our pipeline. So we will type pipeline.scheduler, and here we have our scheduler. Here we will create a noise. We will type torch.random, and here we will pass the shape of x0 with mask to this method to make the shape of the noise that we want to create, same as the shape of our masked image. And we will send this noise to our GPU, okay, which is the same device that our x0 with mask it is available in. And this noise, it is just the epsilon that we can get from the standard Gaussian distribution. Now what we will do, we will create this loop. So we will type for I in TQDM. This TQDM will make us able to track the progress of the generation of our image. And here we will type range, and inside the range we will take the length of the scheduler.timesteps. Here we will get the number of time steps, okay, that we will do in reverse diffusion. And here we will convert this number into a list from 0 to the total number of time steps. We will pass it through each element in this list. Okay, so now at each repetition of this loop, we will get the time step that we are in right now. So t, which is the time step, the current time step, it is equal to scheduler.time steps, and here we will pass the index of the time step that we are in right now, which is this I here. Now we will check if it is the first iteration of this loop. If I equal to 0, it means it is the first iteration of this loop, which means we are at time step t capital, the first time step in reverse diffusion. Here we will make this xt equal to the noise that we created here. Okay, as you know, we will start with noise, with a pure noise, with Gaussian noise. We will make xt equal to a Gaussian noise that we took from the standard Gaussian distribution. Now we will create another noise, and here what we will do, we will create xt minus 1 with mask. We talked about this thing previously. How can we get this thing, this tensor? It is equal to scheduler.add noise, and here we will pass x0 with mask, and we will pass the noise, this one here, and we will pass time step t minus 1. So now we have xt minus 1 with mask. We will take just the known region from this xt minus 1 with mask, as we said in the previous lecture. Now what we will do, we will create this condition. We will check if we finished 10 time steps or not. We will use modular operation to do that. So we will type I modular semantic steps equal to 0. If it is the case, if we moved 10 time steps backward, at this case we can do harmonization steps. So all these 10 time steps, all these previous 10 time steps are for semantic matching between the known and unknown part. And now after completing these time steps, we will do our harmonization steps at the last time step that we reached. We will do this thing after finishing each 10 time steps. Now we will create this for loop. We will use it to do the harmonization steps. So we will type for h in range, and we will pass the number of harmonization steps to it. So if the number of harmonization steps equal to 10, at this case we will get this list from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we will pass it through each element in this list, and we will do the following. Firstly, we will type with torch.no gradient. Here we don't want to compute the gradients because, as you know, we don't need to train our U-network here. We just need our U-network to generate the images. We don't need our neural network to update its weights. Okay, so firstly we will prepare the input to our U-network. How can we do that? We will type xt model input equal to scheduler.scale model input, and here we will pass xt and the current time step. So now we have xt model input that we can pass it through our U-network. So now let's pass it through our U-network. So noise prediction, or predicted epsilon, is equal to pipeline.unet, and here we will pass xt model input and the current time step, and we will get the predicted epsilon. We will use it to get the predicted xt minus 1. Okay, so predicted xt minus 1 is equal to scheduler.step, and here we will pass noise prediction, the current time step, and xt, which is this one here, dot previous sample, And here, by doing this, we will generate a Gaussian distribution based on these things, and we will take the value of xt minus 1 from that distribution, which is a predicted xt minus 1. And as we said in the previous lecture, we will take just the unknown part from this tensor, and we will combine it with the known parts of this tensor. And that's what we will do here. Xt minus 1, it is equal to predicted xt minus 1 times 1 minus the mask plus xt minus 1 with mask times mask. So what we are trying to do here, 1 minus mask, it means that we will make the pixels that represents the black regions equal to 1, while the pixels that represents the white regions equal to 0, which means that we will mask the pixels of the known region, while we will keep the information about the pixels of the unknown region. Okay, and here what we will do, we will mask, or we will remove the information of the unknown region inside this xt minus 1 with mask, while we will keep the information of the pixels of the known regions. So we will make this thing here, we will make it fill the unknown region in this thing here, and we will get this xt minus 1. Now what we will do, we will create a noise from the standard Gaussian distribution like what we learned previously. And here we will create a noise from the standard Gaussian distribution, and we will send it to our device. And here we will check if we completed the 10 harmonization steps or not. If we didn't finish 10 harmonization steps, so at this case we will use this xt minus 1 to create this Gaussian distribution, and based on what we learned in the math behind the diffusion models, we can move from xt minus 1 to xt by doing the following: xt minus 1 times the square root of 1 minus beta t minus 1 plus the square root of beta t minus 1 times the noise, which is the previous equation that we used to move from xt minus 1 to xt. But if we completed 10 harmonization steps, at this case we will make xt equal to xt minus 1. So now let's say that we didn't finish 10 time steps. So at this case we are in the semantic steps. So what we will do here, firstly we will prepare xt to pass it through our U-network. So xt model input equal to scheduler.scale model input, and here we will pass xt and the current time step. This time step now, it is semantic step, and all the time steps that we need to complete 10 time steps, we will call them semantic steps. And when we complete 10 time steps, we will do our repaint algorithm inside the last time step that we reached. Here we will use our U-network noise prediction, or predicted epsilon is equal to pipeline.U-network. Here we will pass xt model input, and here we will pass the current time step, and we will get predicted epsilon. Okay, now we will get xt minus 1 using the predicted epsilon, the current time step, and xt. So we will type xt minus 1 is equal to scheduler.step, and here we will pass noise prediction, the current time step xt dot previous sample. And here we will make xt equal to xt minus 1. As you can see here, these semantic steps, they are just a regular reverse diffusion process. That's it. That is our repaint algorithm, like what we said in the previous lecture. Now, let's see the results. Firstly, let's display our original clear image, which is this. As you can see here, I generated many images to fill the mask region. So as you can see here, our diffusion model kept the window as it is, like this, because here our mask here it is white in this region, which represents our window, and our diffusion model, and using our repaint algorithm, changed the bed. As you can see here, it is different because it is available in this black region in our mask. So now it is different. And our diffusion model kept this place here because it is white in our mask. Now let's see another results, and you can see our diffusion model changed the pad many times. Here is another version, and here is another version here, but all these images have the same window, and as you can see here, and here is another version for the bed. Now as you can see here, we could fill the masked region using our diffusion model, and you can use the same algorithm to work with many different pre-trained diffusion models. Thanks for watching. Hi, in this lecture we will learn how to speed up our diffusion model. The diffusion model that we used previously, we call it DDPM diffusion model. In that model, we needed to move 1000 time steps backward to generate new image, which means that we needed to use our diffusion model 1000 times. At each time, we will move just one time step backward, and that's because the Markov chain. As you can see here, the distribution of x2 variable will just depend on the value of x3 variable. And the distribution of x1 variable will just depend on the value of x2 variable. And of course, the distribution of x0 variable will just depend on the value of x1 variable. So, we should move from x3 to x2, and from x2 to x1, and from x1 to x0. And that's not good, because if the number of time steps that we need to generate any image is large, let's say 4000, in this case we will take long time to generate any image. In other words, we will use our diffusion model 4000 times to generate any image. In this example, we need to use our diffusion model 3 times. Here to move from x3 to x2, and here to move from x2 to x1, and here to move from x1 to x0. So now how can we break this Markov chain? We will do that by using our reparameterization trick. Previously we said that our loss function, it is just the difference between the target noise, the actual noise that we added to our clear image, and the predicted noise that we will get from our U network after passing xt variable and the current time step. And based on the reparameterization trick, we can say that xt, it is just the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon, which is just a noise from the standard Gaussian distribution. And here we will also pass the current time step. Okay. So now we have xt and we have the predicted noise. And based on the reparameterization trick, we can also move from xt to x0 directly. How can we do that? The predicted x0, it is equal to 1 divided by the square root of alpha bar t times xt minus the square root of 1 minus alpha bar t times the predicted noise after passing the value of xt variable and the current time step to our new network. This formula, it is just the formula that we got after applying the reparameterization trick. But here we want to find x0, not xt. So let's say that we are at time step 3 here in this place, and we want to move directly to x0 like this. We can do that using this formula here. But of course, this x0, the predicted x0, will not be good, where we need to move many time steps to make the predicted x0 gets better and better. But the idea here is that we can jump from any time step to x0 directly using this reparameterization trick. So based on what we said, we broke the Markov chain here. We jumped directly from x3 to x0. And because that we will not get good quality image if we jump directly, let's say, from x3 to x0, so we will not jump directly from, let's say, the first time step to the final time step t capital to time step 0, but we will use this property to reduce the number of time steps that we need to move from time step t capital to time step 0. How can we do that? The idea is easy. Based on the formula that we got after applying reparameterization trick, xt equal to the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon t. Epsilon here, it is just a noise that we will get from the standard Gaussian distribution. Epsilon t, it is same as epsilon t minus 1 and epsilon t minus 2 to epsilon 0. And based on this formula, we can say also that xt minus 1 is equal to the square root of alpha bar t minus 1 times x0 plus the square root of 1 minus alpha bar t minus 1 times epsilon. By using this formula, we can jump directly from x0 to xt minus 1. And you should know that we can find the predicted x0 at any time step. So now, let's substitute the value of the predicted x0 here, this place, and we will get the following, this formula here. Xt minus 1 will be equal to the square root of alpha bar t minus 1 times xt minus the square root of 1 minus alpha bar t times the predicted epsilon, like this, divided by the square root of alpha bar t, which is this thing here. So now we can find the value of the predicted x0 just by knowing the value of xt variable and the predicted noise. at time step t, plus this thing here, which is the square root of 1 minus alpha bar t minus 1 times the predicted epsilon. Here we will not take the epsilon from the standard Gaussian distribution to move from x0 to xt minus 1, but we will use our U network to find the predicted epsilon that we can use to move from x0 to xt minus 1. And now we can say that this xt minus 1 variable, it is not a distribution, it is just specific value that will depend on our U network, the predicted noise from our U network. By using this formula, we will get the value of xt minus 1 variable. This thing here, it is the predicted x0, and here it's like that we are trying to move from the predicted x0 to any time step. In this case, time step t minus 1. So let's say that we have 4 time steps. Let's call this one the predicted x0. Okay, now here we have x1, x2, x3. What we want, actually, we want to make this reverse diffusion process faster. We want to reach the clear image faster with a few number of time steps. How can we do that? Let's say that we are at time step 3. What we will do based on this formula, we will jump directly to the predicted x0 based on this formula here. So now we are at time step 0, and now we have this predicted x0. It is not good because we need to move few time steps to make it better, but now we are at time step t0. What we will do here, we will add a noise to move us from this predicted x0 to any time step. At this case, we need to jump this time step 2. So we will add the noise to move us to x1 like this. So we will use our U network to find the noise that will make us move from the predicted x0 to x1. But now you might ask yourself, this noise, it is just will make us move from xt to xt minus 1. But actually, based on the reparameterization trick, we just add a noise to the clear image like this, and it means noise, and we scaled them by specific amount. Let's say 1 minus alpha bar t, and this one here alpha bar t. So here we are trying to find this noise, and we can scale it as we want to move it to any time step. Here in this case, time step t minus 1. But we can make it t minus 10, t minus 30, and something like that. As you know, we need to jump a few time steps to make the generation process faster or the reverse diffusion process faster. So now we will move from the predicted x0 to x1. So we jumped this time step, And we can actually jump more than one time step, like 30 time steps, or actually we can generate good images with just 50 time steps. For example, let's say that we will start with time step 1000, we will jump 20 time steps, and we will reach time step 980. We will jump 20 time steps again, and we will reach time step 960. By doing this, we will just need 50 time steps to move from time step 1000 to time step 0. While in DDPM we need to move 1000 time steps, but here we can move just 50 time steps to generate the same images. Now we are at time step 1. We can also do the reverse diffusion to move to x0 like this. So now this predicted x0, it is better than the predicted x0, the previous predicted x0, because this predicted x0 generated from 2 time steps. If we want to mix between the DDIM and DDPM, we can add a noise from the standard Gaussian distribution. We will add this standard deviation and this here to make it DDPM and DDIM at the same time. But here in DDIM, the most important thing here, we will not add a noise, so the generation process it is deterministic. Which means if you start with the specific noise, okay, and do the reverse diffusion with the DDIM model, you will get, of course, an image. And when you use the same noise and do the reverse diffusion again using our DDIM model, we will get the same image. We will not get another image because here the generation process it is deterministic. But it's not the case with this thing here, with this formula here, because here we are trying to mix between DDPM and DDIM, so we will get many different images for the same noise. Thanks for watching. Hi, in this video we will learn how to do reverse diffusion using DDPM and DDIM and what is the difference between them. Firstly, we will download datasets package, transformers package, FTFY package, pyro package, and of course diffusers package. Now we will import the necessary packages. Firstly, we will import numpy as np, and we will import torch package, and we will import torch.nn.functional as f, and we will import pyplot as plt from matplotlib, and we will import image from pio package. Here I will create my model, so we will import unit 2D model from diffusers package. Here we will specify the device that we want to use, which is our GPU, so we will load our model in our GPU. Here we will create our model like what we did previously. Now we created our model. Here we will send our model to our device that we want to use, which is our GPU. Now I have a model that I trained previously on butterflies images, okay, and it's available in my Google Drive. So I will click here, I will click on this place here, we should click on this symbol here, okay. You should have Gmail account to get Google Drive, which will give you 15 gigabytes of free storage from Google that you can use to store your files in. Now we should open this folder and open this one, and here is our model. It's available here. Actually, if you have anything in the output of your Colab notebook and you want to put it in your drive, So you just need to drag and drop it in this folder here. For example, let's say that we have this model. We create this model here and we want to save it. How can we do that? We just need to type torch.save, and here you should pass the model, your model, and the name of the file that you want to use to represent this model, which is, let's say, model.pt, like this, and we will run this cell. That's it. You should update this place here, and you have your model. Just drag your model and put it in your Google Drive like this. So now this model that we created here, the weights of this model initiated randomly. The structure of this model similar to the pre-trained model structure, but the weights of this model, they are initiated randomly, so we need to put the pre-trained weights inside this structure. How can we do that? As we said previously, we have the file that represents the weights of our pre-trained model, the pre-trained weights. So we will type model.load state dect, and here we should pass torch.load, and here we will pass the path of the file that represents the pre-trained weights, which is this one here. Let's click here. If you want to get the path of this file, just click on these points and copy path like this, and we should put it here. Okay, now we have our pre-trained model. Firstly, we will import ddpm pipeline, ddpm scheduler, ddim scheduler. Let's create our scheduler, our noise scheduler. It is equal to ddpm scheduler, and here we will pass the number of training time steps, which is 1000, and beta schedule, which is squared cosine CAPV2. Here we will create image pipeline. Image pipeline, it is equal to ddpm pipeline, and here we will pass our pre-trained model to this unit argument, and we will pass noise scheduler to this scheduler argument. Here we should specify the inference time steps. We need to make it something like 50 or something like that to get good results. This ddpm scheduler will not use the inference formula for ddpm that we talked about in the first section. So it works even with a very small number of time steps, like 50, and here we will display this image. It is good image. Okay, now what we will do, we will take the scheduler from the pipeline, and here this scheduler will have the time steps. So we will set the time steps to be something like 950. So now we will move 950 time steps to generate any image. Now what we will do, we will use ddpm formula for inference. Firstly, we will create our xt variable, the value of xt variable, which is, firstly, it is just a pure noise from the standard Gaussian distribution. Now we will prepare the input to our diffusion model. So we should type model input equal to scheduler.scale model input, and here we will pass xt, and we will pass the current time step. Now we will pass the model input to our model our U network, and we will get predicted epsilon like this, and here we will get alpha t from our scheduler. So scheduler.alphas, and here we will pass the current time step that we are in right now. So we will get alpha t at this time step, and we will get alpha bar t at this time step. So we will type alpha bar t, it is equal to scheduler.alphas cumulative product, and here we will pass the current time step. So now we have alpha bar t. Now we will check if the time step it is not equal to 0. At this case, alpha bar t minus delta t, as we know here we will not write -1 but minus delta t, because we will jump fixed number of time steps at a time. So alpha bar t minus delta t, it is equal to scheduler.alphas cumulative product, and here we should take the next time step, or t minus delta t time step. How can we get this time step? We will get this time step from our scheduler. So scheduler.timesteps, and here we will pass I plus 1, which is the index of t minus delta t time step. So now we have t minus delta t time step. We will use it to get the value of alpha bar t minus delta t. While if t equal to 0, at this case we will make alpha bar t minus delta t equal to 1. Now we will get the value of beta t, which is equal to scheduler.betas, and here we will pass the current time step. We have alpha t, alpha bar t minus delta t, and beta t. Now we will compute the target beta, which is equal to 1 minus alpha bar t minus delta t divided by 1 minus alpha bar t, and we will multiply the result with beta t. And here we will create a noise that we will get from the standard Gaussian distribution epsilon at time step t. And now we will compute the value of xt minus delta t, which is equal to 1 divided by the square root of alpha t times xt minus beta t divided by the square root of 1 minus alpha bar t times predicted epsilon, and we will add the result to the square root of target beta times the noise, this one here. Now we have xt minus delta t. We will make xt equal to xt minus delta t, because now the current time step it is t minus delta t. This formula, this method, it will need a large number of time steps to create good image, like 950 or 1000 time steps. So it's not good, it will take time. How can we deal with this problem? This is the image that I created using this formula for inference. It is good, but it needs a large number of time steps. Now we will talk about DDIM. Firstly, we will make the number of inference steps equal to 200. We just need 200 steps to create our image. So we will type scheduler.set time steps, and here we will pass 200. And let's see the time steps that we have here. As you can see here, the first time step 995, and here we will jump to 990. Okay, like this. And so here we skipped 5 time steps, and the same thing here. We are at time step 990, and here we will jump to 985. So here we skipped 5 time steps. So it is faster, the number of time steps that we need to reach or to generate a good image, it is just 200 time steps, which is smaller than the previous formula. Firstly, we will create our xt value, which is, firstly, it is just xt capital. It is just a pure noise from the standard Gaussian distribution. Here we will pass it through each time step inside scheduler.time steps, which is this list here, this tensor. Okay, we will pass it through each one of these time steps. We will prepare our xt value, and here we will pass it through our model, our pre-trained model. So we will type predicted epsilon is equal to image pipe.unit, and here we will pass our model input and the current time step, and we will get predicted epsilon. Here we will take alpha bar t from our scheduler, so we will type alpha bar t is equal to scheduler.alpha's cumulative product, and here we will pass the current time step. So now we have our alpha bar t, which is alpha bar at time step t. Now we will check if t it is not equal to 0. In this case, we will get the value of alpha bar t minus delta t, which is equal to scheduler.alpha's cumulative product, and here we will find the value of time step t minus delta t. Okay, how can we do that? We will type scheduler.time steps, and here we will pass the index of t minus delta t, which is I plus 1. Let's say that we are at this time step, okay, 995. So at this case, this I it is just a counter. Its value, firstly, it is equal to 0, which is the first iteration for this loop, which is the index of this time step. So I plus 1 it is equal to 1, which is this time step, which is time step t minus delta t. So now we have t minus delta t. We will use this t minus delta t value as index for scheduler.alpha's cumulative product tensor to get the value of alpha bar t minus delta t. While if t it is equal to 0, in this case we will make alpha bar t minus delta t equal to 1. Here we will get the value of predicted x0, which is equal to xt minus the square root of 1 minus alpha bar t times predicted epsilon, and we will get the value here divided by the square root of alpha bar t. Now any value greater than 1 or less than minus 1, we will make it equal to 1 and minus 1. So how can we do that? Predicted x0 it is equal to predicted x0.clamp, and here we will type the following minus scheduler.configuration.clip sample range, which is minus 1, comma scheduler.configuration.clip sample range. Now we will compute the value of xt minus delta t, which is equal to the square root of alpha bar t minus delta t times the predicted x0, and we will compute the result here plus the square root of 1 minus alpha bar t minus delta t times predicted epsilon. Okay, and here we will make xt equal to xt minus delta t. Look at this amazing image here with just 200 inference steps or 200 time steps in reverse diffusion. It is very good, and we generated this image very fast. Thanks for watching. Hi, in this lecture we will talk about DDIM and out-of-domain images. Firstly, what is out-of-domain images? Let's say that we have a diffusion model. This diffusion model, we trained it previously on Butterfly's dataset, and we will use this diffusion model to generate butterflies images. Now we have all these images here. The first image, it is butterfly image, so we will call it in-domain image, because as we said previously, we trained our diffusion model to generate images for butterflies, and this image, it is butterfly image. And the same thing here, here, and here. But what about this image and this image? These two images are out of domain images. Why? Because we didn't train our diffusion model to generate these images. We trained our diffusion model just to generate images for butterflies. Now, let's say that we have this image here, and we want from our diffusion model to generate xt capital from this clear image. Is that possible? It is not possible with DDPM, because the forward diffusion in DDPM, it is stochastic. But what about DDIM? As we said previously, DDIM, it is deterministic. Now, we want to do forward diffusion using DDIM. We want to make this forward diffusion deterministic, and we want to, from our diffusion model here, to create or to generate the noise xt capital, and when we do reverse diffusion on this noise, we will end up with the same clear image. How can we do that? Previously, we talked about how to do reverse diffusion using DDIM, and here is the formula of reverse diffusion with DDIM. xt minus delta t, it is equal to the square root of alpha bar t minus delta t times xt minus the square root of 1 minus alpha bar t times the predicted epsilon after passing xt and the current time step, divided by the square root of alpha bar t plus the square root of 1 minus alpha bar t minus delta t times the predicted noise after passing xt and the current time step t. Now this is the formula for reverse diffusion. Now let's create the formula that we will use to do forward diffusion with DDIM sampling algorithm. xt plus delta t, it is equal to the square root of alpha bar t plus delta t times xt minus the square root of 1 minus alpha bar t times the predicted epsilon after passing xt and the current time step, divided by the square root of alpha bar t plus the square root of 1 minus alpha bar t plus delta t times the predicted noise after passing xt and the current time step t. We will use this formula to do forward diffusion with DDIM sampling algorithm. As you can see here, this formula that we will use to do forward diffusion, it is deterministic. Why? Because here we didn't take a random noise from the standard Gaussian distribution, and all these things here, they are constants. So now, as we said previously, we will start with this clear image, which is x0, and we will use our U network and this formula here to move to x delta t. Previously we said that we can use DDIM to make the reverse diffusion faster, and here in forward diffusion the same thing. Our DDIM sampling algorithm will make the forward diffusion faster. So here we jumped a few steps and moved from x0 to x delta t. And now we have x delta t. We will use our formula here to jump from x delta t to x 2 times delta t. And we will do the same thing again and again until reaching xt capital. This xt capital, it is deterministic. When we start the forward diffusion with this image, we will get specific xt. capital, specific noise. When we start with xt capital with this noise and do reverse diffusion, we will end up with the same image. So now we are able to generate the noise xt capital for each one of these in-domain images. But what about these out-of-domain images? Is it possible to find xt capital for them? Yes, that's right. We can find xt capital for these out-of-domain images using the same formula. Let's say that we have this out-of-domain image, which is x0. We will do forward diffusion using DDIM sampling algorithm, and we will generate the noise xt capital that related with this image. This noise xt capital, we will start with this noise and we will do reverse diffusion, and we will end up with the same image x0. So now, even though that our diffusion model didn't train previously to create these kind of images, these out-of-domain images, but using DDIM sampling algorithm, we could generate the noise xt capital for each one of these images, and our diffusion model will be able to use this noise xt capital to generate the same image again by doing reverse diffusion. So now, what is the advantage of moving from a clear image to xt capital? We will answer this question in style transfer lecture. Now we will try to implement all these things practically. Hi, in this lecture we will learn how to do forward diffusion using DDIM practically. Firstly, we will import CV2 OpenCV package, and we will import transforms from Torch Vision package. Here we have an image. The name of this image is 1. It is available in our Colab notebook. Let's click here. Here is our image 1.jpg. Let's click on our image and see our image. This image, it is out of domain image. Okay, it is not an image for butterfly, so it is out of domain image. What we will do, actually, we will open this image here. Now x0, which represents our image here, it is equal to image dot open, and here we should pass the path of our image. How can we find the path of our image? We just need to click on these 3 points here, and we will click on copy path, and we will put it here. Now we have our image, our out of domain image, which is x0. Our pre-trained model, the model that we trained previously to generate images for butterflies, this diffusion model expects that the input to it, the size of the input to it, should be 128 times 128. 128 height and 128 width. So now we have this image with this new size. Now we will specify the device that we will use to do forward diffusion. And here what we will do, actually, firstly we will convert this image, this out of domain image, we will convert it into NumPy array. Okay, and we will add a new dimension to this array. The length of this new dimension will be 1, and we will put it firstly. So the dimensions of this image now will be 1, which is the new dimension that we added using n-squeeze method. And when we put 0 here, which means that we want to put this new dimension firstly. After that, we will put the second dimension, which represents the height dimension. The length of this dimension is 128. And we have the width dimension, and the length of this dimension will be also equal to 128. Finally, we have the channel dimension or the depth dimension, which is equal to 3, because as you know, we have 3 color channels: red, blue, and green. Now we have this new array here. We will convert this numpy array. This array is numpy array, as you can see here, because here we used np.array. We will convert this numpy array into PyTorch tensor using transforms.toTensor, and here we should pass our array. So now we will get a tensor, and here this method will do normalization automatically. So it will make the values of the pixels of our image between 0 and 1. The highest possible value in this tensor should be 1, when the value of the pixel equal to 255, and the lowest value inside this PyTorch tensor will be 0 if the value of the pixel equal to 0. Now what we will do, we will multiply this tensor by 2, which means that we will make the highest possible value inside this tensor equal to 2, while the lowest value in this tensor equal to 0. Finally, we will subtract 1 from this tensor, which means that we will make the lowest possible value equal to -1, and the highest possible value inside this PyTorch tensor will be equal to 1. So we finished the normalization process. Now the highest possible value in this x0 will be equal to 1, and the lowest possible value in this tensor x0 will be equal to 0. Now we will send this x0 to our device. So now we put this image in our GPU. We will make x0 equal to xt. Now at the first time step, t equal to 0. So it is equal to x0. At the first time step in forward diffusion, the time step equal to 0. So we will make xt equal to x0. Now what we will do, we will create this function. So we will type define get x capital using DDIM sampling algorithm. Here we will pass xt, and we will pass our diffusion model and the device that we want to use to do forward diffusion. Now what we will do, we have our diffusion model. We will take the scheduler from this diffusion model, and we will take the time steps tensor from this scheduler. And here we will type dimensions, and we should put 0 here. This tensor, this time steps tensor, it is just one-dimensional tensor. This tensor has just one dimension, which is dimension 0. Now, this tensor will start with the time step t capital, which is the first time step in reverse diffusion and the last time step in forward diffusion. And because here we want to do forward diffusion, we should flip this tensor to make the first time step equal to 0. So what we will do actually, we will use a flip method from torch. So we will type torch.flip, and here we will pass this tensor. Now we have time steps tensor. It will start with time step 0 and it will end with the last time step, or time step T capital. Now what we will do, here we will take all the time steps, but we will delete the final time step, the last time step, the time step T capital. How can we do that? We will type T equal to time steps, and here we will open these square brackets. Here we put this column here, which means all the time steps, and this one here, -1, represents the index of the last element in this tensor, which represents T capital time step. So we will take all the time steps, but we will not take the last time step. And we will make the name of this tensor T. Now we will create another tensor, which is T next. This tensor is equal to time steps, and we will open these square brackets and we will put 1 column, which means that we will take all the time steps, but we will not take the first time step, which is time step 0. Okay? Now we have this new tensor, T next. So now we have T and T next. The first element in tensor T equal to 0, which is the first time step 0. And the first element in tensor T next will be equal to delta T, which is the next time step after time step 0. Now let's say that the current time step it is delta T, which is the second element in tensor T. So now the next time step will be equal to 2 times delta T, which is the second element in tensor T next. In general, this tensor will have the current time steps, and this tensor will have T plus delta T time steps. Now we will create this loop here. Firstly, we have two tensors T and T next. We will pass it through each element inside these two tensors using ZIP method. So firstly, let's create our loop for n, comma. Here we will get I and j in enumerate, and here we will type ZIP. We will convert this PyTorch tensor into list, and we will convert this tensor into list also. So at each iteration, we will take an element from this tensor, and at the same time, we will take an element from this tensor. And we will do this again and again until reaching the last element in this tensor and this tensor. And each time we will get a value for I and j. I represents the current time step, while j represents the next time step, or time step t plus delta t. And here n represents the number of the current iteration of this loop. Now what we will do, we have our diffusion model, and we will prepare the input to our diffusion model. So model input, it is equal to diffusion model.scheduler.scale model input, and here we will pass xt, which is firstly equal to 0, and here we will pass the current time step I. And now we will send this input to our device. Now we have our model input. Now we will do forward diffusion. Firstly, we will take the predicted epsilon from our diffusion model. So we will type with torch.node gradient to avoid computing the gradients because we don't need them. We don't need to update the weights of our diffusion model. We just need to use it to do forward diffusion. And here we will compute the predicted epsilon. So predicted epsilon t, it is equal to diffusion model.unit. And here we will pass our model input and the current time step, and we will get predicted epsilon t. Now what we will do, we will find alpha bar t plus delta t, which is equal to diffusion model dot scheduler, and here we will take this alpha bar t plus delta t from alpha's cumulative product, and we will pass time step t plus delta t. So now we have alpha bar t plus delta t. Now we will find the value of alpha bar t, which is equal to diffusion model dot scheduler dot alpha's cumulative product, and here we will pass the current time step t. Now we will compute predicted x0, which is equal to xt minus predicted epsilon t times 1 minus alpha bar t, and here we will take the square root of this thing here by using .sqrt method divided by alpha bar t .sqrt, or in other words the square root of alpha bar t, and based on our previous formula. And here we will compute xt plus delta t, which is equal to alpha bar t plus delta t dot sqrt, which is the square root of alpha bar t plus delta t, times predicted x0 plus 1 minus alpha bar t plus delta t dot sqrt, which means the square root of 1 minus alpha bar t plus delta t times predicted epsilon t. And now we will make xt equal to xt plus delta t. And here we didn't use a clip method to make the highest possible value equal to 1 and the lowest possible value equal to minus 1 in this predicted x0, because this will restrict the xt capital that represents this image, which means that we will not be able to get the same image x0 when we do reverse diffusion on the xt capital that we will get when we use a clip method on predicted x0. Now finally we will make xt equal to xt plus delta t, and we will do this thing again and again until reaching time step t capital, and finally we will make xt capital equal to xt, and we will return this xt capital. Now let's do that. Let's compute xt capital for this image here. Xt capital equal to, here we will call our function get xt capital using DDIM, and here we will pass xt, which is firstly equal to x0, and we will pass image pipe, which is our pipeline for our diffusion model, and we will pass the device that we want to use, which is our CODA, our GPU. Here we will import PIL, and we will type pil.image.from array, and firstly we will take the first sample in this xt capital. This xt capital, it is just a batch with one sample. We will take this sample from this batch. As we said previously, we added this dimension, which represents the batch dimension, and the length of this dimension equal to 1, which means that we have just one sample in this batch. We will take this sample and we will change the order of the dimensions of this sample. Firstly we will put the height dimension, after that we will put the width dimension, and finally we will put the color dimension. Now we will send this sample to our CPU, and we will clip all the values to make them between -1 and 1. the highest possible value should be 1 and the lowest possible value equal to -1. And we will multiply this tensor with 0.5, which means that we will make the highest possible value in this image equal to 0.5 and the lowest possible value in this image equal to -0.5. And we will add 0.5, which means that we will make the highest possible value in this image equal to 1 and the lowest possible value in this image equal to 0. Finally, we will multiply this tensor with 255. So now the highest possible value in this image equal to 255 and the lowest possible value in this image equal to 0. Now we will change the type of this tensor. We will convert it into NumPy array. Firstly, we will type .long method, which means that we will make all the values inside this tensor, we will make them integers. After that, we will convert this tensor into NumPy array, and we will convert the type of this array to unsigned integer 8. Okay? Now we will display this image. We will use pil.image.from array, and we will pass this thing here, this array here, to this method, and we will get this image. As you can see here, it is noisy image. It is noisy version for this clear image. It is X capital for this clear image, X0. Now let's create this original image from this X capital. How can we do that? We will do reverse diffusion. We will make xt equal to xt capital, like what we did in the previous lectures. And here we will pass through our time steps. We will start with time step t capital, and we will move backward to reach time step 0. Each time we will get the number of the current iteration of this loop and the time step. Here we will prepare the input to our model. Here we will use our model to find the predicted epsilon. Here we will find alpha bar t, which is equal to scheduler.alpha's cumulative product, and here we will pass the current time step t. Now, if the current time step not equal to 0, at this case, we will make alpha bar t minus delta t equal to scheduler.alpha's cumulative product, and here we will pass scheduler.timeSteps, open these square brackets, I plus 1. So here we will get the next time step, or in this case the previous time step, t minus delta t, by using our time steps tensor. After that, based on this time step t minus delta t, we will get alpha bar t minus delta t. And if the current time step equal to 0, at this case we will make alpha bar t minus delta t equal to this tensor, equal to 1. Now we will find predicted x0. Predicted x0 is equal to xt minus the square root of 1 minus alpha bar t times predicted epsilon divided by the square root of alpha bar t. Now we can use a clamp method, because as we said previously, now xt capital, it is the best noisy representation for this clear image that we can use to get this original image. So now predicted x0 is equal to predicted x0.clamp, and here we will pass minus scheduler.configuration.clip sample range, comma, scheduler.configuration.clip sample range. Now we will find xt minus delta t, which is torch.sqrt, and here we will pass alpha bar t minus delta t times the predicted x0 plus the square root of 1 minus alpha bar t minus delta t times the predicted epsilon. Now we have xt minus delta t. We will make xt equal to xt minus delta t. When we finish this loop, we will reach time step 0, or in other words, we will reach x0. Now we will import PIL. Here we will do all what we said previously to display this image, this clear image, and as you can see here, it is good image. This image, it is good. And now we learned how to find xt capital from the out-of-domain images and how to generate our clear image from this xt capital. Thanks for watching. Hi, in this lecture we will talk about style transfer and how to use our diffusion model to do style transfer. Firstly, what is a style transfer? Let's say that we have two images. The first image, it is content image, and the second image, it is style image. In simple words, we want to transfer the colors and the background of this style image and put them in this content image. We will do that by using our diffusion model. And finally, we will get this image. How can we do that? As we said previously, we have two images, style image and content image. We will do forward diffusion using DDIM sampling algorithm, and we will get X capital for this style image. And we will do the same thing for content image. We will do forward diffusion using DDIM sampling algorithm, and we will get XT capital for this content image. Now we will start doing style transfer. We will do style transfer in reverse diffusion process. We can do this style transfer using diff style block that we will talk about it later. At each time step, we will take the output feature maps from the bottleneck of our U network, and we will pass it to diff style block, and we will also pass the previous XT estimate to this diff style block. By doing this, we will inject the content of this content image in XT estimate. To be more specific, we will inject the contents inside XT content in XT estimate. We will use the green color to represent the content image, and we will use the orange color to represent the style image. Firstly, we will start with XT capital style, which means that this XT capital, it is completely orange because it is the noise that we can use to generate the style image. Now, as you can see here in XT-1 estimate, the green color, it is more than the green region in XT-1 estimate, it is more than the green region in XT estimate, and the orange region in XT-1 estimate, it is less than the orange region in XT estimate. And that's because that we injected XT content image again with XT estimate using diff style block. Here the orange color represents the information or the characteristics of the style image, and the green color represents the characteristics of the content image. So by injecting the feature maps that we will get from the bottleneck of our unit after passing XT content in X estimate T using diff style, we will increase the characteristics of the content image in XT-1 estimate. We can also do style transfer using out-of-domain images as style images. Let's say that we have this content image, this person here, and we have this out-of-domain image. let's say that our diffusion model just able to generate images for faces. So we didn't train our diffusion model to generate this style image. But as we said in the previous lecture, we can find xt capital for out of domain images. So we can find xt capital for this style image. Now we will do style transfer using our diffusion model, and we will get this amazing image. So we have our content with the new style, and we can also transfer the style of bedrooms. Let's say that we have this content bedroom and we have this style bedroom, and we will get this new image, the same contents but with different style. Now how can we do content injection? Previously we talked about this general formula, and we said that we can mix between DDPM and DDIM using this general formula. xt minus delta t is equal to the square root of alpha bar t minus delta t times xt minus the square root of 1 minus alpha bar t times the predicted epsilon after passing xt and the current time step divided by the square root of alpha bar t plus the square root of 1 minus alpha bar t minus delta t minus sigma t squared times the predicted epsilon after passing xt and the current time step plus sigma times epsilon, which is a pure noise that we took from the standard Gaussian distribution. This formula, it is general formula that we can use to mix between DDIM and DDPM. So if sigma equal to 0, which means that we will convert this formula into just DDIM. Now this part here, we call it predicted x0. We will refer to it by p capital sub t, and here we should put how we computed the predicted epsilon. We just passed the value of xt variable and the current time step. Now this is the predicted x0. This part here we will refer to it by d capital, and here we will put how we computed the predicted epsilon. We just passed xt to our U network, xt and the current time step to our U network to find the predicted epsilon. This part here, it is just the direction that pointing to xt. Previously we said that we can move directly from xt to x0. After that we will move from x0 to xt minus delta t. This part here will do that. We'll move as from x0 to xt minus delta t, which is now it is xt, it is the current state. So for this reason we said that this is the direction pointing to xt. Now let's start content injection. Firstly, you should know that this is our U network, okay? Anything that we will take from the bottleneck of this U network, we will say that we took these feature maps from H space. These feature maps, these output feature maps, they will have the content inside the image. If our diffusion model trained previously on images of dogs, and now our diffusion model able to generate images for dogs, in this case when we pass an image that generated previously using this diffusion model through our diffusion model, our U network, so when we move it through our U network and reaching the bottleneck of our U network, we will take the output feature maps at the bottleneck. These feature maps will represent the identity of that dog. Another example, let's say that we have a diffusion model that we trained previously on face images. Now our diffusion model able to generate face images. we used this diffusion model to generate an image, and there is a face inside this image. We passed this image through the same diffusion model, the same new network, and during moving through the layers of this new network, we reached the bottleneck and we took the feature maps. These feature maps will represent the identity of the face inside this image, or in other words, the content of the image. While these skip connections will have the style of the image, like the colors, the texture, and the background, etc. So you should keep this in your mind. The intermediate feature maps that we will take from this middle block of our U network, these feature maps will have the content of the image, while the skip connections will have the style of the image. Okay? Now, let's say that we are at time step T capital, which is the first time step in reverse diffusion process. We have XT capital style, which is the noise that represents our style image. And we have also XT capital content, which is the noise that represents our content image. Now what we will do, actually, we will check if we are at time step T capital. In this case, we will pass this XT capital style through our U network. And now, when we reach the bottleneck of our U network, we will take the output feature maps from it, and we will call it HT style. And of course, our U network finally, from the final layer, will give us the predicted epsilon after passing the value of xt and the current time step. The most important thing here that we now have this HT style, okay, which represents the content of this xt style. Now we will do the same thing with xt capital content image. Now we will check if we are at time step T capital, which is the case here. So we will pass xt capital content through our U network. And when we reach the bottleneck of our U network, we will take the feature maps from this bottleneck, from this middle block of our U network, which has the contents of xt content variable. And we will get the predicted epsilon. We will use this formula here with sigma equal to 0, which means that we will do DDIM here during reverse diffusion to get xt minus delta t content. And here you should know that we are still at time step T capital. We will move to time step T minus delta t when we finish the injection process at the current time step, which is T capital in this case. We have HT style and HT content. Here we will check if we are at time step T capital, which is the case here. So we will multiply this HT style by 1 minus gamma, and we will multiply HT content by gamma. After that, we will add the results. We will use gamma here to control the amount of injection at each time step. By increasing gamma, we will increase the amount of HT content in the resulted H estimate T. The best value for this gamma hyperparameter equal to 0.6. Now we have this new feature maps, H estimate T feature maps. Now we need this part here just to find HT style at time step T capital. And we don't want to find HT style for the rest time steps. So we don't need to look at this thing here anymore. But now you might ask yourself why we need to add HT style to HT content to find H estimate T. We can just make H estimate T equal to HT content, which had the contents that we want to see in the generated image. And because that we started with XT capital style, noise, which represents the characteristics of the style image. So by doing this, we will make sure that the generated image will have the style of the style image. So why we need to add HT content and HT style together to get estimate T and using this gamma hyperparameter? That's what we will learn now. Let's look at this plot here. This is our U network, and these feature maps, we took them after passing XT style through our U network. So we didn't replace anything here. They are just the feature maps that created using our U network from its input. And here we will compare these feature maps with this skip connection that will have the style of the image. And here we replaced these feature maps with the feature maps that we will get from XT content image. And we will compare these feature maps with the skip connection of our XT style image. As you can see here, the correlation between the feature maps of the style image and the skip connection, it is strong. And the correlation between the feature maps of XT content image and the skip connection of XT style image, it is very small, which means the generated image will not be good. So we need to increase this correlation between the skip connection GT1 and the feature maps that we will use. So for this reason, we combined HT content and HT style to generate estimate T to increase the correlation between estimate T and the skip connection, which will increase the chance that we will generate good image. Now we are still at time step T capital. As we said previously, we will not move backward until finishing content injection. Now we have estimate T. Now what we will do, we will check if we are at time step T capital, so we will pass XT style through our U network, and during moving through our U network, we will reach the bottleneck of our U network, and here we will replace the feature maps, the output feature maps, with these new feature maps, estimate T feature maps. Okay, so now we have the style in these skip connections, and we have the content in these feature maps, and we have good correlation between the contents and the style. And finally here we will get the predicted epsilon when we pass XT new. XT new, it means the new image that will have the style of our style image and the content of our content image. And here, as we said previously, we used estimate T feature maps during computing the predicted epsilon. And here we will use our formula to do reverse diffusion, but we will make sigma equal to 0, which means that we will do DDIF. And here we used the predicted epsilon after passing XT new given estimate just in computing the predicted x0. And here we don't use this predicted epsilon when we want to compute the value of the direction pointing to xt new, because they found that we should use this predicted epsilon just to find or to compute the predicted x0. When we use this predicted epsilon inside both P and D, we will not achieve good style transfer. So now we can find P capital because we have the predicted epsilon after passing xt new and replacing the output feature maps in the bottleneck with estimate T. But how we can find D capital? We need to find the predicted epsilon after passing xt new without replacing the output feature maps from the bottleneck. Let's go back to this place here. As we said previously, we are at time step t capital now, so we will pass xt style to this u network, to our u network, and we will use our u network again here. We will pass also xt capital style to our u network, and here we will not replace the output feature maps in the bottleneck, and we will get the predicted epsilon after passing xt new through our u network. And that's what we need to find d capital. Now we have p capital and d capital, so we can use this formula to find xt minus delta t new. And here we will check if the time step, the current time step, it is less than t edit or not. Actually, we will stop the content injection at time step 400. Okay, so if the current time step it is less than 400, in this case we will just do the denoising steps, the normal denoising steps that we did in DDIM previously. But now we are at time step t capital. We didn't reach time step 400, so we will move back to another time step and we will do content injection again. Now we are at time step t minus delta t. The current time step now it is t minus delta t. So we can say that t it is equal to t minus delta t. Now we will not take h style t because we are at time step t minus delta t. So we will disconnect this thing here and we will take ht new. But how can we get this ht new? As you know, we have xt capital minus delta t new. We found this xt capital minus delta t new in the previous time step. So now we will pass this xt capital minus delta t through our u network, and we will take the output feature maps from the bottleneck of our u network, and we will use these output feature maps ht new to increase the correlation between h estimate t that we will create, that we will compute, and the skip connections at the current time step. And as you know, previously we found xt capital minus delta t content. Okay, so now we will pass it through our u network and we will take ht content at the current time step. We will multiply it with gamma and we will multiply ht new with 1 minus gamma and we will compute h estimate t. And as we said previously, we have xt capital minus delta t new, so we will also pass it through our u network, and here during moving through the layers of our u network, when we reach the bottleneck of our u network, we will replace the output feature maps of this bottleneck with h estimate t that we computed, and our u network will return the predicted epsilon after passing xt new and replacing the output feature maps of the bottleneck with h estimate t. And again, we can find p capital but we can't find d capital. So firstly we need to find the predicted epsilon after passing xt new without replacing the output feature maps. That's easy. We just need to pass xt capital minus delta t new through our u network and we will get the predicted epsilon after passing xt new. Now we can find p capital and d capital, so we will be able to do reverse diffusion again and move to xt minus delta t new. Now we can say that we are at time step t minus 2 times delta t. And here now we will check if we are at time step 400 or less than 400. At this case we will do the denoising steps, the normal denoising steps using DDIM. Otherwise we will keep doing content injection at each time step before reaching time step 400 or less than 400. Let's say that we reached time step 400 or the current time step it is less than 400. At this case, like what we said previously, we will do normal DDIM sampling algorithm. We will take this xt new and we will do reverse diffusion with DDIM sampling algorithm. for the rest of the time steps that we have until reaching time step 0. When we reach time step 0, so we will get x0 at this case. This x0 will have the style of our style image and the contents of our content image. In the next video, we will learn how to do all these things practically. Thanks for watching. Hi, in this lecture we will learn how to do style transfer with Python. Firstly, we will import CV2 and we will import transforms package from Torch Vision, and we will download the out of domain image that we will use as a style image. So firstly we will type x0 equal to image.open, and here we should pass the path of our style image, our out of domain image. But actually here we should import this image class. How can we do that? From pil import image class, like this. Okay, now we have our out of domain image, our style image, which is our clear image. We will resize our image and we will make the height of this image equal to 256 and the width of this image equal to 256. Here we will specify the device that we will use in forward diffusion and reverse diffusion, which is our GPU. Now we will convert this x0 to numpy array like this. Here we should import numpy as np, and here we will type np.array and we will pass x0. So now we converted this x0 into numpy array. After that we will use transforms.toTensor to convert this numpy array into PyTorch tensor. After that we will add a new axis, and the length of this new axis is equal to 1, which is the batch dimension. Now we will send this image, this clear image, this style image to our device. So we will type x0.toDevice. Now we will make xt equal to x0. Now we are at time step 0. This is our clear image. So we will make xt at time step 0 equal to x0, which is our style image. Now we will import DDIM pipeline from diffusers. Here we will specify the ID of the model that we want to use. Here we will use this model, DDPM Church 256. This model will generate church images, and you can use other model here like this model, DDPM EMA Celebrity AHQ 256. Okay, but now we will use this model, DDPM Church model. We will specify the device that we want to use. Here we will type image pipe equal to DDIM pipeline.from pre-trained. Here we will pass the model ID, the ID of the model that we want to use, the ID of the diffusion model that we want to use, and here we will send this pipeline to our device. Now we have our image pipeline. This pipeline will make it easy to use our diffusion model to generate images. Here we will generate one image. We will call it image1, which is equal to image pipe, and here we will specify the number of entrance steps, and we will make it equal to 50. Okay, here we are using DDIM pipeline. In other words, we are using DDIM scheduler, so we can use very small number of time steps to generate the images. Dot images, and here we will open these brackets and put 0 between them. Now we have our image 1. So now we generated one image using our church DDPM diffusion model. We talked previously about this function, get x capital using DDIM function. This function will do forward diffusion, and as we said previously, we will use this function to generate xt capital for the out of domain images or in domain images. Okay, now we said previously that we downloaded our style image, and now our style image, it is available in this variable xt variable. Now what we will do, we will call this get x capital using DDIM function. We will pass xt, our style image, the pipeline that we want to use, our image pipeline, and the device that we want to use, which is CODA, our GPU. Now we will get this xt capital. It is the noise that related with our style image. Here we will make xt capital style equal to xt capital. Our style image, it is this one here, okay, which is available here in this place. This is our style image, and xt capital for this style image, it is this noise here. This is xt capital for this x0, this style image. Now, as we said previously in the previous lecture, we can do reverse diffusion using DDIM sampling algorithm to generate our style image again from this xt capital. And now we have our style image. Okay, this is our style image. Now we know that we have xt capital for our style image, for our out of domain style image. Now we will import these packages: CV2, transforms, torch, numpy, and tqdm package. Now we will create our content image, which is in domain image. We will use our diffusion model, our DDPM church model, to generate this image. How can we do that? Firstly, we will take the time steps from image pipe.scheduler.time steps. Now we have this PyTorch tensor. The first element in this tensor represents the first time step in reverse diffusion, and the last element in this tensor represents the last time step in reverse diffusion, which is time step 0. Now we will create a noise. We will take this noise from the Gaussian distribution, the standard Gaussian distribution. Here we will make xt capital content equal to this noise, because this noise we will use it to generate our content image. So it is xt capital for this content image. Now we have xt capital content, which is equal to this noise, and we will make xt content equal to noise, because as you know, t small here will be equal to t capital when we are at the first time step in reverse diffusion, which is time step t capital. So now xt small content equal to noise, which is this one here, or in other words, xt content equal to xt capital content. Now we will pass it through these time steps. Okay, we will get the number of the current iteration for this loop and the current time step. What we will do, we will take alpha bar t from image pipe.scheduler. alpha as cumulative, and here we will pass the current time step. Now we will check if the current time step it is not equal to 0, it is greater than 0. In this case, we will find alpha bar t minus delta t from image pipe.scheduler.alpha as cumulative. And here we should get the next time step, or time step t minus delta t in reverse diffusion. How can we find this t minus delta t time step? We will use this time steps tensor image pipe.scheduler.timesteps, and here we will pass the index of time step t minus delta t, which is I plus 1. Now we have our alpha bar t minus delta t. But if t is equal to 0, we are at time step 0. At this case, we will make alpha bar t minus delta t equal to image pipe.scheduler.final alpha cumulative product, which is equal to 1. Now, what we will do, we will use our model. Firstly, we don't want to update the weights of our model, so we will put this context manager with torch.noGradient. So we will not compute the gradients for anything inside this context manager. We will prepare the input to our model. So a model input equal to image pipe.scheduler.scale model input. Here we will pass xt content and the current time step. Okay, here we will compute the predicted epsilon. So predicted epsilon at time step t, it is equal to image pipe.unit. Here we will use our diffusion model. Here we will pass our model input, the current time step, and we will get the predicted epsilon. Now we will compute predicted x0, which is equal to xt content minus the square root of 1 minus alpha bar t times the predicted epsilon divided by the square root of alpha bar t. Here we will use a clamp method to make the lowest possible value inside this predicted x0 tensor equal to -1, and the highest possible value in predicted x0 equal to 1. This image pipe.scheduler.configuration.clip sample range, it is equal to 1. Okay. Here we will compute xt minus delta t, which is equal to the square root of alpha bar t minus delta t times the predicted x0 plus the square root of 1 minus alpha bar t minus delta t times predicted epsilon. Here we will make xt minus delta t equal to xt content, because now t is equal to t minus delta t. The current time step it is t minus delta t. And we will do this thing again and again until reaching time step 0. Now we created our content image. This is our content image. We used pil.image.fromArray method to display this image. When we reach time step 0, so now xt content it is x0 content. We will take this image from xt content tensor. As you know, it is a batch of samples. We will take just the first sample. As you know, this batch has just one sample. We will take this sample. We will rearrange the dimensions of this sample. We will put the height dimension firstly, after that the width dimension, and finally the channel dimension. Now we will type pil.image.fromArray. Here we will firstly take this x0, we will send it to our CPU because we can't display this image without sending this tensor into our CPU. After that, we will make the lowest possible value in our tensor equal to -1 and the highest possible value in our tensor equal to 1. We will multiply this tensor by 0.5 and we will add 0.5 to the resulted tensor. Finally, we will multiply this tensor with 255 to make the lowest possible value in our tensor equal to 0 and the highest possible value in our tensor equal to 255. We will convert the elements of this tensor to integers. We will convert this tensor into numpy array, and we will convert the type of this array into unsigned integer 8. And now we have our content image, which is this image here. Now let's do style transfer. We will take the style of this style image and we will put it in this content image. How can we do that? Firstly, we will get timesteps tensor from image pipe.scheduler.timesteps. Here we will make xt style equal to xt capital style, and we will make xt content equal to xt capital content. As you know, here we will do reverse diffusion. The first timestep in this reverse diffusion it is t capital, so t small here at the first timestep it is equal to t capital. So xt style it is equal to xt capital style that we created previously, and xt content it is equal to xt capital content. This xt capital style it is the noise that related with this style image. This xt capital content it is the noise that related with this content image. Now we'll create this variable xt new and we will make it equal to none. Firstly, we have this gamma variable. We will make it equal to 0.7. We said previously that the best value for gamma variable equal to 0.6, but when you are working with out of domain images as style images, it is better to try many different values for this gamma variable to get the best image. Here we will make editing steps equal to 400, which means that we will stop the content injection if the current time step it is smaller than or equal to 400. Now we will create this loop. We will pass it through our time steps. We will start with t capital and we will end with 0 time step. Firstly, we will take the value of alpha bar t, which is equal to image pipe.scheduler.alpha's cumulative product, and here we will pass the current time step, and we will make this condition. If the current time step it is not equal to 0, in this case alpha bar t minus delta t will be equal to image pipe.scheduler.alpha's cumulative product, and here we will pass t minus delta t time step, which is image pipe.scheduler.timesteps, and here we will pass I plus 1. But if the current time step is equal to 0, in this case we will make alpha bar t minus delta t equal to 1. Okay, now we will make this condition. We will do content injection if the current time step is greater than edit steps greater than 400. Now what we will do in this content injection, firstly we will find h content. We will create this variable, gate variable, which is equal to content, and here we will prepare the input to our diffusion model. So model input will be equal to image pipe.scheduler.scale model input, and here we will pass xt content and the current time step. Here we will create this hook. This hook we will use it to get the content feature maps from the bottleneck of our diffusion model. So let's create this hook, h content hook. It will be equal to image pipe.unit, and here we will type down blocks, and we will take the final down block, which is down block 5, and inside this down block we have ReasonNet blocks. We will take ReasonNet block with index 1. And here we will specify the layer inside this ReasonNet block that we want to take the feature maps from, which is convolution layer 2. And here we will use register forward hook method to create our hook. We will pass a function. This function it will work on these feature maps that we will get from this conv2 layer. Let's go and see this get h content function. This is get h content function. Firstly, we will make h content equal to none, h style equal to none, gate variable equal to none. Here we will create get h content function. PyTorch package will give us three things: the module, the input to the module, and the output from the module. In the other words, the input to this convolution 2D layer and the output from this convolution 2D layer. Here we will take the output from this layer. Firstly, we will make this h content variable global variable, which means when you change this variable in this function, this variable will change in any other place, even outside this function. And when you change this variable in any other place outside this function, so this variable will change inside this function as well. And the same thing for this gate variable. We will make this gate variable global variable. So when we change the value of this variable outside this function, so the value of this variable inside this function will change also. We made the value of gate variable equal to content. Okay? So let's see that. Here we made gate variable equal to content. And as we said previously, gate variable, it is a global variable. So its value in this function will change also. And now the value of this gate variable, it is not none, but content. So now this condition, it is true. So we will make h content equal to the output. The output feature maps from this layer, from this bottleneck of our U network. And after that, we should remove the hook. How can we remove the hook? We just need to type the name of the hook that we created, which is this one here, h content hook. Okay, we should type the name of this hook, h content hook dot remove. By doing this, we will remove this hook. We need to remove this hook to be able to create another hook. Okay, now let's go back to our loop. PyTorch will call this function automatically when we reach the bottleneck of our diffusion model. Now we created our hook that we will use to get the content feature maps from our unit. Now we will use our diffusion model. We will type this context manager inside this context manager. We will use our U network. Predicted epsilon, it will be equal to image pipe.unet. Here we will pass the model input and the current timestamp. So now we used our U network. We will move it through our U network, and when we reach the bottleneck of our U network, when we reach this layer, the convolution layer inside this ReasonNet block, inside ReasonNet block with index 1 and down block with index 5, when we reach this layer, PyTorch will call this get h content function. And here we made gate equal to content, so we will make each content equal to output. So we will make the output feature maps, the content feature maps in this each content, and we will remove this hook because we don't need it anymore in this time step, in this current time step. Now what we will do, we will find the predicted x0, which is equal to xt contents minus the square root of 1 minus alpha bar t times the predicted epsilon divided by the square root of alpha bar t. And here you should know that we should not use a clamp method. We should not restrict the predicted x0 when we do content injection, to make sure that we will get good result. Here we will find xt minus delta t, which is equal to the square root of alpha bar t minus delta t times the predicted x0 plus the square root of 1 minus alpha bar t minus delta t times predicted epsilon. Now we will make xt minus delta t equal to xt content. So now we have h content. Now let's take h style. How can we do that? Here we will create another hook that we will use to get the style feature maps from our U-network. How can we do that? We will type hStyle hook, which is equal to image pipe.unet.downblocks pipe.reasonets1.conv2. We will take hStyle tensor from the same layer that we used to take hContent tensor. Okay, we should do that. And here we will use register forward hook method to create our hook, and we will pass the function that we will use to get the output and the input and the module. Let's go and see this get hStyle function. This is get hStyle function. We will get the module. PyTorch will give us the module itself, the input to the module, and the output from the module. Here we will make hStyle variable global variable, and we will make gate variable global variable. Why? Because we want to use this hStyle tensor in another function. So when we change the value of this hStyle in this function, so we will change this variable in any other place, even outside this function and inside another function. Now when we make gate variable equal to style, so we will make hStyle equal to the output from this layer, and here we will remove this hook. We will activate this function when we reach this layer. Okay, now we have our hook. And here we will check if we are at the first iteration of this loop. In other words, if we are at time step t capital, the first time step. So at this case, we will prepare the input to our model input equal to image pipe.scheduler.scale model input, and here we will use xt capital style, and we will pass the current time step. Okay, if we are at time step t capital, and here we will use our model, and when we reach this layer, so PyTorch will use this hook to get the output from this layer, and we will change hStyle variable based on the outputs from conv2 layer. Let's say that we aren't at time step t capital. At this case, model input will be equal to image pipe.scheduler.scale model input, and here we will use xtnew. Okay, and we will pass the current time step. And here we will use our U-network to extract the style feature maps, hStyle. We can call this tensor now h new. Here we will combine the style and the contents, or in other words, we will do noise injection. Firstly, we will make gate equal to none. Okay, here we will use our model. If the current time step is time step t capital, or we are at the first iteration for this for loop, at this case, model input will be equal to image pipes.scheduler.scale model input, and here we will pass xt capital style and the current time step. Otherwise, model input will be equal to image pipe.scheduler.scale model input, and here we will pass xt new and the current time step. And here we will use our model, our U network, to find the predicted epsilon given ht. We will use this thing here when we want to compute d capital, which is equal to image pipe.unit, and here we will pass our model input and the current time step. Okay, now we have the predicted epsilon given ht. Now we will make gate equal to combine, and here we will create another hook, which is h hat hook, which is equal to image pipe.unit.down blocks, and here we will pass the index of this down block and the index of the reasonable block and the layer that we want to take the values from it. Dot register forward hook, and here we will pass the function combine style and content function that will take the module, the input, and the output. Now let's see this combine style and content function. This is combine style and content function. It will take module, input, and output. And here we have many variables. We have gamma variable, which is global variable, h style variable, which is a global variable, h content variable, which is a global variable, and gate variable, which is a global variable. Here, when we change a gamma variable from outside this function, so the value of this variable will change inside this function. H style also will change based on what we got previously from this get h style function, and h content variable will change also based on what we got from get h content function. Here we will check if gate equal to combine. We changed the value of this gate to combine, so this is right. At this case, we will remove this hook, so we will type h hat hook dot remove, and here this function, in this function we will not use the output. Okay, we will use h content and h style, so we will type return. This function will change the output from this convolution layer to make it this thing here. So we will type return 1 minus gamma times h style plus gamma times h content. Okay, that's it. Now we will check if we are at the first iteration or if we are at time step t capital. At this case, we will use our diffusion model. We will type model input equal to image pipe.scheduler.scale model input, and here we will pass xt capital style and the current time step. And we will get a predicted epsilon given h hat, which is equal to image pipe.unit. Here we will pass the input, model input, and the current time step. Here we will find predicted x0, which is equal to xt style minus torch the square root of 1 minus alpha bar t times predicted epsilon given h hat divided by the square root of alpha bar t. And here, as we said previously, we will not use a clamp method because it will affect on style transfer during content injection. Here we will find xt minus delta t, which is equal to the square root of alpha bar t minus delta t times the predicted x0 plus the square root of 1 minus alpha bar t minus delta t times the predicted epsilon given ht. Here we will make xt nu equal to xt minus delta t. Okay? This xt nu, firstly it is equal to none, but now in the next time step it is equal to xt minus delta t. Now let's say that we are not at time step t capital, so at this case model input will be equal to image pipe.scheduler.scale model input, and here we will pass xt new because now we have xt new and the current time step, and here we will get predicted epsilon given h hat, which is equal to image pipe.unit, and here we will pass model input and the current time step. Here we will compute predicted x0, which is equal to xt new. As you can see here, it is xt new, it is not xt capital style, minus the square root of 1 minus alpha bar t times the predicted epsilon given h hat divided by the square root of alpha bar t. We will not do clamp here also, and here we will find xt minus delta t, which is equal to the square root of alpha bar t minus delta t times predicted x0 plus the square root of alpha bar t minus delta t times the predicted epsilon given ht. Now, let's say that the current time step is smaller than or equal to 400. So we will not do content injection. We will not do all these things here. Okay? We will just do regular denoising steps using DDIM sampling algorithm. How can we do that? Here we will prepare the input to our model. Model input will be equal to image pipe.scheduler.scale model input. Here we will pass xt new and the current time step. Here we will get predicted epsilon, which is equal to image pipe.unit. Here we will pass the input and the current time step. Now we will compute predicted x0. Okay, we will type xt new minus the square root of alpha bar t times predicted epsilon divided by the square root of alpha bar t. Predicted x0, it will be equal to predicted x0.clamp, and here we use the clamp method because now we are not do content injection, so we can use this clamp method. Here we will find xt minus delta t, which is equal to the square root of alpha bar t minus delta t times the predicted x0 plus the square root of 1 minus alpha bar t minus delta t times predicted epsilon. And here we will make xt new, it is equal to xt minus delta t. We will do this thing again and again until reaching x0. Okay? Now, as we said previously, we have this content image and this style image. Let's see the result. This is the result that we will get after doing style transfer. It is something, it will have the content, which is this church here, and the style of this style image. Okay? And I used the same diff style block and the same procedure, style transfer procedure, and I tried many different style images, and I got these results. As you can see here, this is the second result, and this one here also. These are good results, okay? And you can try to use another diffusion model like celebrity AHQ model to see the results. Let's use this model, celebrity BAHQ 256 model, Firstly, we should install diffusers package, datasets package, transformers package, ftfy package, pyro package. Okay. Now we will, let's say, take another style image. Let's use this style image, okay? And we will use this model. This model will generate face images. Okay, we will combine content image that we will generate from this model with this style image. Okay, firstly, we will take this style image 7. Now we will download this model. Now we will get xt capital for this style image using our get xt capital using DDIM function. We will pass xt image pipe device to our get xt capital DDIM to get xt capital for this style image. Here we should import torch. Okay. Now we have xt capital for this style image. We will make xt capital style equal to this xt capital because this noise is the noise for this style image. Now let's see this noise. Okay, this is the noise for this style image. Now let's try to remove the noise inside this style image by doing reverse diffusion using our diffusion model. And let's see if it will return the same image or not. As you can see here, here is our style image again. Now what we will do, we will run this. We will create our content image. Okay, let's run this cell. Now we have this image, and as you can see here, this face, it is the content of this image. Now let's do a style transfer. Here, as we said previously, if we are working with out of domain images as style images, you should try many different values for gamma to find which one the best. Let's start with gamma 0.3 and edit steps equal to 400. Let's run this, and here's the result as you can see here, and you can try many different values. Let's try another style image and see the results. We will use this style image. Okay, so we will take the path of this image and we will put it here in this place. We will run this cell and we will get xt capital for this style image like this. Now we have xt capital for this style image. Let's do reverse diffusion to make sure that we will get the same style image again from this xt capital. Yes, we have this style image. We got this style image from xt capital. Now we will use this style image to do a style transfer with this content image. Okay, let's do it. Let's run this cell. Let's start with 0.5 gamma and see the results. As you can see here, here's the result. It will combine between the person itself, this person here, and the style image, which is this one here. Okay, we can change gamma, we can increase it like this. Thanks for watching. Hi, in this lecture we will talk about stable diffusion model. What is a stable diffusion model? Let's say that we have this prompt here, an astronaut riding a horse. And now we want to, from our diffusion model, to generate an image based on this prompt. This stable diffusion model will do this for us. In simple words, stable diffusion model, it is just conditional diffusion model. By using this stable diffusion model, we will be able to set a condition about what our diffusion model will generate. Now let's learn how this diffusion model, this stable diffusion model, able to generate high quality and high resolution images. Let's say that we have a pre-trained stable diffusion model. Okay, we will start with the pure noise from the standard Gaussian distribution. We will call it latent noise. The width and height of this noise equal to 64. But why we said latent noise? Previously we talked about the variational autoencoder, and we said that during a training the conditional diffusion model, we will not pass the noisy version of the original image directly through our diffusion model because it is large. The width and height of this image, it is very large, which means that our diffusion model will take long time to generate any image. So we used the variational autoencoder to compress this image into latent version. After that, we will add the noise to this latent version of the original image. The width and height of this latent representation of the original image, it is much smaller than the original image, the width and height of the original image. And because that the width and height of the latent representations, they are very small, at this case our diffusion model, our conditional diffusion model will work faster and it will generate images faster. So now we will start with the pure latent noise from the standard Gaussian distribution. And after doing reverse diffusion, we will end with the latent x0, and we will use the decoder part of the variational autoencoder to create high resolution image from that latent x0 representation. Now what we will do, we will start with this latent xt capital, and we will pass it through our text conditioned latent U network. And as we said in the first section, we will use the cross attention blocks to create this conditional U network. And here what we will do, we will also pass our prompt. Firstly, we will convert this prompt to a new representation using frozen clip text encoder. This frozen clip text encoder is just a neural network. It will convert our prompt, our text, into a numerical representation that has the most important thing about this text. And we said frozen here because we will not train the parameters of this model. It is a pre-trained model. In other words, this model trained previously on very large data set. And this model has enough knowledge to know how to extract the most important thing inside any prompt that you want to pass. After passing this prompt through our frozen clip text encoder, we will get this numerical representation. We will call it text embedding. For each prompt, for each text, this frozen clip text encoder will create text embedding, which represents the numerical representation for that text. And the size of any text embedding will be equal to 77 times 768. We will pass this text embedding through each cross-attention block inside our text conditioned latent U network. It's like that we are trying to inject the condition inside our U network. They trained this U-network to understand these text embeddings, and it will predict the noise based on the latent XT and the text embedding. Here we are just doing inference, okay? Here we are just trying to do reverse diffusion. We will start with latent XT capital and we will end with latent X0. Now we will get the output from our text conditioned latent U network, and the size of the output it is 64 times 64, which represents the predicted epsilon. We will pass this predicted epsilon through our scheduler, and our scheduler will give us the latent xt minus delta t, and we will do the same thing again and again until reaching latent x0 that we will take from our scheduler. And we will now use decoder part of our variational autoencoder until reaching latent x0. After that, we will pass this latent representation of x0 through our variational autoencoder decoder to create this high resolution image. This high quality image, it is similar to the text that we passed through our stable diffusion model. Now let's learn how to do all these things practically. Firstly, we should download diffusers package, transformers package, SciPy package, FTFY package, and accelerate package. Now we should change runtime to GPU. Let's run this cell to download all these packages. Now let's download our stable diffusion model. Firstly, we will import a stable diffusion pipeline from diffusers package, and now we will download our stable diffusion model. So we will type pipe equal to stable diffusion pipeline dot from pre-trained, and here we will pass the model ID. They created this stable diffusion pipeline to make us able to work with the stable diffusion model easily, to make us able to generate images from our stable diffusion model easily, like DDPM pipeline and DDIM pipeline that we used previously. Now let's run this cell and create this pipeline. Now we created stable diffusion pipeline. Now we will send this pipeline to our GPU, which will make the generating process faster, because now we will use our GPU to do reverse diffusion. Okay, now we will run this cell. Now we sent our pipeline to our GPU. Okay, there are many things inside this pipeline. We will talk about each one of these things later. Now let's create our prompt. Prompt equal to astronaut riding a horse. Let's use our pipeline to generate the image. We will pass this prompt through our pipeline. Okay, and we will get the image from this stable diffusion pipeline. By default, the number of inference steps equal to 50 steps. Now we created our image. Let's display this image. Let's add a new cell and we will put it here, and let's run this and see the result. And here's our image. Okay, if the resulted image is not good, you can change the guidance scale, and you can also change the number of inference steps, like what we said in the first section in this course. This guidance scale will control the importance of the prompt for our U network, conditional U network. While the number of inference steps, it is the number of time steps that we will move during reverse diffusion. We can specify some value between 0 and 10 for this guidance scale. Let's make the guidance scale equal to 2 and the number of inference steps equal to 200. Let's see the result. It will take long time to generate this image because we need to move 200 time steps backward. Now, here is the output image that we created using our diffusion model, our stable diffusion model. We can increase the guidance scale to make sure that we will get something similar to what we have in this prompt. Let's make it 5 and see. Here is another image from our stable diffusion model. Now, let's learn how this stable diffusion pipeline works. Firstly, we will import these things. From transformers, we will import clip text model and clip tokenizer. These two things, we will use them to convert our prompt into a numerical representation or text embedding. Here we will import autoencoder KL and unit 2D conditional model and PNDM scheduler, which is another scheduler that we can use to make the reverse diffusion faster. We talked about DDIM scheduler. Now we have this PNDM scheduler. This scheduler will also make us able to skip time steps during reverse diffusion. Now we will download the variational autoencoder that they used for this stable diffusion model, to train this stable diffusion model. And of course, this variational autoencoder is available in this stable diffusion pipeline to do inference. Okay, so now we will load this variational autoencoder. So variational autoencoder is equal to autoencoder KL dot from pre-trained, and here we will pass the model ID, and we will take from this stable diffusion model just this variational autoencoder. So we will make this subfolder argument equal to variational autoencoder. Let's see what is inside this model ID. Okay, we have this stable diffusion v14. Let's go to this files and versions, and you can see many different things inside this model ID. One of these folders is variational autoencoder. We will take just this one. Okay, let's run this cell. Before that, we should run this one, and we will run this cell. Now we have our variational autoencoder that we will use to compress our original image into the latent representation and decompress the latent representation to the original image. We have two things in this variational autoencoder: the encoder part and the decoder part. Okay? Now we will learn how to convert the prompt into the numerical representation. Firstly, we will load the tokenizer. So tokenizer equal to clip tokenizer, this class here, data from pre-trained, and here we will pass the path of this tokenizer, which is OpenAI / clip VIT large patch 14. Which is the same tokenizer that is available in this stable diffusion pipeline. And we will download the text encoder. This text encoder will take the output from this tokenizer, and it will create the numerical representation of the prompt. So text encoder is equal to clip text model dot from pre-trained, and here we will pass the same path. Okay, now let's run this cell. So we will load the tokenizer and the text encoder. Now we have this tokenizer and text encoder. Now we will create our U network. our conditional network. So unit equal to unit to the conditional model dot from pre-trained, and here we will pass the model ID. Here we used unit to the conditional model from diffusers package to load this network from this model ID. We have this unit folder. We will download this folder using this unit to the conditional model dot from pre-trained method. Let's run this cell. Now here's our model. We have many things inside this model. We have down blocks, okay. We have cross attention block 2D that we will use to inject the condition inside our U network, and many other layers as you can see here. Now we can use the same scheduler that they used to train this stable diffusion model, which is this PNDM scheduler, or we can use another scheduler like LMS discrete scheduler. There are many different schedulers. We just talked about DDPM and DDIM schedulers, but we have many different schedulers. We can use this scheduler to generate our images, which is LMS discrete scheduler. Here we will create the scheduler. So we will type scheduler equal to LMS discrete scheduler, and here we will specify beta start, which is this one here, 0.00085, and beta end, which is 0.012. Beta scheduler equal to scaled linear, and here we will specify the number of time steps, which is equal to 1000. Okay, by doing this our scheduler will know that T capital equal to 1000 when they trained this stable diffusion model previously, which is important thing during inference. Now we created our scheduler that we will use during reverse diffusion. Now we will specify the device that we will use, which is our GPU. We will send our variational autoencoder network to our GPU, and we will send our text encoder network to our GPU, and we will send our U network to our GPU. Okay. Now what we will do, we will create the prompt. We will create this list here, and we will put our prompt inside this list. Okay. And here we will specify the width and height of the image that we will generate. The default height of the stable diffusion model equal to 512, and the default width of this stable diffusion model equal to 512 also. Here we will specify the number of time steps, the number of inference steps, which is equal to 100, and here we will specify the guidance scale, which is, let's say, 7.5, and here we will make the noise that we will take from the standard Gaussian distribution, which is latent x T capital fixed. How can we do that? We will type generator equal to torch.manual seed, and here we will put any number. By doing this, we will get the same noise again and again and again, which means that we will generate the same image again and again and again. Because the scheduler that we will use here, it is also deterministic scheduler. Here you can pass many prompts. You can put them in this list. So at this case you will generate many images. But here we have just one prompt. So our batch size equal to 1. In other words, we want to generate just one image because we have just one prompt. The length of this list equal to 1. Okay, that's it. Now we specified all the important things. Let's change this prompt into numerical representation. Okay, we will use our tokenizer. Text input, it is equal to tokenizer. Here we will pass the prompt and many different arguments. Here this padding argument, it is equal to maximum length, which means that we will change the number of tokens or the length of each prompt inside this list to make it equal to the maximum length of this tokenizer, which is 77. Here in this list we have just one prompt, okay, one element, one text. We will convert this text into 77 tokens, okay? How can we do that? Firstly, what is token? It is just the word inside the text. Each word we call it token. Each thing inside our text, each word we call it token. As you can see here, the number of tokens, it is smaller than 77. So what we will do, we will add padding tokens to this text to make the number of tokens inside this prompt equal to 77. And we will do the same thing for any prompt inside this list. We should make the length of each prompt in our list equal to 77 to make sure that the size of the numerical representation for each prompt will be the same. It is something important for our U network. And here we have maximum length equal to tokenizer.model maximum length. Okay, this is the maximum length that we will use. As we said previously, it is 77. And here we will make truncation equal to true, which means that if we have a prompt with the very large number of tokens, or in other words, the length of this prompt, it is more than 77. In this case, we will trim this prompt and we will take just the first 77 tokens inside that prompt. And here we will make the tensor that we will get from this tokenizer, we will make it PyTorch tensor. By doing this, return tensors equal to PT. And here's our text input. It is just a dictionary, but the values inside this dictionary, they are PyTorch tensors. This dictionary will have two keys: input IDs key, attention mask key. Okay? The value of the first key, input IDs key, it is just a tensor. This tensor, the elements inside this tensor, each one of these elements will represent the ID of the corresponding token in our prompt. We have a vocabulary. This vocabulary will have an ID for each token. It is very large vocabulary, a vocabulary with very large number of words. Each word will have a specific ID. We will convert each token in our prompt into its ID, and we will put these IDs in this tensor, input IDs tensor. As we said previously, we added padding tokens to make the number of tokens in our prompt equal to 77, and for this reason we repeated this ID again and again, because this ID represents the padding token. And here we have this attention mask. This attention mask key, the value of this key, it is just this tensor here, this PyTorch tensor. This PyTorch tensor will tell our text embedding or text encoder which token it is the padding token and which token it is actually available in the prompt, in our prompt. By doing this, we will make sure that our text encoder will focus more on the tokens that related with our prompts during text embedding generation. The first 10 tokens, they are just the tokens that is available in our prompt, and we put it once in our attention mask to tell our text encoder about these tokens, while for the rest tokens we put it just zeros because they are not important, they are padding tokens. Now what we will do, we will pass this text input to our text encoder to convert each prompt into a numerical representation. We will pass all these IDs to our neural network to create this new representation. We will pass them to our text encoder network to create this numerical representation. This numerical representation will focus on the most important thing in our text. And here what we will pass to this text encoder, we will just pass input IDs. As we said previously, firstly, we will take this input ID's value, this tensor here, and we will send it to our device. After that, we will pass it through our text encoder network and we will get text embeddings. Now, let's see this text embeddings tensor. As you can see here, it is just PyTorch tensor. Let's see the size of this tensor. The size of this tensor, it is equal to 1 times 77 times 768. For each token in our prompt, we will get a numerical representation for that token. Okay? Now we have our text embeddings. We will use these text embeddings to set conditions, to make our network create an image that is similar to this prompt. But we will do another thing here. Here we will take the maximum length from our text input dot input IDs dot shape, okay, which is 77. Here we will create unconditional input. As we said in the first section, we said that we will pass two things to our network, to our conditional network: unconditional input and conditional input. Why? To make us able to control the importance of the prompt, or in other words, to make us able to use this guidance scale. So we will create unconditional input, which is equal to tokenizer. Here we will create this empty list. We will just create a prompt with padding tokens, so it will not have important information. And we will make padding equal to maximum length. Okay, and we will make the maximum length equal to the maximum length here, and we will make the input IDs, we will make it PyTorch tensor. Okay, so now we created this unconditional input, and we will pass this unconditional input dot input IDs through our text encoder. So we will get unconditional embeddings. These embeddings, they will not have any condition, because we created these embeddings from padding tokens. It's like that we just created a prompt with just padding tokens, 77 padding tokens. So now we have this unconditional embeddings. Let's run this cell. Now what we will do, we will concatenate unconditional embeddings with text embeddings. We will concatenate them based on the batch dimension. So now why we did that, why we increased the number of samples in this batch, or why we created this text embeddings, we did that just to use our network one times at each time step. As you know, we can pass a batch of samples rather than just one sample each time. We will use torch.concatenate. Here we will open this list here. We will pass unconditional embeddings and text embeddings. Now let's run this cell. Now we have these text embeddings that will have unconditional embeddings and text embeddings. We will pass this text embeddings through our network to get two things: the predicted epsilon with condition and the predicted epsilon without condition. Previously we created this text embeddings tensor. This tensor has the unconditional impedance and text impedance. Now we will create our latent noise xt capital, latent xt capital. So latents equal to torch.random, and here what we will do, we will create this PyTorch tensor. The first dimension of this PyTorch tensor of this latent xt capital, it is the batch size. Previously we made this batch size dimension equal to 1. But if you want to generate many images at once, in this case, you should increase the batch size. So let's say that the batch size equal to 4. In this case, here we will create 4 xt capitals. And we will try to reduce the noise for each one of these xt capitals gradually in this reverse diffusion process. And when we finish the reverse diffusion process, we will end up with 4 latent x zeros. The second dimension in this PyTorch tensor equal to unet.in channels, the number of channels that our U-network expects, which is same as the number of channels from the output of the encoder part of our variational autoencoder. Here what we will do, we will divide the height by 8 and we will divide the width by 8, which will give us 64 times 64. So now let's see the number of input channels to our U network. It is 4, and here the height divided by 8, it is equal to 64, and the width divided by 8, it is equal to 64, and the batch size equal to 1, because we have just one prompt, so we will generate just one image. And here we will specify the generator to make sure that we will get the same latent xt capital again and again and again. Here we created our latent xt capital. Here we will send it to our device. Let's run this cell. Now let's set the time steps. Scheduler.set time steps, and here we will pass the number of inference steps. Let's run this cell. So now, as we said previously, we made this number of inference steps equal to 100. Okay, so now we will move just 100 time steps backward. Here we want to scale these latents. So latents equal to latents times scheduler.initial noise sigma. We didn't do that for DDIM and DDPM because the value of scheduler.initial noise sigma in these algorithms was 1. But here in this scheduler, the value of initial noise sigma is different, which is equal to 14.6. Okay, so we will multiply these latents with this value. Now let's create our denoising loop, our reverse diffusion process. Firstly, we will import TQDM to show us the progress of the generation process. Here what we will do, we will set the time steps to inference, number of inference steps. Here we will pass it through these time steps. Now what we will do firstly, we will repeat the latents along the batch dimension. Here the batch dimension equal to 1 because we have just one prompt, so we need to generate just one image. So when we will repeat the latents along this dimension, so we will make this batch dimension equal to 2. Why we need to do that? Why we need to repeat these latents along the batch dimension? The answer is easy. Rather than using our diffusion model, our U network 2 times, rather than passing the latents 2 times, we will pass them at once as a patch through our U network, which will make our U network faster. And here we will pass the unconditional impedance with the first latents in our latent model input, and we will pass the text embeddings, the conditional embeddings, with the second latence in our latence model input. By doing this, we will get from our U-network the conditional predicted epsilon and the unconditional predicted epsilon. So now what we should do, we will create a list with latence, comma, latence. And we will use torch.concatenation to join these two things together along the batch dimension. And here we can type latence, comma, latence, or we can multiply this list with 2. We will get the same thing. Here what we will do, we will prepare the input. We will pass latence model input and the current time step through this scale model input. So now we have our latence model input. We will predict the noise. We will find the predicted epsilon. Here what we will do, we will pass latence model input and we will pass also the current time step and the text embeddings. Here, as we said previously, in this latent model input we have two things, latence 1 and latence 2. They are the same, latence 1 equal to latence 2. But now, latence 1, we will pass the latence 1 with the unconditional embeddings inside text embeddings. And we will pass latence 2 with the conditional embeddings inside text embeddings. And here our U-network will give us the predicted epsilon. This noise prediction tensor will have the unconditional predicted epsilon and the conditional predicted epsilon. To separate these two things, we should use chunk method. So noise prediction unconditional, comma, noise prediction text is equal to noise prediction dot chunk, and here we should pass 2. So now we computed the unconditional predicted epsilon and the conditional predicted epsilon. Now we will find the final predicted epsilon. The final predicted epsilon will be equal to the noise prediction unconditional plus the guidance scale times the noise prediction text minus the noise prediction unconditional. Here this guidance scale will specify the importance of the conditional predicted epsilon in the generated image. Now we will move backward using a step method from our scheduler. So latence is equal to scheduler.step, and here we should pass noise prediction and the current time step and the latence. Now we moved to time step t minus delta t, and we should do this thing again and again until reaching time step 0. Now let's use the decoder part of our variational autoencoder to convert this image into high quality image. Firstly, we should scale the final latence or x0 latence. We will multiply them by 1 divided by 0.18215. It is something important before passing these latence through our decoder or the decoder part of our variational autoencoder. Here we will use our variational autoencoder. Okay, we will use the decoder part of our variational autoencoder. So because this variational autoencoder, it is just a neural network, and we don't want to compute the gradients for this neural network, we don't want to update the weights of this neural network. This neural network trained previously and learned how to compress and decompress the images. So we will create this context manager with torch.noGradient, and here we will use the decoder part of our variational autoencoder. So we will type image equal to VAE, variational autoencoder dot decoder, and here we will pass these latents. Okay, let's run this cell and see the result. Here we will multiply our image with 0.5 and we will add 0.5 to the result here. After that we will use clamp method to make the lowest possible value in this tensor equal to 0 and the highest possible value in this tensor equal to 1. So now we have this image. Now this image we will send it to our CPU, so image.detach.cpu, and here we will change the order of the dimensions. The first dimension is the batch dimension. We will make the height dimension firstly, after that the width dimension, and finally the channel dimension. And finally we will convert this torch tensor into numpy array. Now we have this numpy array. We will multiply all the elements inside this numpy array by 255. So the lowest possible value in this numpy array will be 0 and the highest possible value in this numpy array will be 255. And we will convert these elements into integer. And after that we will change the type of this numpy array and we will make it unsigned integer. As we said previously, we can generate many images, not just one image. Here the batch size might be greater than 1, okay? Based on the number of prompts in the list. So we will pass it through each image inside this images array, and we will pass it through image.fromArray method. And now we can display any image inside this PIO images. Let's run this cell and see the result. Firstly, we should import this image class from PIO import image class. Let's see the result. And as you can see here's the result. After using our stable diffusion model, it is good image. Here you can use DDIM scheduler that we used previously, but you should not use a clamp method with the predicted X0. Just try it and see the results. Hi, in this lecture we will learn how to fine-tune our pre-trained stable diffusion model. Firstly, what is the meaning of fine-tuning? Let's say that we have a pre-trained stable diffusion model. This stable diffusion model, they trained it previously on very large data sets. A data set with very large number of images. Now we want to, from this stable diffusion model, to learn about our own images. And at the same time, we don't want to make this stable diffusion model forget all what it learned previously. How can we do that? We will train our stable diffusion model like what we did with our unconditional diffusion model. We will use the optimizer and the loss function, and we will update the weights of our diffusion model. And the most important thing here, we will not start with random weights, but we will start with rich weights. These weights have enough information about how to create amazing images. And now we will also add new information to these weights about our own images. So now we will use Dreambooth Collab Notebook to do that easily. We will type Dreambooth Collab, and here we will click enter. We will enter to this Collab Notebook Dreambooth stable diffusion.ipymb. Firstly, we should use the GPU, so we will click here on runtime and we will click on change runtime type, and here we will select GPU and click on save. Now what we will do, firstly, we will run this cell. It will give us all the information about our GPU. Okay. The name of our GPU, it is Tesla T4. The memory size, it is 15 gigabyte. Now we will install all the requirements. So we will run this cell. Here we will download train dreambooth.py script. We will use this script to train our pre-trained stable diffusion model on our own dataset, on our own images. Now we installed all what we need. Now we will log into Hugging Face community. Firstly, we need to generate a token. You should have Hugging Face account, like what we said previously. Here's my account. What we will do here, we will go to settings, and now we will go to access tokens, and here let's create a new token. I will call it my token, and here we will click on generate a token. Now we have this token here. I will copy this token. Okay, now I will put this token here, and I will run the cell. Here we will decide whether to download our stable diffusion model to our Google Drive or not. Here we will do that, so we will click on this save to Google Drive box. This stable diffusion model will take around 4.5 gigabyte from your Google Drive. Now what we will do, we will put the model ID, okay, model name, which is this one here. We should click on this place here. So we will copy the model ID. We will download this pre-trained stable diffusion model from Hugging Face community, and we will put it in our Google Drive. The weights of this stable diffusion model are very good. They are able to generate amazing images. And we will start with these weights, and we will try to tune them to understand our own images. As we said previously, we will put our stable diffusion model in our Google Drive. But here we will create the directory that we will put our stable diffusion model in, which is stable diffusion weights /ZWX. After running this cell, we will find this directory in our Google Drive. Firstly, you should connect your Google Drive to your Colab notebook. You just need to click on this symbol here. And of course, you should have Gmail account to be able to go to your Google Drive. Now let's see this directory that we created using this cell here. It is available in Google Drive. Here we will click on My Drive, and here we should click on Stable Diffusion Weights, which is this folder here, okay, that we created here. And here we should click on this ZWX folder, which is this one here. We will put our stable diffusion model in this ZWX folder. This cell here just created the directory that we want to use to save our stable diffusion model in. But we didn't download our stable diffusion model until now. When we download our pre-trained stable diffusion model from Hugging Face community using this notebook will automatically put our stable diffusion model in this directory, in this ZWX folder. Here we will specify the hyperparameters of the training based on your memory, the size of your memory, which is 15 gigabytes. Let's firstly talk about the gradient checkpointing parameter. This parameter, this method, will reduce the space that our stable diffusion model wants from our memory to work and without filling our memory. Now let's talk about gradient checkpointing in depth. Firstly, let's say that we are not using gradient checkpointing method. We have this model with 6 layers, and we have this input here. We will pass it through the first layer, layer 1. And we will pass the outputs from layer 1 through the activation function, let's say RALU activation function. As we said previously, it is important to put an activation function between layers to make your model, your neural network, able to handle nonlinear relationships. Now the output from RALU activation layer, we will call it the activations of layer 1. Now we have the activations from layer 1. We will pass these activations through layer 2. So the activations of layer 1, they will be the inputs to layer 2. And we will pass the outputs from layer 2 through another RALU activation function. And the output from this activation function, we will call it the activations of layer 2, etc. We will call the process of moving from the input to the output of our neural network forward propagation. When we finish the forward propagation, we will get the activations for each layer in our neural network. Here we will get the activations that related with layer 1, the activations that related with layer 2, the activations that related with layer 3, and the activations that related with layer 4, the activations that related with layer 5, and the activations that related with layer 6. But why we need these activations, the activations that related with each layer in our neural network? Firstly, we need to store all these activations in the memory, because the activations are required to compute the gradients that we will use to update the weights of our neural network, the weights of each layer in our neural network. The process of finding the gradients, we call it the backpropagation. For example, let's say that we want to update the weights of layer 6. Okay? How can we do that? PyTorch will use the chain rule to compute the gradients, but we will not talk about the chain rule because it's not important for us here. Here, when PyTorch want to compute the gradients of layer 6, PyTorch will need the activations of layer 6, and at the same time we need the loss function. And if you want to compute the gradients of layer 5, so you need to have the activations that related with layer 5. And the same thing for all other layers. PyTorch will do that for us, but PyTorch needs this activation to compute these gradients. So we need to store these activations, but these activations will take space in our memory. And if your model is very large, so it will take large space from your memory. So now gradient checkpointing will solve this problem for us. This torch.no gradient, it will store half of the activations in our memory. So it will reduce the space that these activations will take from our memory. And it will also store the function parameter. Now let's see what will happen when we are using torch.no gradient. Firstly, let's say that we have this input here, and we have this layer, layer 1. At step 1, we will have the input to layer 1 and the output from layer 1. Now, we will pass the output from layer 1 through layer 2, okay, and we will delete this output of layer 1 from the memory, okay, and we will get the output from layer 2. As you can see here, the memory storing output of layer 1 is released. So we removed the output from layer 1 now from our memory. Step 3. As you can see here, the output of layer 2, we will keep it in our memory and we will pass it through layer 3 and we will get the activations of layer 3. That is step 3. Now what we will do, the output of layer 3, we will pass it through layer 4 and we will get the activations of layer 4 and we will delete the output of layer 3, the activations of layer 3. And as you can see here, the memory storing output of layer 3 is released. So we removed these activations and we will keep the activations of layer 4. Step 5, we will pass these activations of layer 4 through layer 5 and we will get the outputs, the activations of layer 5. Now we will pass the activations of layer 5 through layer 6 and we will get the outputs, the activations of layer 6 and we will remove the activations of layer 5. As you can see here, the memory storing output of layer 5 is released and we will keep the activations of layer 6 in our memory. And as you can see here, after this forward propagation, the memory is only occupied by the inputs, this one here, we didn't remove the input, and the outputs of layer 2, 4 and 6, okay? The activations of layer 2, layer 4 and layer 6. So now we have reduced the space needed to save the activations by half. Now let's talk about backpropagation. How can we do backpropagation when we're using this gradient checkpointing method? Let's say that we are here. We will start from layer 6. It is easy to compute the gradients of layer 6 because we have the activations of layer 6. The activations of layer 6, they are available in our memory. But how can we find the gradients of layer 5 to update the weights of layer 5? We removed the activations of layer 5 previously in forward propagation. To do that, we should recompute these activations. We have the activations of layer 4. We kept the activations of layer 4 in our memory. So we will pass them through layer 5 and we will get the activations of layer 5. We will use them to compute the gradients of layer 5 to update the weights of layer 5. And it's easy to compute the gradients of layer 4 because we have the activations of layer 4. So PyTorch will compute the gradients of layer 4 easily. But what about layer 3? We don't have the activations of layer 3. So we should recompute the activations of layer 3. So we should pass the activations of layer 2 through layer 3 to get the activations of layer 3. After that, we can compute the gradients of layer 3, the gradients that we will use to update the weights of layer 3. What about layer 2? We have the activations of layer 2. PyTorch will easily compute the gradients of the weights inside layer 2. What about layer 1? We don't have the activations of layer 1. So we should pass the input through layer 1 to compute the activations of layer 1. After that, PyTorch will easily compute these gradients. When we have the activations of layer 1, PyTorch will easily compute these gradients using chain rule. But as you can see here, when we are trying to recompute the activations of the layers, here we will recompute the activations of half of the layers inside our U network during backpropagation. By doing this, the time that we need to do backpropagation process, it will be longer. which means this gradient checkpointing method will make the training time longer because we need long time to update the weights of our U network. But when we save the activations of all layers, so we don't need to recompute the activations of any layer in our neural network because we have all the activations, so PyTorch will find the gradients quickly. After that, PyTorch will give these gradients to the optimizer. And that's the idea behind the gradient checkpointing. It will reduce the space that we need to make our stable diffusion model work. But at the same time, it will increase the time that we need to train our stable diffusion model. Now let's go back to Dreambooth Collab notebook. Here, as you can see in this table, in the first row of this table, we will make the train batch size equal to 1, which means that we will put just one sample inside each batch. Here it is difficult to make the batch size greater than 2 because it will fill our memory. But if your memory size it is greater than 15 gigabytes, so you can increase the batch size more than 2. And it's worth to mention that by increasing the batch size, you will make the training process better. Because here we will compute the gradients based on many samples. Because the noise inside these gradients will be small. In simple words, we will update the weights of our neural network with good gradients, with good values. Here we will also use mixed precision method to reduce memory consumption. Let's talk about this parameter in details. Now let's talk about what is mixed precision training. Firstly, we should talk about floating point precision. Historically, deep learning has used single precision, which is floating point 32. This floating point 32 precision will take 32 bits from our memory. And here you should know that the basic unit in the memory, it is the bit. Here they represented each parameter, each weight of our neural network by 32 bit, which means that each parameter, each weight will take 32 bits from our memory. We will use these bits to represent the value of the weight. Here we are using binary system, but we can convert it into just floating point number. Now the range of possible values that we can represent using this floating point 32 precision is from this very small number to this very large number. Now let's say the size of your stable diffusion model, the size of your U network, it is very large. So it means that we have a large number of weights. Each weight will take 32 bits from our memory. So at this case, this model will take very large space from our memory. So now how can we reduce this space? We can do it by changing the precision that we will use to represent any weight. Here we will use floating point 16. So now each weight will take 16 bits from our memory, which is half what it was previously. So now we reduced the space that our model needs from our memory by half. But the problem with this precision is that the range of the possible values that we can represent using this precision, floating point 16 precision, it is very small compared to floating point 32 range. As you can see here is the smallest value that we can represent using this floating point 16, and here is the largest value that we can represent using this floating point 16 precision. As you can see here, the range of possible values that we can represent using floating point 16, it is much smaller than the range of possible values that we can represent using floating point 32. which means that when we want to represent any weight using this floating point 16, we will not be able to make the value of this weight outside this range. It's like that we will restrict the values that our weight can take. And this thing might affect on the accuracy of the model that we will get after training. So we need to solve this problem. To solve this problem, we will create a copy of our model. The first model, we will make the precision of the first model floating point 16, and we will make the precision of the copy equal to floating point 32. We will use this model with the floating point 16 precision to do forward propagation and backward propagation. By doing this, we will make the space that we need during forward propagation and backward propagation half what it was previously, because here we are using floating point 16 precision for each weight in our model, which means the activations that we will get during forward propagation will be floating point 16 precision, and the gradients that we will get during backward propagation they will be floating point 16 bits, and the weights are also floating point 16 bits. Firstly, let's say that we did forward propagation and we did backward propagation, so now we have the gradients, and the precision of these gradients will be floating point 16. Now what we will do, we will convert the precision of these gradients to floating point 32. Why? Because now we want to use these gradients to update the weights of the copy. As you know, the precision of the copy, it is floating point 32. By doing this, the weights inside this copy might take values outside the range of floating point 16. Now the weights of our copy, it is not restricted with the range of floating point 16, but the gradients, actually, they are restricted by the range of floating point 16. And we will learn how to solve this problem also later. Now we will pass these gradients with the precision 32 through our optimizer with the precision floating point 32, and the optimizer will update the weights of the copy. Now we will convert the precision of this copy to floating point 16 and put it in the first model. Okay, now we have the first model and the copy, and we will do the process again and again until finishing the training steps. Now, as we said previously, the gradients, they are restricted because the precision of the gradients is floating point 16. So now let's say that the value of the gradient, it is very small value, which is outside the range of floating point 16. So how can we represent this gradient? We can do that by using loss scaling. As you know, the loss function and the loss value, it is very important thing to compute the gradients. PyTorch will use the loss value to compute the gradients of our neural network. So when we multiply the loss value with a specific factor, and after that doing backpropagation, this will make the gradients that we will compute during backpropagation, all of them, they will be multiplied with the same factor. It's like that we moved the range of the gradients to make the range inside the floating point 16 precision. By doing this, we will be able to represent most of the gradients using just our floating point 16 precision. And because that we know the factor that we used, that we multiplied our loss value with, so we can divide these gradients by this factor and we will get the actual gradients that we want. And as you can see here, firstly we will start with the scaled loss. We will do backpropagation and we will get scaled gradients, and the precision of these gradients floating point 16. Now we will convert the precision of these scaled gradients to floating point 32, and we will divide these scale the gradient by the factor that we used previously to get gradients, the actual gradients with the floating point 32. And here we will pass them through the optimizer, and we will use the optimizer to update the weights of the copy. We will convert the precision of these weights to floating point 16, and we will put them in our first model. After that, we will compute the loss again. We will scale that loss with the same factor, and we will do this thing again and again until finishing the training steps. And this is the mixed precision. And here we said mixed precision because we used both floating point 16 precision and floating point 32 precision during training. Now we have also gradient accumulation steps. This parameter, we will use it to increase the batch size without increasing the memory usage. Let's say that we want to make the batch size equal to 2, so we will make the gradient accumulation steps equal to 2. And we will keep the train batch size equal to 1. And we have also this parameter, use 8-bit Adam. By making this parameter equal to true, at this case, the optimizer that we will use, it will not take large space from our memory, because it will do all its operations with the 8-bit precision, which is very low precision. This parameter also will reduce the space that we want from our memory to make our stable diffusion model works. Here, because that our memory size it is 15 gigabyte, so we need to set these parameters to make the memory usage less than 15 gigabyte. We will create this list, concepts list. This list will have the prompt of our images that we will use during training our stable diffusion model. Here we can create a specific prompt for each image in our own dataset, but here we will just use one prompt for all images. Here I will change this prompt. Instance prompt, I will make it photo of ZWX my image. Okay, and here I will do the same thing, and here also. Okay, now let's run this cell, and we will get this JSON file here, concepts list.json. This list will have the prompt that we will use during training on our own image. Now we will upload our images. How can we do that? Firstly, we should run this cell. Now we will click on choose files, and here I have my own images. I will select all of them and I will click open. Now what we will do, we will create data folder like what we did previously. We have this data folder here. Inside this data folder we will have ZWX folder, and inside this folder we will have all our images. There are 6 images. Okay, I will use them to train our stable diffusion model. The prompt for all these images is photo of ZWX my image. Now you created the directory of your dataset, which is this one here, and you put your images in that directory. Now what we will do, we will use a train dreambooth.py script. This script, this Python script, will train our pre-trained stable diffusion model. It will train it on our own images. Here we will put the model ID of our stable diffusion model, our pre-trained stable diffusion model. Okay, we will put it here. So pre-trained model name or path equal to model name. And here we will specify the variational autoencoder that we will use during training, which is this one here. And we will make the output directory argument equal to output directory variable. هذا الاوتبوت directory variable راح يحدد المكان اللي راح نوضع به الستيبل diffusion model بعد تحميله من موقع الهاجن فيس. Here we will make the resolution of our stable diffusion model equal to 512, which means 512 height and 512 width. And here we will specify the batch size, which is equal to 1, which means inside each batch we will have just one image. Okay, here we will use mixed precision. Here we will make gradient accumulation steps equal to 1. Here we will make the learning rate equal to 0.000001. It is very small value because we don't want to destroy the weights during training. We want from our diffusion model to remember what it learned in the previous training. Here we will make the maximum training steps equal to 800. وهنا راح تجعل ال save sample prompt يساوي الفوتو of zwx my image، وكذلك ال concepts list تساوي ال concepts list.json. Now let's run this cell. Now we trained our stable diffusion model. We fine-tuned our stable diffusion model. Let's try to use this stable diffusion model. And as we said previously, we said that we will store our diffusion model in this directory. Okay, so now let's go to our Google Drive. Firstly, we should enter to stable diffusion weights, and inside this folder we will have this folder zwx, and inside this folder we have two things, this folder and this folder, and inside this folder 800 folder you will have the weights of your model. Now we will use this model to generate amazing images. Now we should put the directory of our diffusion model, stable diffusion model, which is this directory here. We should copy the path and we should put it here. Okay, that's it. Now what we will do, we will run this cell, run to generate a grid of preview images from the last saved model. And here is these images. They are amazing images for me. Here we will convert the weights of our stable diffusion model to checkpoint. Why? We will learn why we need to do that later. Let's run this cell. Run conversion. Here we will make the data type of the weights equal to float 16. By doing this, the space that this file, this checkpoint file, will be 2 GB, but if it is float 32 it will take 4 GB. Okay, now we have our stable diffusion model, model.checkpoint. We will see this model in this directory in this folder, 800 folder. Let's go to this folder. Firstly, we should click on drive and my drive, and we will go to stable diffusion weights ZWX 800, and here we should click on 800, and here's our model.checkpoint. We will learn why we need to use this file later. Okay, now what we will do inference. In other words, we will use our stable diffusion model. Firstly, we will import all these things. The most important one is stable diffusion pipeline and DDIM scheduler. Here we will make model path equal to weights directory, which represents this directory. We will go to drive, my drive, and stable diffusion weights ZWX. This directory, we will copy the path, which represents the model ID. We will pass it through from pre-trained method, okay, like this, and we will send this model to our GPU. Here we will use DDIM scheduler, okay, and we will make the configuration of this scheduler equal to the configuration of the scheduler that we used during a training. So we will type pipe.scheduler.configuration. Okay, now we have our scheduler, DDIM scheduler. We will put this scheduler in our pipeline to make the inference time smaller. Here we can set the seed, the value of the seed. This seed, we will use it to create the generator that we will use to generate the noise XT capital. By doing this, you will be able to reproduce the same images that you generated previously. Okay, we will run this cell. Now we should generate an image using our diffusion model, a photo for let's delete this one, a photo of ZWX my image. Now our stable diffusion model will try to generate an image based on this prompt, which is of course the images that we use to fine-tune our diffusion model. Here we can specify the number of inference steps. Let's make them 15, and here we have the guidance scale and the number of the images that our diffusion model will generate. We will generate 4 images here. Here we have negative prompts. If you don't want to see specific thing in your image, you can put it here. Okay, now let's run this cell and see the image that our diffusion model, our stable diffusion model will generate. As you can see here, here is the images that our stable diffusion model generated. Now let's try to change these images a little bit. Let's try to add more to our prompts, because as we know, this is stable diffusion model. They trained it previously on very large number of images. So let's try to add to this prompt to make our image something similar to what we want. As you can see here, I put it the previous prompt, and here I put it enemy style, and let's see the results. As you can see here, here's the first result, the second one, the third one, and the last one, this one here. Now I will add Van Gogh Starry Night style to my image, and let's see the results. And here is the results. As you can see here, we have all these images. You can try to run this cell many times to get the best image that you want. And here is another image. This one here also, and this one, and this one. As you can see here. Here we have another images. As you can see here. Now try to use what you want, try to change the prompt and see the results. And try to use your own images to train your stable diffusion model and see the results. Thanks for. Hi, in this lecture we will talk about control net and how we can use it with stable diffusion model. Firstly, why we need to use control net with our stable diffusion model? We need to use this control net to get more control about what our stable diffusion model will generate. Previously, we learned how to generate an image based on our text. And we saw previously that our stable diffusion model will generate an image based on our text. The contents inside the generated image, it will be similar to our text. That's good, but we need more control. For example, let's say that we want to generate an image for deer using our stable diffusion model. And you want to make the deer that you will generate using our stable diffusion model to be something like this, to stand like this, and the shape of the deer you want it to be something like this. So at this case, you will not just pass a text about what you want to generate, but you will also pass this thing here, which has the shape of the deer that you want to generate using your stable diffusion model. Here we will extract the shape of the deer from this source image using canny edge detection. This function will convert this source image to this image here. This image will just have the shape of the deer inside this source image. Okay, we will use this one, this canny edge image as input, as condition to our stable diffusion model. And we will use our stable diffusion model with this condition to generate all these amazing images. The shape of the deer in all these images similar to the source image that we have here. All these deers have the same shape for our source image, but of course with different colors and backgrounds. So how can we do that? How can we train our stable diffusion model with control nets? This control net will allow us to control the final image generation through various techniques like pose, edge detection, depth maps, and many more. Now, how control net works? Firstly, we should create 2 copies of our stable diffusion model. The parameters or the weights of the first copy will be frozen, which means that we will not train them. We will use them as they are even during training. And we will use the encoder part of the second copy to create our control net. The parameters or the weights of the encoder part of the second copy will be trainable parameters, which means we will update them during training our control net. This control net will take the condition as inputs, for example, canny edge inputs, and we will also pass the noisy image through our frozen copy of our stable diffusion model. We will pass this condition firstly through a zero convolution layer. We will make the number of filters inside this zero convolution layer equal to the depth of the noisy image, which is equal to 3. By doing this, we will make the depth dimension of the output of this zero convolution layer equal to 3. Let's talk about zero convolution layer in depth. Firstly, let's talk about the size of each filter inside this zero convolution layer. The size of each filter inside this convolution layer will be 1 times 1 times d, which means the width and height of each filter inside this zero convolution layer will be 1. And the depth dimension will be equal to the depth dimension of the input to this zero convolution layer. For example, let's take just one filter of this zero convolution layer. We will multiply this filter firstly with this part of our input, and we will get this single number. We will slide this filter along the input, and we will do the same thing again and again until reaching the end of the input. Now we will have this feature map. The width and height of this feature map that we created using this filter will be similar to the width and height of the input. So now we know that zero convolution layer will not change the spatial dimensions, the width and height. The output spatial dimension will be equal to the input spatial dimension to zero convolution layer. But when we increase the number of filters inside this zero convolution layer, we will be able to change the number of feature maps that we will get from this zero convolution layer. So we can say that we can control the depth dimension of the output from zero convolution layer based on the number of filters inside this zero convolution layer. As you know, each filter will create its own feature map. So the number of the output feature maps will be equal to the number of filters inside zero convolution layer. But why we put it 0 in the name of this layer? Why we set zero convolution layer? It's because that the parameters of this zero convolution layer will be zeros initially. We will not initialize the parameters of the zero convolution layer randomly, but we will make the value of each parameter in zero convolution layer equal to 0 firstly before training. This thing will make the training better. You might ask yourself why it is better to initialize the weights of our convolution layer, our zero convolution layer, firstly with zeros. The answer to this question in this place here. Here we will add the output of zero convolution layer to the noisy input image. When the values of the parameters of zero convolution layer equal to zeros firstly, at this case, when we add the noisy image to the output of from this zero convolution layer, the output from this addition operation will be the noisy input image itself. By doing this, the encoder part of the stable diffusion model will not shock by the input to it. It is just a normal noisy image that it trained previously on, and it learned how to remove the noise from it. And by doing this, we will avoid destroying the weights of the encoder part of the stable diffusion model during training this control net. We will start with something familiar to our encoder part of the stable diffusion model. After that, we will move on during training. because this stable diffusion model, it is a pre-trained model. We will not just train from scratch, but we are trying to do fine-tuning here. And using zero convolution here, it is very important to do good fine-tuning. During training, we will gradually update the weights of zero convolution layer to fuse the condition in good way with the noisy input image. Now we will pass this noisy input image through the first block in our stable diffusion, and we will pass the output here to the first block in the encoder part of the stable diffusion. The parameters here, as we said previously, they are trainable parameters in this block and in all blocks inside this encoder. Here we will convert the prompt using text encoder to numerical representation. After that, we will pass it through this block inside our stable diffusion model, and we will encode the current time step through time encoder to get a numerical representation for the current time step, and we will also pass it through the first block in the stable diffusion model. Here we will do the same thing. We will convert the prompt and the time to a numerical representations, and we will pass them through the first block in control net. And we will move through these layers to reach the middle block. After the middle block of this encoder part, we will put zero convolution layer, and we will get the output from this zero convolution layer. And what we will do here, we will pass it to the middle block of our stable diffusion model. As we said previously, here this block, it is not a trainable block. The parameters inside this block, they are not trainable parameters. So what we will do actually here, we will get the output of this middle block, and we will add the output of zero convolution layer to this output, as you can see here. By doing this, you will not just create your image based on the prompt, but also based on the new condition like Kenny inputs. And here we will also take the feature maps from this skip connection of this block, and we will pass these feature maps through 3 zero convolution layers, and the outputs from these 3 zero convolution layers, we will add them with the outputs from these 3 decoder blocks. We will do this thing again. We will take the feature maps, the output feature maps from these 3 blocks, and we will pass them through 3 zero convolution layers, and we will add the outputs of these 3 convolution layers to the output feature maps from these 3 decoder blocks. You should know that all these zero convolution layers, they are trainable layers. The parameters inside them, they are trainable parameters. And we will do this thing again and again until reaching the output of our stable diffusion model. The output will be the predicted epsilon. This predicted epsilon will be based on our prompt and our condition here. And we will update the weights of this control net to reduce the difference between the actual noise and the predicted noise. And that's how can we train our control net with the stable diffusion model. Here now we have many different conditions. Firstly, we have this original image. We will apply Kenny detection to get this image. This image will be the condition for our control net. Okay? Because this control net, we fine-tuned it previously on Kenny input. And like what we said previously, we will use this control net to do reverse diffusion, just reverse diffusion, and we will get this amazing image. and this one here. And here we have this prompt, a man standing on top of a cliff. Okay, and you can add to this prompt to change the style of the generated image also. So now you have more control about what your Stable Diffusion model will generate. And we have this input. It is just a sketch. It is a scribble drawing, very simple drawing. We trained our control net previously on these scribble drawings, so now we will pass this scribble drawing through our control net, and here we will add the prompt and the condition. The prompt here, it is a turtle in a river, and as you can see here, our Stable Diffusion model with control net created these amazing images here, and you can change the prompt as you want to change the style of the image. So now we created these amazing images with just XT capital, pure noise from the standard Gaussian distribution, and scribble, condition, and simple prompt. And here we applied pose detection on a specific image. Okay, this image here. And now what we will do, and now we have control net that trained previously on pose detection images. So we will use this control net during reverse diffusion. We will pass human pose through our control net and our frozen copy of our Stable Diffusion model, and we will do reverse diffusion to get these amazing images. And also we will pass this text, this prompt, to control the background and texture, and the style of the person itself. Here we set a man wearing sunglasses near a street corner, and as you can see here, we got what we want. The man inside this generated image stands like this input here, this condition that we passed through control net. In the next lecture, we will learn how to use control net with a Stable Diffusion, practically using diffusers package. Thanks for watching. Hi, in this lecture we will talk about control net with a Stable Diffusion model. We will learn how to use control net to create amazing images. Firstly, we will install diffusers package, transformers package, xformers package, and we will install accelerate package. Okay, let's run this cell. Now we will install OpenCV package and control net AUX package. Let's run this cell. Now I have this image. It is my image on my desktop. I will put it here in my notebook. So I will click here and I will drag and drop this image here. Okay, so now here is my image. I will copy the path of this image. Now from diffusers.utils, I will import load image class. I will use this class to load my image and put it in this variable, image variable. So image equal to load image, and here I should put the path of my image, which is this one here. Okay, I should put it here between these two parentheses, and here's my image. Okay, now I will import CV2 package, OpenCV package, image class, and NumPy package. Okay, now I will convert this image variable to NumPy array. Okay, Let's see what is inside image now. It is just numpy array, okay? Here I will create two variables. The first one is low threshold variable and I will make it equal to 100. The second one is high threshold variable and I will make it 200. I will use these two variables to convert my image, my source image, to Kenny inputs. Okay? If the value of any pixel greater than 100 and lesser than 200, we will accept it as an edge. Okay? Now, let's create the Kenny input based on our image. So we will type image equal to cv2.kenny, and here we will pass the image, our numpy array, this image here, and we will pass low threshold variable and high threshold variable. Now what we will do, firstly you should know that after applying Kenny function, the shape of the output will be just two dimensions, the height and width dimension. What we will do here, we will add the third dimension, which represents the depth dimension. Firstly, we will add new dimension with length 1. Let's now see the shape of image. As you can see here, we have this new dimension with length 1. Now we will convert the length of this dimension to be 3. How can we do that? What we will do, we will use mp.concatenate, and here we will repeat this numpy array 3 times along this dimension. The index of this dimension equal to 2. The index of the first dimension is 0, the index of the second dimension is 1, the index of the third dimension is 2. So we will create this list here. Inside this list we will repeat the image array 3 times. This one, and this one. And we will put them along the depth dimension or the channel dimension. And the index of this dimension equal to 2. Now let's see the shape of this image array. As you can see here, now this array has 3 dimensions: the height, the width, and the depth dimension, and the length of the depth dimension equal to 3. Now we will display this image. So we will type Kenny image equal to image class dot from array, and here we will pass our numpy array. Now let's display our image, and here is our image. As you can see here, the shape of my face, it is available here. Okay, it's good. Now we have the condition that we will pass it through our control nets. Now let's download our control net from Hugging Face community. Firstly, we will import the Stable Diffusion control net pipeline from diffusers, and we will also import control net model from diffusers package. Here we will import PyTorch package. Now we will download the control net that we will use to get more control about what our Stable Diffusion model will generate. So control net equal to control net model dot from pre-trained, and here we will pass the model ID. Here we will use the control net that I trained previously on Kenny images, and here we will load it with half precision to reduce the memory consumption. Now we will create the pipeline that we will use to generate the images. So pipe equal to Stable Diffusion control net pipeline dot from pre-trained, and here we will pass the model ID of our stable diffusion model that we will use. And we will also pass the control net model. Okay. And here we will use the half precision. Now our pipeline has the stable diffusion model and the control net, so we can use it to do reverse diffusion and create amazing images. Okay, now let's run this cell. Now we will enable model CPU offload. So we will type pipe.enable model CPU offload. By doing this, the pipeline will automatically take care of GPU memory management. By doing this, we will reduce the GPU memory consumption, and we will also enable Xformer's memory efficient attention. Firstly, you should know that the cross-attention layers and self-attention layers, these layers will take large amount of our memory, and these layers are very slow. So we will use Xformer's package to make these layers faster, and at the same time we will prevent them from taking large space of our memory. To do that, we just need to enable Xformer's memory efficient attention. Actually, you can use this one also during training of your stable diffusion model. Now we will create our prompt. Let's say anime style, okay, blue eyes, white skin. Now we will use the pipeline to generate the image. Firstly, here we will use our pipeline. We will pass the prompt, which is this one here, our prompt, anime style, blue eyes, white skin, and we will pass the Kenny input, Kenny image, and we will also pass the negative prompt. Here you can use this negative prompt if you don't want to see something in your image and you want to make sure that you will not see something in your image, so you can put it here. And here we will specify the number of inference steps. Now let's run this cell. Now let's see the generated image. Okay, and here is the generated image. It is good image. As you can see here, we have blue eyes and white skin, as you can see here. But I don't see the anime style here. Here I changed the prompt to this one, anime Naruto, green trees, best quality, extremely detailed, and I multiplied this list by 4 because I want to generate 4 images using the same prompt. Okay, by multiplying this list by this number 4, so we will repeat this prompt 4 times in this list. And we will do the same thing here. We will multiply this empty list by 4, this list that represents the negative prompt. So we will create 4 empty negative prompts, and we will set this negative prompt argument to this list. Okay, and we will make the guidance scale equal to 15. Now let's see the final results. Here's the first image generated using our diffusion model. As you can see here, the green trees and the yellow hair. Let's see another image. Here is another image. Here the color of the eyes is blue. Let's see another image. Here is another image, and here is another image with the anime Naruto style. Here we have another image, which is good image. Now we will download another control net. This control net trained on scribble images. Let's firstly create our sketch. Firstly, we should click on bitmap images, and here we should click on open with paint program, and here we will fill this white region with black color, and now we will click on white, and we will click on this place here. Now let's increase the size, and we will click on this one here. Now we will create our sketch. Let's create very simple fish like this. Okay, this very simple sketch, and we want to from our control net and stable diffusion model to create amazing image from it. Okay, now we have our sketch. We will save it, Ctrl S, and now we have our sketch here. We will click on this place here, and we will put this image here in this place. Now we have our sketch. Let's now create our prompt. Here is our prompt: fish, red body, best quality, extremely detailed. Now let's download this sketch. So we will copy the path. We will use load image class, and we will pass the path of this sketch, and we will get this image. Now we will download this control net. They trained this control net on scribble images. Okay, now we will create the pipeline, and here we will pass the stable diffusion model that we will use here. You can use a dreamlike diffusion model, which is very good stable diffusion model if you want. And we will also pass the control net to this pipeline. Now we will create the prompt. Like what we said previously, it is just a fish, and we want the color of this fish is red, and we want best quality with extremely detailed. We will use load image class, and we will pass the path of this sketch. Now we have our image, and like what we did previously, we will use xformers, and we will enable model CPU offload. Now we will pass the prompt and the image, and we don't want negative prompts, and here we will make the inference steps equal to 50 and the guidance scale equal to 15. Let's see the final image. Wow, that's good image. It is an image for fish. It is similar to the shape of the sketch, which is this one here. Now let's draw another thing. Let's make the size equal to 5 pixels, and we will make the color white. Here I will create enemy character. Okay, like this. And that's it. Now we will save this sketch and we will put it here. Now we will copy the path of this sketch and we will put it here. We will change the prompt. It is enemy. Here we will put boy. And best quality, extremely detailed. Now we will run this cell. Let's run this cell also. Let's here make just 20 inference steps. We will multiply this with 4 to generate 4 images, and we will multiply this place here also with 4. Let's run this cell. As you can see here in this image, we created this image based on this sketch here. Okay, it is good image, as you can see here. And we can also use this argument control net conditioning scale to specify the importance of the sketch or the condition that we will pass through our control net. The value of this control net conditioning scale should be between 0 and 1. As you can see here, we made the value of control net conditioning scale equal to 0.2, and here is the results, as you can see here. And as you can see here, it is a little bit similar to our sketch, but it is much better than our sketch. When we increase the value of control net conditioning scale, the generated image will get closer and closer to the shape of our sketch. As you can see here, we made the value of control net conditioning scale equal to 0.3, and this generated image, it is closer to our sketch. Hi, in this lecture we will talk about in-painting with a stable diffusion model. Previously, we talked about repaint algorithm, and we used this algorithm to do in-painting with unconditional diffusion model. Now we are working with a stable diffusion model. It is not a good choice to use repaint algorithm with stable diffusion models because you will not get good results. Here we will train our stable diffusion model with mask. We will put the mask with the input to our stable diffusion model, and we will pass this new input to our stable diffusion model, and we will try to predict the epsilon, and we will try to reduce the error. So here we need to fine-tune our stable diffusion model again to do in-painting. They did that for us, so we will use their stable diffusion in-painting model to do inference, or in other words, to do reverse diffusion and create new images. Firstly, we will download diffusers package, transformers package, FTFY package. We don't want this one, and we will download accelerate package. Let's run this cell. Now we will import NumPy array as MP, PyTorch package, PIL package, and here we will import stable diffusion in paint pipeline from diffusers package. This pipeline will make it easy for us to do in painting with a stable diffusion. Here we will specify the device that we will use to do reverse diffusion, and what we will do here, firstly we will specify the model ID, which is this one here, runway ml/stable diffusion in painting. Now we will create the pipeline that we will use, which is pipe equal to stable diffusion in-paint pipeline.from pre-trained, and here we will pass the model ID and the precision of our model or our pipeline, and here we will send our pipeline to our device, and here we will import requests package, and we will import bytes IO from IO package. We will use these two things to download our image and the mask of the image from these two links. Now we will create this function. This function will download our image and the mask of the image. So we will define this function, define download image, and here we will pass just one argument, which is the URL, the link. And here we will use requests package to get all the information about the URL. And now we have this variable, response variable. We will get the contents from this response variable. So we will type response.content, and we will pass these contents to our bytes IO. Okay? Now the content is just one image. So we will open this image using pil.image.open, and we will convert the order of the color channels to be red, green, and blue, RGB. Now we have two links. The first link represents the image, and the second link represents the mask of the image. Let's run this cell. Now, firstly, let's download the image, our image. Here is our image. It is an image for a dog. Okay. Now let's download the mask of the image. We will use the same function, download image function again, and we will pass mask URL, the link of the mask. And here we will resize the mask image to be 512 times 512. And we will get this mask here. We just need to remove this dog from this image, and we want to replace it with another thing based on our condition, based on our prompt. Okay. Now we will create our prompt. As you can see here, we want to see a robot instead of the dog inside this image. Here we will specify the guidance scale, and we will make it equal to 7.5, and we will specify the number of samples we want to generate 3 images from our stable diffusion model. And here we will create our generator. This generator, by specifying the seed of the generator, here we made the seed of the generator equal to 0. It means that we will get the same xt capitals again and again and again, which means that we will end with the same 3 images again and again and again after doing reverse diffusion. We can change the seed number to change the images that we will generate, these 3 images that we will generate using a stable diffusion model. Now we will use our pipeline. We will pass the prompt, we will pass the image, we will pass mask image, also the mask of our image, and here we will pass the guidance scale, the generator, and the number of images that we want to generate. Now let's run this cell. Now after finishing reverse diffusion, we will get these amazing images. This one, it is the original image. We removed this dog, and we completed the masked region with all these robots. Okay, and that's very good, as you can see here. Thanks for watching. Hi, in this lecture we will talk about optical flow, which is one of the most important techniques that we should know before moving to learn how to convert our video into animation. Firstly, what is optical flow? Optical flow shows the movements of the pixels between two frames. For example, let's say that we have these two frames. This is the first one and the second one. The optical flow for these two frames is this one. This optical flow will tell us which pixel in the first frame moved in the next frame, and the direction of movement and the amount of movement. So as you can see here, all the pixels that represent this card, they moved in a specific direction in the next frame. So each one of them has its own vector that represents the direction of movement and the amount of movement. We will call all these vectors that represent the movement of each pixel by optical flow. In 2015, they started using deep learning to solve optical flow tasks. They tried to train a U network to find the optical flow from two images or two frames. The structure of the U network that they used, it is this one here. We will pass the first frame of our video through this branch here. There are many convolutional layers in this branch. We will pass this image through them, through all these layers, all these convolution layers. And we will do the same thing for the next frame of our video. We will pass it through this branch, all these convolution layers. And here we will do special thing. We will find the correlation between these feature maps. So how can we do that? To understand the idea behind this correlation layer, we should understand this formula here. Firstly, here we want to find the correlation between two patches. One of these patches is available in F1 feature map, and the other patch is available in F2 feature map. The center of the first patch, it is x1, which in this case it is this location here. The index of this location is 1, 1, and the center of the other patch, it is x2, which is this location here. The index of this location, it is 2, 3. Because as you know, in Python we start with index 0. So the row of this center, it is equal to 2, and the column of this center, it is equal to 3. Now what we will do actually, we will do dot product. This symbol here for dot product. Okay. This formula here will multiply this patch with this patch, element wise, and after that it will add the results to get just one single value, which is something similar to the convolution operation that we talked about previously. Here, this patch in F1 feature map, it is like a kernel that we will multiply with this patch in F2 feature map. So this operation is something similar to convolution operation. Now after applying this formula, we will get just one single value. This value will represent the relationship between this batch and this batch. So now we are doing matching process, which is something very important in optical flow. When the correlation between these two patches is very high, it means these patches, they are very similar to each other. And by doing this, we will be able to know that x1 batch, it is just moved and created x2 batch in feature map 2. Our neural network will try to learn these correlations. And by using these correlations, we will be able to match between batches. Here we took just one single example about how to compute the correlation. But actually, we will find the correlation of this batch with all possible batches in this feature map too. And we will go to another batch here, and we will find the correlation between this batch and all possible batches in F2. And when we want to find the correlation between, for example, the first batch in F1 feature map and all batches in F2 feature map, we will get new feature map. And when we want to find the correlation between the second batch in F1 feature map and all batches in F2 feature map, we will get another feature map in the output. Okay, so we will get very large number of feature maps. So now the depth dimension of the output will be large, which is equal to the possible patches inside F1 feature map or possible patches inside F2 feature map. As you can see here, these two feature maps, F1 and F2, they have the same size. So now we have very large number of feature maps in the output. Our output is very large, and that's not good. We did a lot of computations to get this output. This thing will take time, and if our output is very large, so it will take a lot of our memory also. All these things, they are not good. So what we will do here, we will reduce the spatial dimensions of the output. How can we do that? The idea is super easy. Here we will not compare this batch with all possible patches in F2, but with the nearest batches in F2. So here what we will do, we will restrict the search space. For example, here we have our batch, which is X1 in this case, this one here. Here we will not find the correlation between X1 and all X2 patches, but we will find the correlation between X1 with the nearest X2 patches to our X1 batch. In other words, here is our X1 batch, and here is the center of this batch. Let's say that the displacement, the maximum displacement, equal to 1. By doing this, we will restrict the search space. Now we will find the correlation between this X1 with this batch here that has the same center of X1 batch. Okay? And this batch here, which moved just one step from the center of X1. So now we have two batches, and this batch here also we have 3 batches, and this batch here. So we have 4 batches. So in other words, we will just find the correlation between this batch with the patches that are near to the center of our X1 patch, but in F2 feature map. So here we didn't take all patches in F2 feature map, but just a few of them. So here we reduced the computations, because here we will not use this formula a lot. And we will take another patch in F1 feature map, and we will find the nearest patches in F2 feature map for this patch in F1 feature map, and we will do computations to find the correlation, and we will do this process again and again until reaching the last patch in F1 feature map. By doing this, we will reduce the size of the output from our correlation layer, and we will speed up our network because we will reduce the computations. But the problem here, you will not be able to match any patch in F1 feature map with very far patch in F2 feature map. So for example, if you have very fast object in your video, if you use this correlation layer, you will not be able to match the batches that are related with this object in the first frame and the next frame. So you will not be able to get the correct optical flow for this object. And we will pass the output from this correlation layer through many layers, and we will pass the output through this refinement part of our network. This refinement part will increase the spatial dimensions of our optical flow by using up convolution layers. And here's the output optical flow feature map. You can see the resolution of this optical flow. It is not similar to the resolution of the input frames. And they found that adding another convolution layers will not be helpful. It will increase the spatial dimensions of the optical flow, but it will be something similar to any other simple resizing methods. So for this reason, they used the variational refinement to make the resolution of the optical flow similar to the resolution of the input frames. In the next lecture, we will talk about GM flow method to find optical flow. Thanks for watching. Hi, in this lecture we will talk about GM flow, and we will learn how to use it to find optical flow. Our previous way was as following. We found the local correlation between feature 1 and feature 2, and we passed the results through several convolution layers, and finally we got the optical flow. Now what we will do actually, we will pass our feature 1 and feature 2 through this transformer model. Actually, inside our stable diffusion model, there are many transformer blocks. These blocks have self-attention layers and cross-attention layers. But what is self-attention and cross-attention? Let's say that we are looking to this garden. Each thing in this garden, we call it node. We have node 1 for the first tree, node 2 for the second tree, node 3 for the first bird, node 4 for the second bird, node 5 for the third bird. And each node here in this scene, it has three things, three vectors: key vector, q vector, and v vector. For example, node 1 has key 1, q1, and v1. Now what we want actually, we want from our neural network to find the relationship between all these nodes in this scene. We will use these keys, queries, and values to do that. Here, what is key? Key, it means the most important things and characteristics of the node. We will get these keys, queries, and values from 3 feed forward layers. The first layer, it is key layer. The second layer is query layer. The last layer is value layer. Now if we want to know the relationship between nodes, firstly let's take node 1, and we want to know the relationship between node 1 and all the other nodes. Firstly, we will take the query of node 1. This one will ask each key, how important are you to me? And these keys will have the answer for this question. Of course, we will train our neural network to make these keys have the answer. Of course, to answer this question, we just need to multiply this q1 with each key in the scene. Actually, here we will do dot product. We will multiply q1 vector with the k2 transpose vector divided by the square root of the number of elements inside any one of these vectors. We did that for normalization because it is important during training our neural network. After that, we applied softmax activation function to the result. By doing that, we will be able to convert our attention scores into probabilities. Now we have the relationship between node 2 and node 1. We will call the results that we will get here the attention. We will multiply this value with value vector for node 2 in this case, and we will get the amount of the contribution that node 2 can do to our node 1, and we will do this thing for the rest nodes. We will compute the contribution that each node can do for node 1. After that, we will add all these together to get a new node. This new node has the global interaction between node 1 and all the other nodes, so it is more useful than our node 1 itself. We will do this thing for the other nodes in our scene to get more useful features. And cross attention, it is very similar to self attention, but here actually we will take K transpose and V vectors from different places. We will take them, for example, from text embeddings to make some kind of condition, but we will take Q vectors from our feature map, our original feature map, or our original image. And here we will do same what we did previously. We will multiply these queries with the K transpose vectors, and we will divide them by the number of elements inside each vector, and we will take softmax for the result to get the attention matrix. After that, we will multiply this attention matrix with V vectors to get a new features or new nodes. Now let's go back to our GM flow model. Here we will pass feature 1 and feature 2 through our transformer model. Why we use a transformer model? Because this model, we can use it to consider the mutual dependencies between feature 1 and feature 2 by using self-attention layers inside this model. And that's what we will learn later. And this transformer model will also return two things, two feature maps. We will pass these two feature maps through this global correlation softmax, and after that we will get the optical flow. This method will solve the problem of the previous method. It will be able to catch the fast objects in your video. In other words, it will be able to find the optical flow for the fast object. Because here we will match each batch in F1 to all patches in F2. We will use global correlation softmax to catch the large displacements in the pixels. Now let's say that we have two frames, frame 1 and frame 2. Okay, here is frame 1 and frame 2. Firstly, we will pass frame 1 and frame 2 through any convolutional neural network, for example AlexNet, to get a new feature representation for these two frames. These two feature maps that we got from this neural network, they will have the most important thing inside our frames. So now we have F1 and F2. The size of F1 and F2 is H times W times D. This size will be based on the convolutional neural network that we used to extract these two feature maps. Now we will pass these two feature maps through transformer model. This transformer model will create high quality discriminative features that we will use for matching. They will be very useful to find the optical flow because these features are high quality features. They are better than this one and this one. But why these feature maps that we will get from this transformer model, they are better than the previous features? That's because our transformer model able to inject the mutual information between f1 and f2 in the resulted feature maps. So the resulted feature maps, they will be more useful than the previous feature maps. But how we can do that? We will use cross-attention layers to do that, to do this injection process. Firstly, we will pass these two feature maps through our transformer model. Our transformer model will add another feature map for each one of them, which is positional encoding feature map. We used it previously to make our stable diffusion model able to distinguish between time steps, but here we will use it to make it able to distinguish between pixels, the location of the pixels. We will use it to make our transformer model able to know the spatial locations, which is something important to find the optical flow. Now when we reach the first cross-attention layer in a transformer model, we will do the following. Here we will change our cross-attention layer a little bit. What we will do actually, firstly we will get the Q, K, and V for feature map 1, and we will get Q, K, and V for feature map 2. Now let's pass feature map 1 first. So what we will do in this cross-attention layer, we will keep the query matrix of the feature map 1 as it is, and we will replace the K and V matrices of feature map 1 with the K and V matrices of feature map 2. By doing this, you will inject some information about feature map 2 in the resulted feature map 1. And we will do the same thing for feature map 2. We will keep the query matrix of feature map 2 as it is, and we will replace the K and V matrices of feature map 2 with the K and V matrices of feature map 1. And we will use our formula to get the attention matrix, and we will multiply the V matrix with the attention. And finally, we will get the new feature map 2. As you can see here in this formula, firstly, we added the positional information for F1 and F2, and we passed them through our transformer model to get a new feature map. And we have one problem here with this transformer model. The original transformer model has quadratic computational complexity. It means that when we increase the spatial dimensions for these feature maps, the time that we need to pass these two feature maps through our transformer model will increase quadratically. To solve this problem, we will use a special kind of a transformer model, which is a Swinny transformer. This model has efficient and fast attention layers. Now we will pass these two new feature maps through this correlation softmax block. This block will find the correlation between feature map 1 and feature map 2. To do that, we just need to multiply the new feature map 1 with the new feature map 2 transpose, and we will divide them by the square root of the number of channels of any one of these new feature maps. We did that just for normalization because it is good for training our neural network. Now the size of this correlation matrix is H times W times H times W. In other words, this correlation matrix will have an array for each pixel inside the new F1 feature map. This array will have the correlation between this pixel inside the new feature map 1 with all pixels inside the new feature map 2. And now we will pass this correlation matrix through softmax function to get this M capital matrix. The size of this matrix will be similar to the size of C capital matrix. This matrix, it is the matching distribution matrix. And now what we will do, we will create G capital matrix or grid matrix. The size of this matrix is H times W times 2. The elements of this matrix are the XY locations. When we multiply them with this capital matrix, the matching distribution matrix, we will get G hat. And this G hat will have the predicted new location of each pixel in our first frame. And we found these new locations based on the correlation matrix that we computed between the new F1 feature map and the new F2 feature map. Now if you want to find the optical flow, we just need to subtract the original locations from the predicted locations to get the matrix. This matrix will have the optical flow. Now we have just one problem actually. This global correlation softmax block expects that all the pixels in the first frame, they are available in the next frame. So they can be matched by comparing their similarities using our correlation matrix. But this assumption will be invalid for occluded and out of boundary pixels. They solved this problem by just passing our optical flow and the new F1 feature map through this self-attention, and inside this self-attention we'll do the following. Frame 1. We will find the matching distribution between the pixels of the same frame, and we will redistribute our optical flow that we found previously on the pixels of our frame 1 based on these similarities. It's like that we will propagate the high quality flow predictions for matched pixels to unmatched pixels by measuring the feature self-similarity. Now we will learn how to use GMFlow model practically. Now we will learn how to download and use GMFlow model. Firstly, we should download GMFlow repository in our notebook. To do that, we just need to type !get clone, and here we should put the link of the repository. Now we will run this cell, and that's it. Now we downloaded this repository. Now we will import GMFlow from gmflow.gmflow.gmflow. Okay, let's run this cell. Now let's create our GMFlow model. So we will type GMFlow model equal to, and here we will use this GMFlow class to create our model. We will make feature channels argument equal to 128, num scales equal to 1, upscale factor equal to 8, num head equal to 1, attention type swim, ffn dim expansion equal to 4, number of transformer layers equal to 6, and we will send this model to our GPU. Now we created our GMFlow model, but the weights inside this model, they are random. So we will replace them with the pre-trained weights. Actually, they trained a model with the same structure previously. We will take the weights of that model and put them in our model. You can download these weights from GMFlow repository. We just need to go to this place here, to click on Google Drive here to download it, and you will get many different pre-trained weights files. As you can see here, we will just select one of them. We will use this one, GMFlow Centel, to find optical flow. We will put it in our Google Drive. Now we have this GMFlow Centel in our Google Drive. We will copy the path of this file, and we will put it here. So what we will do here, actually, we will import torch library, and we will use torch.load, and we will put the path of this file, and we will get this checkpoint. You will see many different things inside this dictionary. We will take just the weights from it. How can we take the weights from this dictionary? We just need to type checkpoint, and we should open these square brackets, and we should type model, and that's it. These are the weights that we will put in our GMFlow model. Now let's put them in our GMFlow model. To do that, we just need to type the name of the model, GMFlow model dot load state dect, and here you should pass the weights, and that's it. Now we can use this GMFlow model to find the optical flow. And because that we don't need to train this model, we just need to use it. So we will type GMFlow underscore model dot evaluation, like this. In my Google Drive, I have many images. I will take two of them. Okay, the first image, which is this one, and another image, for example, this image. Okay, let's take them. We will import CV2 package. We will type import CV2, and here CV2.image read, and we will put the path of the first image like this, and let's call it image 1, and we will take the second image, or image 2. Let's take the path of this image, for example this one here. So now we have the first image and the second image. Now we will change the order of the color channels from BGR to RGB, which is something important actually, because they trained our GMFlow model previously on RGB images, not BGR images. We will do this for the first image and for the second image. And as you can see here, here is our image, our first image, and our second image, this one. That's good. Now these two images, they are NumPy arrays, and we want to pass them through our model, PyTorch model, so we should convert them into tensors. So let's convert the first one, image 1 equal to torch dot from NumPy, and we should open these parentheses, and we should pass our image 1 here, and we should change the order of the dimensions. Let's see the original dimensions in our image 1. So we will type image1.shape. Here is the first dimension, the second dimension, and the third dimension. The first dimension, it is the height dimension. The second dimension, it is the width dimension, and the last dimension, it is the color dimension. what we will do here, we will take this dimension and put it in the first. So we will make this dimension the first dimension, and this one the second dimension, and this one the last dimension. Let's do it. We will use permute method, and we should open these parentheses, and here we should put the index of this dimension, which is 2. The index of this one is 0, the index of this one is 1, and the index of this one is 2. So we should put 2 firstly, and we should put 0, and we should put 1 here. And we should convert the type of this tensor to float, and we will send it to our GPU. Okay, we will do the same thing for the second image. Now we prepared the input to our GMFlow model. Now what we will do, we will import input pattern class from GMFlow folder, and we will use it to pad these 2 frames so that the dimensions of each one of these frames are divisible by 8, which is something required by our GMFlow model. So let's import this input pattern. We will type from GMFlow folder dot utils folder import everything. Okay, let's run this cell. Actually, this input pattern is available in utils script inside utils folder, which is inside GMFlow folder. So we will type from GMFlow folder dot utils folder dot utils file import everything, and now we can use this class. Let's create an object for this class. We will call it pattern object, which is equal to input pattern class, and here we should pass the shape of any one of these images. Let's take, for example, the first image. So we will type image1 dot shape, and here we will make padding factor equal to 8. Now we can use this pattern object. Now what we will do, we will use this pattern object dot pad method, and here we will pass the first frame, and we will pass firstly the first frame, and we will add another dimension to this frame, which is the batch dimension. We just need to open these 2 square brackets, and we should put none between them like this. By doing this, you will add new dimension at the first, and the length of this new dimension equal to 1. It means a batch with 1 sample. And the same thing with image 2. And this function will return image 1 and image 2 after padding. And now we will use our GMFlow model to extract the optical flow. Firstly, we will type with torch.noGradient to avoid computing gradients during doing inference or during using our GMFlow, because as you know, we don't need to train our GMFlow model. They trained it previously. And here we will type optical flow dictionary equal to GMFlow model, and here firstly we should pass the next frame, and after that we should pass the first frame or the current frame, image 1, and here we will make a tension splits list equal to this list here with just 1 element, which is equal to 2, and we will make correction radius list equal to this list here with just 1 element, which is equal to -1, and we will make this parameter probe radius list parameter equal to this list here, which has just 1 element, which is equal to -1, and we will make prediction by direction flow equal to true, which means that we will use our GMFlow to extract forward optical flow and backward optical flow. Now let's see what is inside this optical flow dictionary. Let's put it here and let's run this cell. And as you can see here, here's our optical flow dictionary. Inside this dictionary, we have our optical flow. Let's extract it from this dictionary. Let's open these two square brackets and type flow predictions, and we will get this list. Okay. And now we will extract our optical flow from this list. We will just need to open these square brackets and put 0 here. And that's it. Now we have our optical flow. Actually, our forward optical flow and backward optical flow. We will learn how to extract each one of them from this tensor. Firstly, let's extract forward optical flow. To do that, we just need to type optical flow prediction, and here we will open these square brackets and put 0 between them, which means the first element in this optical flow prediction tensor, which represents our forward optical flow. And as you remember, we added paddings to our images before passing them through our GM flow model. So these paddings will also appear in our forward optical flow and backward optical flow. So what we will do, actually, we will remove them. We will use our padder to do that. So we will type padder.mpad, and here we will pass our forward optical flow. And here we will also again add the batch dimension to this forward optical flow by opening these square brackets and putting none between them. And here is the new dimension: 1 times 2 times h times w. This optical flow represents the movement from the current frame or the first frame to the next frame. And as you can see here, the width and height of this optical flow, it is equal to the width and height of our original images, which means that we have a vector with two things, x and y, for each pixel. This vector will represent the amount of movement of that pixel and the direction of movement when we moved from the previous frame to the next frame. In other words, when we add this vector, this x and y, to our original location of that pixel in our previous image, in our previous frame, we will move this pixel to its new location in the next frame. And now we will extract backward optical flow. This optical flow will represent the movement from the next frame to the current frame or the previous frame. So backward flow equal to padder.npad, and here we will type optical flow prediction, and here we will pass the index of this flow, this backward flow, which is the second element in our optical flow prediction tensor. And here we will add batch dimension to this backward flow. And here is the shape of this backward flow. The first dimension, it is the batch dimension. The second dimension represents xy dimension. And here we have the height and the width. And now we will take the shape of this forward optical flow, and we will get the batch size, the number of channels, the height and the width of this optical flow. Let's run this. And as you know, the size of this optical flow, it is similar to the size of this optical flow. And now we will create a grid of locations. We will use torch.meshGrid, and we will pass torch.arrange h to it, which represents all y locations of our pixels from 0 to 463, and the same thing here, torch dot arrange W, and this one will represent all X location in our image from 0 to 811, and we will get two things, Y and X. Let's display this one here. This Y tensor will have a Y value for each pixel in our image. For example, here Y equal to 0 for this pixel, this pixel, this pixel to this pixel. And the same thing here, Y equal to 1 for this pixel, and this pixel to this. So this tensor will have a Y value for each location in our image. Now let's display X tensor. X location for this pixel equal to 0, X location for this 1 equal to 1, X location to this pixel equal to 2, etc. So now we have Y location and X location for each pixel in our original image. And these locations, actually, they are the original locations of our pixels. Or in other words, the locations of our previous frame. So now what we will do, we will change these locations based on our forward optical flow to get the new locations of our pixels after moving from the previous frame to the next frame. Now what we'll do, we will stack this tensor, X tensor, which represents X location for each pixel, with this tensor, Y tensor, which represents Y location for each pixel, the original Y location for each pixel, or the Y location for each pixel for the previous frame. Here we will create a new dimension and we will stack them along that dimension. Let's firstly see what is the shape of X tensor, and here's the shape of this tensor. It is similar to the width and height of our original image, and the same thing for this Y tensor, as you can see here. So now what we will do, when we use this torch.stack method, we will create a new dimension. We will put it in the first, okay, and stack these two tensors on that dimension. Let's see the results. And here's the result. We created a new dimension and we put it X and Y tensors along that dimension. And now what we'll do, we will add another dimension with length 1 by opening these two square brackets and putting none between them. And here's the result. This dimension will represent the X dimension. We will convert the type of this tensor to floats rather than integer and send it to our GPU, and we will add our forward optical flow, or in other words, the amount of movement and the direction of movement that each pixel in our previous frame need to move to the next frame. And we will add all these vectors to our original locations to get the new locations of our pixels. And here is the result. As you can see, we will put the result in this variable wrapped grid using forward optical flow. Now we will do normalization for these new locations in our wrapped grid using FWD. Firstly, we will take the new X locations from our wrapped grid using FWD, and we will divide these locations, X locations. We will divide each one of these X locations by the width of this wrapped grid using FWD tensor minus 1. This thing will make the highest value in this X new tensor equal to 1 and the lowest value equal to 0. And we will multiply the resulted tensor with 2, which means that we will make the highest value in the new tensor equal to 2. And we will subtract 1 from the final tensor, which means that we will make the range of values of the resulted tensor between 1 and minus 1. So now we have this normalized wrapped X grid FWD and normalized Y grid FWD. We did this normalization process because it is important to use these locations to change the locations of the values of our pixels based on these new locations. Now what we will do, we will stack these two tensors, normalized wrapped X grid FWD and normalized wrapped Y grid FWD, and we will put this new dimension in the last. Here you should know that the size of this normalized wrapped X grid FWD equal to the batch size times the height times the width. Okay, now what we will do, we will add a new dimension at the last, and we will stack these two tensors along that dimension. And here is the final shape: batch size times height times width times 2, which will contain the first and the second tensors. Now we have normalized wrapped grid FWD. Now we will do something called forward-backward consistency check. We will do this process to find the occluded pixels, the pixels that were hidden in the previous frame and they showed up in the next frame. These pixels will have inconsistent optical flow. So we will do forward-backward consistency check to find these pixels. Actually, here we will use the forward optical flow and the backward optical flow to find these inconsistent regions, the occluded pixels. Let's learn how to do that. Firstly, we will import torch.nn.functional as f capital. And here we will wrap our BWD flow based on our normalized wrapped grid FWD. Think about it like this. Let's say that we have two frames. Here is our previous frame and our next frame. Okay? And here we just rotated our head like this in the next frame. Now let's draw our backward optical flow. Okay, it will be in this direction, or something like that. Okay, each pixel inside this head will have its own vector. Okay, when we add these vectors to this grid of the original locations, we will get a new grid of locations for the head. Let's say that this is our new grid of locations. Now what we will do, we will wrap our image, especially this region here, based on these new locations to move all these information inside these locations, all these pixels to this region. Okay, that's what we mean by wrapping. What we are trying to do in this consistency check, we are trying to use forward optical flow tensor. This tensor will have many vectors, one vector for each pixel, okay, in our image. But here we are trying to focus on the movement parts in our image, so we will draw just these few vectors. Each one of these vectors represents how much this pixel needs to move and in which direction to reach to its new location in our next frame. Now what we will do, we will add these vectors to our original grid of coordinates, XY grid. Here let's take just these vectors, we will add them to our original locations to get new locations. Okay, and what we will do actually, we will use these new locations and we will move these vectors of our backward optical flow tensor based on these locations. We will change the locations of these vectors based on these locations here. So we will get something like this. As you can see here, we will get something like this. Okay, these vectors now, they are here. We wrapped these vectors based on these new locations that we got from our forward optical flow. And finally, our vectors from our backward optical flow, they are available in the same region of our of the vectors of our forward optical flow, so we can add them together. Okay, and because the direction of these vectors of forward optical flow and backward optical flow, they are in opposite directions, so in other words, we are trying to subtract them to find the difference between backward optical flow and forward optical flow. And now what we'll do here, we will also again stack x and y along this new dimension 0, and we will add another dimension which is the patch dimension, and we'll convert this tensor into float and we will send it to our coda. It is something similar to what we did previously actually. And this tensor will represent the locations of our next frame. We will add to it BWD flow, our backward optical flow tensor, to change these locations to the locations of our previous frame. And we will get wrapped grid using BWD. And we will do also normalization to get normalized wrapped X grid BWD and normalized wrapped Y grid BWD. And we will stack these two tensors along this new dimension, and here is the final shape, the batch size times the height times the width times 2. And here what we will do actually, we will wrap this FWD flow or in other words, change the location of the vectors inside this FWD flow and move them to these locations inside our normalized wrapped grid BWD. By doing this, we will change the locations of the vectors inside FWD flow and move them to the previous frame. And by doing this, we will be able to find the difference between the wrapped FWD and BWD. In ideal case, the difference should be 0, but as you know, we have occluded pixels. These occluded pixels will create differences, and we will use these differences to create a mask. Now we will get wrapped FWD flow with BWD by passing our FWD flow and normalized wrapped grid BWD. And now we have two things: wrapped BWD flow with FWD and wrapped FWD flow with BWD. Now let's find the difference between them. We just need to add our wrapped BWD flow with FWD. By doing this, you will see the difference. And the same thing with difference BWD tensor. We will add wrapped FWD flow with BWD to our BWD flow to find the difference, to find the occluded regions, and we will find the magnitude of these differences. We don't need direction here, we just need magnitude. Each occluded region will have larger magnitude. To find these magnitudes, we just need to use torch.norm function. And now what we'll do, actually, we will compute the length of each vector in our FWD flow, okay, using torch.norm, and we will add these lengths to the length of each vector, and we will get flow image, and we will multiply this flow image with 0.01 plus 0.5. Here we created this threshold that we will use to create the mask. And now we will create the mask. Let's call it FWD occlusion, which is equal to, we will take difference FWD if the length of any difference vector inside this difference FWD, it is greater than threshold, our threshold. In this case, we will make it equal to 1 or true. Otherwise, we will make it equal to 0. We can also call it mask tensor. And here what we will do, we will send this tensor to our CPU and change the place of our dimensions. And we will make the type of this tensor equal to long. Okay. And we will convert it into NumPy, and we will multiply each element inside this tensor by 255. Okay, and here's the final result. Here is the mask. Okay, we will use this mask a lot when we are trying to do video-to-video animation with a stable diffusion model. We will use it to fix the background and to keep the same face during the animation. We will learn how to do that later. Now let's say that we want to wrap our image 1 to image 2 using our FWD flow, forward flow. How can we do that? To do that, we just need to find the shape of our image 1, and we will get the batch size, the number of channels, the height and the width of our first image. And what we will do here, we will create our grid, okay, and we will do same as what we did previously. We will get this wrapped grid using FWD, and here we will find our normalized wrapped grid FWD. And to wrap our image 1 to image 2, it's easy. We just need to type wrapped image 1 with FWD, and here we will use a grid sample, and we will pass our image 1, our previous image, our previous frame, and we should pass our normalized wrapped grid FWD to get the result. Now what we will do, we will display our wrapped image 1 with FWD. Okay, here we have the batch dimension. We will take the first sample in this batch. As you know, we have just one sample, which is our image, our wrapped image, and we will change the location of our dimensions to be able to display them. And we will send our image to CPU, and we will convert it into NumPy array, and that's it. And here is the result. It is not perfect actually, and this region here, it is the occluded region. Let's mask this region with our mask that we created previously. Okay, firstly let's divide this mask by 255 to make the highest possible value here, the result equal to 1, and the lowest possible value in our mask equal to 0, and we will convert the type of this tensor to unsigned integer 8, and now we will subtract the resulted tensor from 1, and let's display our final image, and that's our final image. That's great, and we masked the occluded area. Okay, that's great. These things: forward optical flow, backward optical flow, and occlusion mask to build shape-aware system in our video-to-video machine. Thanks for watching. Hi, in this lecture we will convert our video into frames using FFmpeg package, and we will put these frames in our Google Drive and connect our Google Drive with our Colab notebook. So now we have our frames in our Colab notebook, and from these frames we will take just a few frames and we will call them keyframes. Okay, here is the first keyframe, the second keyframe, and the last keyframe. And here what we will do, we will pass these keyframes through our encoder, and we will get the latent at time step 0 for the first keyframe, and the latent at time step 0 for the second keyframe, etc. Okay, we will add a noise to each one of these latents to get the latent at time step T capital for the first keyframe, and the latent at time step T capital for the second keyframe, etc. And we will also pass these keyframes through our Kenny function to create our conditions, and we will get the following. We will get this condition for the first keyframe, and this condition for the second keyframe, etc. Now let's do that. Firstly, we should install FFmpeg from the official page and based on your operating system. Here I have Windows, so I will select this option and we will download this one. And here we will click on FFmpeg get full.7z. Now we downloaded our FFmpeg. You will find it in downloads. Okay. To open this folder, this compressed folder, you should download WinRAR Archiver program. It is free. Now we will go inside this folder. Okay. We will click on this one. We will open this one and we will open this folder, bin folder. We will extract these three files. So we will click on extract to. We will go to downloads and create a new folder. Let's call it FMPEG folder. Okay, and click on OK. And that's it. Now we have this folder which has these three files. Now let's take this folder, okay, and put it in C drive in this place here. I put this folder here to make sure that I will not remove it in the future. Actually, our Windows doesn't know our file is here. Let's go inside this folder and copy the path. Okay, and let's click on search and let's type path here. And now we should click on this, edit the system environment variables. Now we should click on environment variables. Okay, and we should click on path. We should click on new. And here we should paste our path, which is this one here, and click on OK. Now our Windows is able to detect this package and use it. Let's click on OK. That's it. Now we will open CMD window and we will type ffmpeg like this, and here is the result. Now our Windows is able to use FFmpeg package. We will use this package to convert our video into frames. In our C drive, we will create another folder here. We will click on new folder and we will call it frames like this. And we have this video that we want to convert into frames in our C drive. As you can see here, we want to convert this video into animation using artificial intelligence. Now what we will do, now we will copy the path of this video. We will click on copy as path. Now what we will do, we will type fmpeg-i, and here we should put the path of our video. Okay, we'll click on copy as path and we will delete this and put our path here like this. Okay, and here we should put the path of our folder that we want to put our frames inside it, which is a frames folder. We will copy the path of this folder. Click here. We should delete this part here and put it like this and change this one. And here we will give each frame a number as a name. For example, for frame 1 we will give it number 1, frame 2 we will give it number 2, frame 3 we will give it number 3, etc. Now we will click enter, and as you can see here we have our frames. Inside frames folder, here's the first frame, the second frame, the third frame, the fourth frame, etc. We have around 466 frames. We will put these frames in our Google Drive. Now we just need to drag and drop it in our Google Drive like this. Now let's connect our Google Drive with our Colab notebook. Now we will click here and we will click on this symbol here to connect our Google Drive with our notebook, and we should click on connect to Google Drive, and that's it. Now you will see this folder, Drive folder. Click on it and click on My Drive, and you will see our folder, Frames folder, which has all the images, all the frames. Okay, let's click on one of them, and here is the first frame and the second frame. That's good. Now we will install diffusers package, transformers package, spacey package, FTFY package, and accelerate package. So here firstly we will type exclamation mark pip install diffusers, transformers, spacey, FTFY, accelerate. And we will also install OpenCV contribution Python. So we will type exclamation mark pip install OpenCV contribution Python -QQ, and we will do the same thing here. We will install controlnet AUX. So we will type exclamation mark pip install controlnet AUX -QQ. Let's click on run, and that's it. Here we will import Stable Diffusion ControlNet pipeline and ControlNet model from diffusers package, and we will import PyTorch library and OpenCV library, and we will click on run. Now we will create this variable, device variable, which is equal to torch.device, and here we will type the following: coda if torch.coda is available, else CPU. And here what we will do, we will specify the device that we are using right now. Here we are using our GPU. Okay, so here this variable will be equal to coda, otherwise this variable will be equal to CPU. Let's see what is inside this variable, and as we can see here it is coda. And here we will download our controlnet. How can we do that? We will type controlnet variable, it is equal to controlnet model class, okay, dot from pre-trained, and here we will put the checkpoint of this controlnet. Okay, here we will use Canny controlnet or SD controlnet Canny. As you can see here, this controlnet, it is available in Hugging Face community. We just need to copy the path of this controlnet and put it here, comma, and here we will make torch dtype parameter equal to torch.float16 to reduce the size of this model by reducing the precision of each weight inside this Canny controlnet to float16. Now what we will do, we will create our pipeline that we will use to generate the images. So we will type pipeline variable equal to stable diffusion control net pipeline class dot from pre-trained, and here we will put the path of the stable diffusion model that we want to use. For example, we will use Dreamlike stable diffusion model version 1, and it's up to you to choose any stable diffusion model. And here we will make this control net argument equal to our control net, our Kenny control net, and we will make torch dtype argument equal to torch.float16 to reduce the size of our models, and we will send all these models, or in other words our pipeline, to our GPU. So we need just to type dot to device. Okay, that's it. Now we will click on run. Now what we need to do, actually, we need to create our condition. Okay, firstly we should import load image from diffusers.utils, and we should import image from pil package. Okay, let's run this cell again, and let's create our condition, our Kenny input. Let's take, for example, one of these frames. Let's take the first one. Let's copy the path of this frame and put it here. And now we will type image equal to load image, and here we will pass the path of our image. Now we need also to import NumPy array to convert our image to NumPy image. So we will type image equal to np.array, and here we will pass our image like this, and here we will see what is inside our image variable now, and here is the result. It is just NumPy array. Okay, let's see the shape of this array. We have 3 dimensions: the height dimension, the width dimension, and the channel dimension. Okay, now let's convert this image into Kenny input. How can we do that? We will use OpenCV, a library, to do that. We will use Kenny function inside our OpenCV library. So we will type image equal to cv2.kenny, and here we will pass our NumPy array, our image, comma. Here we have 2 arguments, low threshold argument and high threshold argument. By adjusting the values of these 2 parameters, you will be able to control the amount of details that you want to see in your Kenny input. So let's make low threshold variable equal to, for example, 100, and high threshold variable equal to 200. And now let's run this cell. Let's call this one Kenny input. Now we want to display this Kenny input. Firstly, let's see the shape of this Kenny input. So we will type Kenny input.shape like this, and here we have 2 dimensions, the height dimension and the width dimension. We need to add another dimension, which is the channel dimension, to be able to display this image, this Kenny input. How can we do that? As you can see here, we will add another dimension at the end by doing the following: Kenny input equal to Kenny inputs colon colon, and here we will put none. So here we will add another dimension, the channel dimension, with length 1. let's see the shape of this Kenny input. And yes, we have 3 dimensions. The last dimension, the length of the last dimension equal to 1. Let's make it equal to 3 because we have 3 channels, green, blue, and red. To do that, firstly, you should type Kenny input equal to mp.repeat, and we will open these parentheses and pass our Kenny input. And we will specify how many times you want to repeat the channel dimension. We want to repeat it 3 times, and we should specify the dimension that we want to repeat it, which is the channel dimensions. The index of the first dimension is 0, the index of the second dimension is 1, the index of the third dimension is 2. So we will put 2 here. Now let's see the shape of our Kenny input. The length of our channel dimension equal to 3. Now we will use image class to display our image. So we will type Kenny input equal to image.from array, and here we will pass our Kenny input, and here we will display our Kenny input. Okay, and here's the result. Here is our Kenny input. Now let's pass our Kenny input through our pipeline to create our image. And now we will create our prompt, which is masterpiece man CG style. And here we will pass this prompt through our pipeline, and we will pass our Kenny input, this image here, okay, through our pipeline also. And if you want, you can pass negative prompt, and we specify the number of inference steps to 20 steps, which means that we need just to move 20 steps to create an image, to create one image. And here we made the guidance scale equal to 5 and control net condition scale equal to 0.7. Let's run this cell. And here is the result, as you can see here. Now we will put all these things inside a function. Let's call this function create Kenny input function, and this one will take just one argument. Okay, now let's click on tab, and here is the result. We will type return, and this one will return our Kenny input. Okay, now if you want, you can add more parameters to this function. For example, low threshold parameter. Let's make it by default equal to 50, and another parameter which is high threshold parameter, and let's make it by default equal to 70. Let's remove these things here, and if you want, you can change their values. Now let's call this function. Firstly, let's run the cell, and let's call this function. Let's pass our image, and we will get what? We will get our Kenny input. Okay, that's it. Now we can convert any image to Kenny input by just calling this function, and here's the result. Now what we will do, we will go inside this pipeline and change many things inside it. We will not use it directly actually here. So firstly, we will extract all what we need from this pipeline. Firstly, we will extract the scheduler from this pipeline. So scheduler equal to pipeline.scheduler, and we will extract our stable diffusion model, our U network from this pipeline. So U network equal to pipe.unet, and here we will extract the encoder from this pipeline. So firstly we will call it E, which means encoder. It is equal to pipe.variationalAutoencoder.encode, and here we will extract the decoder from this pipeline. So D equal to pipe.variationalAutoencoder.decoder, and here it's important to know the variational autoencoder scaling factor. It's important for our encoder and decoder, and we will see that later. So now we will extract this variational scaling factor, which is equal to pipe.variationalAutoencoder.configuration.scaling factor. And here we will extract the tokenizer from our pipeline. So here we will type clip tokenizer equal to pipe.tokenizer. It is important to tokenize our prompt, our text, and convert it into something that we can pass it through our U network. And here we will extract the transformer model, clip transformer, from our pipeline. So we will type clip transformer equal to pipe.textEncoder. Actually here we will pass the output from our clip tokenizer to our text encoder, and the output from our text encoder we will pass it through our U network using cross-attention blocks inside our U network. In other words, we will do injection. We will inject this text, inject the output from our clip transformer using these cross-attention blocks. And here we will extract our control net from our pipeline. Control net equal to pipe.controlNet. Now let's run this cell. Actually, all these things, they are available in our GPU because our pipeline it is available in our GPU. So here controlnet.device, and the result equal to CODA. So our control net here, it is available in our GPU and our clip transformer, our clip tokenizer, and our decoder, encoder, U network, and our scheduler. Now let's create our positive and negative prompt. Here is our positive prompt, which is digital painting, man, blue sky, cyborg city, Stanley, art germ, law, fantasy artwork. And here is our negative prompt: ugly, tiling, poorly drawn hands, deformed, body out of frame, blurry, bad anatomy, blurred watermark. Okay. Now we will pass these two prompts through our tokenizer. We will use our clip tokenizer firstly. So positive prompt input, it is equal to clip tokenizer, and here we will pass our positive input. Okay, and here we will make padding equal to max length and maximum length equal to clip tokenizer dot model maximum length. So now these padding and max length arguments will specify the number of tokens that we will pass through our clip transformer. And here the clip tokenizer dot model maximum length, it is equal to 77, which means that we want to pass 77 tokens through our clip transformer. As you can see here, our prompt the number of tokens in our prompt or the number of words in our prompt, they are less than 77. In this case, it will add many padding tokens to make the length of this text or the number of tokens inside this text equal to 77. Okay, and truncation equal to true, which means that if the number of tokens inside our prompt they are greater than 77, in this case it will take the first 77 tokens and it will remove the rest. And here we want to get a PyTorch tensor from this model, so we will make return tensors equal to pt. And the same thing here. Let's run the cell. Let's see what is inside positive prompt input. As you can see here, it is a dictionary. This dictionary has two things: input IDs and attention mask. Now let's see the shape of this input IDs, the tensor of this key, input IDs key. So let's open these square brackets and put input IDs between them. And now let's display the shape of this tensor. As you can see here, we have just one prompt. So the first dimension equal to 1. And here the length of this tensor, the number of elements inside this tensor equal to 77, which is equal to the model max length. It is also equal to 77. That's right. And the same thing with our negative prompt input. As you can see here, here is the shape of negative prompt input IDs. Now we will pass these input IDs through our clip transformer. And here you should know that we should send this tensor, this input IDs tensor, inside positive prompt input and negative prompt input to our GPU before passing it through our transformer model. So we will do the following. Firstly, we don't need to compute gradients because here we are trying to do inference. We just need to use our clip transformer. We don't want to train it. So we will type with torch.noGradient, and here let's find the positive condition cp underscore positive, which means clip positive. It is equal to clip transformer, and here we will pass our positive prompt input dot input IDs. So now we have our tensor. This tensor we will send it to our CODA, our GPU, and we will pass our tensor through our clip transformer, and we will take the first element in the result. We will open these square brackets and we will put 0 between them. So now we have our clip positive. And now we will do the same thing to get clip negative. Clip negative equal to clip transformer, and here we will type negative prompt input dot input IDs, and we will send this tensor to our GPU. After that we will pass it through our clip transformer, and we will take the first element in the result. And actually there is just one element here, so we will take it and we will put it in clip negative. Now we will combine these two things together in just one tensor. How can we do that? Clip condition, it is equal to torch dot concatenation cat, and here we will open these square brackets and we will put cp negative here, and we will put cp positive here in this case. Now let's see the shape of the result, and here's the shape. The first dimension equal to 2 because this dimension has two things, cp negative and cp positive, and each tensor here has this shape 77, 768. Now we prepared our text condition. And we can put all these things in just one function like this. Define prepare prompts function, and this function will take two things, positive prompt and negative prompt, and it will do the following. Firstly, it will pass them through our tokenizer, okay, and it will use our transformer model to convert them into something that we can pass it through our U network. And finally, we will return CP like this. Now, let's use it. We will pass our positive and negative prompt. Let's see the result. And here is the result. It is our text condition that we will pass it through our U network. Okay, that's it. Now we will learn how to create latents to our stable diffusion model. We will read one image, one frame from our frames. Let's, for example, read the first frame. Okay, and we should also import torchvision.transformers as TFS. Let's run this cell again. And now we will prepare our image to pass it through our encoder to convert it into latent representation. So we will type image equal to TFS dot to tensor, and here we should pass our image, and we will add another dimension to the resulted image. So here what we will get, actually we will get a tensor with this shape. The first dimension represents the channel dimension, the second dimension represents the height dimension, and the last dimension represents the width dimension. But we need to add another dimension, which is the batch dimension. How can we do that? We will use nsqueeze method. So we will type .nsqueeze, and here we will specify the location of the new dimension. We want to make the index of the new dimension equal to 0. So we will put it in the first with length 1, and we will send the final tensor to our GPU. And the type of this tensor equal to torch.plot16, because as you know, all our models, the weights of our models are torch plot16. So if we want to pass any tensor to our models, it should be in the same type. As you can see here, the highest value inside our tensor now, it is 1, because we used to tensor. This to tensor will make the highest possible value in our tensor equal to 1, and the lowest possible value in our tensor equal to 0. But why? As you know, any image, the values inside any image should be between 0 and 255. But after using this to tensor method, this to tensor method will make the highest value equal to 1 and the lowest value equal to 0 in the resulted tensor. Okay, but actually our encoder expects that the range of the values should be between -1 and 1. So we should convert this range to -1 to 1. How can we do that? We just need to type image equal to image times 2 minus 1. And that's it. Now let's check the new range. And as you can see here, the highest value equal to 1 and the lowest value equal to -1. As you know, we don't want to compute the gradients because we don't want to train our encoder. So we will type with torch.noGradient, okay? And here we will pass our image, our normalized tensor, our normalized image through our encoder, and we will get x0, or in other words, the latent representation at time step 0. And we will type .latent distribution .sample, and now we have our latent representation at time step 0, and we will multiply it with variational autoencoder scaling factor. It is important for our stable diffusion model. For this reason, we multiply this representation, the output from the encoder, by this variational scaling factor. And now we have our latent representation of our image. Now, if we want to get xt capital, the latent representation at time step t capital, we just need to create a noise here. Noise equal to torch.random. And here we will pass the shape of our latent, and we will pass the resulted tensor to our GPU. And here we will take the first time step in our scheduler. As you know, we are trying to do reverse diffusion. The first time step here, it is t capital. Okay, so t capital equal to scheduler.timesteps, and here we will put 0. And now we have our t capital. Now what we will do, we will get xt capital, which is equal to scheduler.add noise, and here we will pass our latent at time step 0, and we will pass the noise, and we will pass the time step t capital. So now we move this x0 to xt capital. Let's see the result. And here's the result. As you can see here, the first dimension represents the patch dimension, the second dimension represents the channel dimension, the third dimension represents the height, and the fourth dimension represents the width. Now let's put all these things inside a function. We will call it create latence function, and this function will take our image, okay, and it will do all these things on our image. Okay, and finally it will return xt capital. Let's try to use it. And yes, it works. We will type xt capital equal to create latence, and here we passed our image, and that's it. In the next lecture, we will learn how to extract an xt capital for each frame and a canny input for each frame. Thanks for watching. Hi. In the previous lecture, we learned how to convert our video into frames and how to put them in our Google Drive and how to connect our Google Drive with our Colab notebook. Now, what we will do, we will take keyframes from our frames. So here we will not use all these frames, but we will use few of them. For example, let's say that we have 200 frames and we want to use just 100 frames. To do that, we need to skip just one frame each time. So in this case, we will take the first frame, we will jump the second frame, and we will take the third frame and we will jump the fourth frame, and we will take the fifth frame and we will jump the sixth frame, etc. Now let's say that we want just 50 keyframes. So we will divide the total number of frames, which is 200, by 50, and the result will be equal to 4. And here we should decrease the result by 1, so we will get 3, which means that we should jump 3 frames each time. So here we will take the first frame, we will jump the second frame, and the third frame, and the fourth frame, and we will take the fifth frame, etc. Let's do it. Now we will create the keyframes. Firstly, we should import globe package. Okay. I put this package in this place here. Okay, let's run this. And now let's delete this one. Now we will create function. This function we will call it create keyframes function, and this one will take just one argument, which is the directory of our frames, and we just need to copy the path of this folder, frames folder. So the directory actually in this case is this one. And now what we will do inside this function, we will take the path of each frame inside this folder, inside this frames folder. We will use globe package to do that. So we will type frames paths variable equal to globe.globe, and here what we will do actually, we will add our directory, this directory, okay, to this part here by putting **.png. Our globe package will understand that I want the path of all these frames, okay, the path of this one, this one, this one, etc. And our globe package will also understand that I want just the files with PNG extension. So if there is any other file with another extension, we will not take it. We will not extract its path. So now we have the path that related with each frame. Now let's display what is inside this frames paths. Let's type print, and we should put this here. And yes, now let's call this function with our directory. And as you can see here, each element inside this list represents a path for a specific frame in our frames folder. Okay, that's good. Now let's delete this. Now let's compute the number of frames in our frames folder. It's easy. Num frames equal to the length of this list, frames paths list, because the number of paths inside this list will represent the number of frames in our frames folder. Okay, let's print the result, and let's call this function again. And as you can see here, we have 466 frames in our frames folder. Now let's say that I want just 70 keyframes. So here we will create this variable, number of keyframes variable, which is equal to 70 in this case. And we will create this parameter, number of keyframes parameter, which is by default equal to 70. You can change it if you want when you call this create keyframes function, but it is by default equal to 70. And now we should specify how many frames we should skip each time. So we will type print. To find this number, we just need to divide the number of frames that we have by the number of keyframes. And to avoid getting fractional number, we will put this symbol here. And now let's run this and call this function. And here's the result, 6, which means that we should jump 5 frames at each time. Now we created this loop for current keyframe in range from 1 to the number of keyframes. And here we should specify the number of frames that we should skip at each time. So we will pass the number of frames divided by the number of keyframes. And here, this function, this range function, will reduce the result by 1 automatically. So if the result equal to 6, so it will reduce it by 1, so it will skip 5 frames at each time. Here, the first parameter in our range function will specify the number that we will start with, which is in this case equal to 1. And the second parameter, which is equal to number of frames plus 1, will specify the last number in our loop. Actually here, this function, this range function, will end with the number of frames, not the number of frames plus 1. Now, we will extract the number of each frame from its path. As you know, in this frame's paths list, we have the path that related with each frame in our frames folder. So how can we do that? Here we created this variable frames names. The name of this frame 0001 and the name of this frame is 0002, as you can see here. So here we will create this loop inside this list. Here what we will do, we will pass it through each path inside this frames paths list, and we will do the following to that path. We will split each part of that path based on this slash character. Let's take an example. Let's, for example, copy this path. And now we have this path, and we use this split method, and we put it slash here. By doing this, we will create this list. Firstly, we will divide our path based on this slash character. So here we have content, here we have drive, here we have my drive, here we have frames, and finally we have the name of our image or our frame, which is 0001.png. But we don't want to see this png. What we will do here, actually, we will take the last element in this list, which means this one here. Now we will take the first 4 digits. Actually here, the index of this dot is -4, and the index of this character, the first character that we want, is 0. So what we want, actually, we want to take this character, this character, this character, and this character, and we don't want to take all these characters. So we just need to put the index of the first character that we want and the index of this character here, -4. By doing this, you will take just these 4 characters and you will not take the rest. Let's display what is inside this frames names list. We just need to type print, and we just need to put this frames names inside it, and let's call our function, and here's the result. Actually here, after taking this number, we will convert it from string to integer. So you will see them like this as integer numbers. You will not see zeros in the left. Okay, now let's complete our loop. Now we have the name of each frame in our frames folder. Now we have our current keyframe. We want to reach the path of the current keyframe. So we will type current keyframe name. Okay, and here we will use our frames names list. We will search about this current keyframe inside our frames names, and we will extract the index of the path of this current keyframe. We will use this index to extract the path of this current keyframe. Let's say that our frames names list has just three values, three elements: 5, which means frame 5, 4, which means frame 4, 3, which means frame 3. Okay, and let's say that we are at the first iteration in this loop, which means that current keyframe equal to 1. Let's put 1 here also. Okay, now what we want, actually, we want to search about the index of this keyframe inside our frames names. And as you know, we have frames paths list. This list will have the path for each frame in our frames names list. And for example, frame 5, the index of frame 5, it is 0, and you will see also the path of this frame 5, and the same index in a frames paths list, which is index 0. And frame 1 in our frames names, the index of it equal to 2, and you will see the path of this frame 1 in a frames paths list in the same index, which is index 2. So we extracted the current keyframe index to find the path of this current keyframe in our frames paths. So now we will type frames names dot index, and here we will pass current keyframe, which is 1, which means that we want to get the index of element 1 inside our frames names. The index of this is 0, the index of this is 1, the index of this equal to 2, so the result equal to 2. Now I want to get the path of this frame, of this keyframe from frames paths. So I will do, we will put frames paths, and here I will put the index of our current keyframe, the index that we got from here, and we will put it here. And as you can see here, now I have the path of this keyframe. That's what we will do here. Now we have the current keyframe index. Now we will extract the path of this keyframe. Now we have the path of our current keyframe. And here you can add another parameters like the height and the width. Here we will make the height and the width similar to the height and the width of any frame in our frames folder, but you can change them as you want. Actually, all these frames, they have the same shape. Now what we will do, let's take the height of this frame or this image. Here we should put 1, and the width of this image, here we should put 2, and here we should put height comma width, and I will make them by default equal to the height and the width of our original frames. Here, if you want to change the size of your frames, you can use tfs.resize method, or you can use resize method from OpenCV library. Now we will compute a Kenny input for each keyframe, and we will compute an XT capital for each keyframe. Let's start with the Kenny inputs. Previously we created this function, create Kenny input function. Let's copy the name of this function. Now we will use it to convert our keyframe into Kenny input. And here I will make the low threshold equal to 70 and the high threshold equal to 100. I think I made a mistake here. We should use a resize method from CV2. Yes, the problem also here. The first dimension, the index of the first dimension is 0 and the index of the second dimension is 1. And yes, there is no problem. What we did here, we took the length of the first dimension in our image. The index of this dimension is 0, which represents the height of the image, and we took also the index of the second dimension, or the length of the width dimension. So now we have the width and height. Now we will resize our image. So we will type image equal to cv2.resize, and here what we will do, we will load our current keyframe and we will convert it into NumPy array, and we will specify the new size by putting dsize equal to, here firstly we should put the width, and after that we should put the height, and now we have our resized image. Now we will pass this resized image through our create Kenny input function, and here the low threshold argument equal to 70 and the high threshold argument equal to 100. That's good. Now we have our Kenny condition. Now what we will do, we will save the Kenny condition for each keyframe in a new folder. Let's create a new cell here. Here we will create 3 folders. The name of the first folder is Kenny inputs, which has a Kenny input for each keyframe. The second folder is keyframes latents, which has a latent for each keyframe. And the last folder, we will use it to save the generated images. Now let's run this cell. Let's click on this symbol here. Now we have 3 folders. What we will do here, actually, we will put our Kenny inputs inside this folder. How can we do that? Here we will use cv2.imagewrite method, and here firstly we will pass the directory, the folder, the path of the folder that we want to put our Kenny input inside it, which is this one. We will copy the path of this folder and we will put it here. Okay, and we will complete this path with the name of this Kenny input, the name of the file that represents this Kenny input. So we will type F here, okay, and we will open these curly brackets and we will put the name of the keyframe of the current keyframe, which is available in current keyframe variable dot, and here is the extension that we want for this file, JPG. Now let's test our function. Let's run this and let's run our function also. Okay, image is not a numpy array, so let's convert it into numpy array. mp.array like this. Now let's run it again. Let's remove this one. And let's see what is inside Kenny inputs. As you can see here, we have many images inside this folder. Let's open one of them. For example, this one. As you can see here, here is our Kenny input for frame 421. Now, let's find the latent for each keyframe. I will use a create latents function. Here I will add another thing to this function, which is t argument, which is by default equal to the first time step in our scheduler in reverse diffusion. But sometimes you don't want to start with time step t capital if you want to keep some details about your image, so you can change this argument. Okay, and I will delete this one. That's it. Now let's copy the name of this function and let's put it here. Here we will pass our keyframe, our current keyframe, and we will get xt capital for this keyframe. Finally, this xt capital, it is PyTorch tensor. If we want to save this PyTorch tensor, we just need to type torch.save, and here we will pass our tensor, and here we will pass the path of this xt capital of this latent. Here firstly we will type f, and here we will put the folder that we want to put our xt capital inside it. As we said previously, we created 3 folders. Here's the folder that we are talking about, keyframes latents folder /, and here what we will do, we will open these curly brackets and we will put the name of our current keyframe .pt, because it is PyTorch tensor, so the extension of this file should be pt. Now what we will do, we will run this cell again to see the result. As you can see here, here is the latent that related with the first frame or keyframe 1, and here is the latent of the frame 13. But as you can see here, we are using CPU, not GPU, so it will take time. And you should keep in your mind that here, if you are using CPU, you should make torch dtype equal to torch.float32. But if you are using GPU, you can use torch.float16. And here, as we said previously, you can change the time step that you want to start with. Here, I want to start with the first time step in reverse diffusion. But you can make it, for example, 2 or 3 or 4 to keep more details about your original image. Now we learned how to find all Kenny inputs and all xt capitals. Thanks for watching. Now what we will do, we will pass xt capital for each keyframe, and any input for each keyframe through our stable diffusion model, and we will do reverse diffusion to generate these images. Okay, let's do that. Here we created this very simple function. The name of it use SD. This function has many arguments. The first one is the scheduler that we want to use with our stable diffusion model, and the latent and the canny input, the width and height of our image that we want to generate, text condition, keyframe number, and here we have first time step argument, and here we will make it by default equal to the first time step T capital, but if you want you can start with different time steps. Okay, now we created this loop for T in scheduler.timesteps. First time step colon. Here we will pass it through time steps. We will start with our first time step and we will move on to time step 0. Okay, now what we will do, firstly we will take this argument latent, we will put it in this list and we will multiply this list by 2, which means that the resulted list will have 2 elements like this. Okay, and we will concatenate these 2 elements together. Actually here we will put these 2 elements on the batch dimension, but why we did that? We did that because we want to do classifier free guidance, which will make us able to define the guidance scale and use it to control the importance of the prompt in the generated image. And we will put the result in latent model input. Now what we will do, we will pass this latent model input with the current time step T through our scale model input or scheduler.scale model input, and we will get latent model input. Now we will prepare our canny input so that we can pass it through our control net. So we will do the following: control net condition equal to pipe.prepare input, and here we will make image argument equal to canny input, the width equal to the width, and the height equal to the height, and we will make batch size equal to 1, and the number of images per prompt equal to 1, and here we will make dtype equal to torch dtype, torch dtype. Okay, now here is our control net condition. We will also multiply it by 2, and here we will concatenate them together, and now we will have this control net condition. Now we will use our control net, so we will type with torch.noGradient, when here we will type down block res samples, comma mid block res sample, which is equal to control net, and here we will pass our latent model input, the current time step, and here we will make encoder hidden states equal to the text condition, and the control net condition equal to control net condition, which is this one here, and return dict equal to false, and conditioning scale equal to 0.7. Okay, we will take these 2 things here and we will pass them to our U-network. So here we will type noise prediction equal to U-network, and here we will pass our latent model input And here we will pass the current time step, and we will pass the text condition. We will make encoder hidden states equal to CP, and we will make down block additional residuals equal to down block RES samples from our control net, and we will make mid block additional residual equal to mid block RES sample from our control net, and we will make return dect equal to false. And here we will open these square brackets and put 0 between them. Now we have our noise prediction, our predicted epsilon. What we will do here we will do classifier free guidance. Here we will type noise prediction and conditional. Actually, we used our negative prompt to find this noise prediction and conditional. And we have noise prediction text. This one, we used the positive prompt to create this one, which is equal to noise prediction.chunk, and here we passed 2. Now what we will do, here we should specify the guidance scale. Let's make an argument here, which is guidance scale, and let's make it equal to 0.6, okay? And you can change it if you want. And yes. So here we will type noise prediction equal to noise prediction and conditional plus guidance scale times noise prediction text minus noise prediction and conditional. Now what we will do here, we will move one time step backward. So we will type latents equal to scheduler.step or latent equal to scheduler.step, and here we will pass our noise prediction tensor, our current time step, and our latent tensor, and we should type dot previous sample. And we will repeat this loop again and again until reaching time step 0. And after reaching time step 0, what we will do, we will multiply our latent with 1 divided the variational auto encoder scaling factor. It's something important to create the final image. So now we have our new latent. Here we will use our decoder, so we should type with torch.noGradient, and here we will pass our new latent through our decoder, and we will get our new images or our new image. And here we will make the highest possible value inside the new images equal to 1, and the lowest possible value in this new images equal to, and this new image equal to 0. So we will type the following: new images equal to new images times 0.5, and we will add the result to 0.5 dot clamp, and here we will put 0, 1. And now we will send our new image to our CPU, and we will change the order of the dimensions inside this tensor. We will keep the first dimension as it is. We will make, here we will put the channel dimension at the last, and here we will put the height and the width dimension. Okay, and we will convert this tensor into an NumPy array, and we will multiply this tensor with 255, and we will convert the type of this array to unsigned integer 8. Now what we will do, we will pass this new image through our image.from array, and actually we have just one image, so this list will have just one image. And now we have our image. We will save this image inside our output keyframes folder, which is this one here. And the name of this image or this frame, it is equal to the keyframe number. So here we will put keyframe number.jpg. So here the path of the file is output keyframes slash the keyframe number.jpg. And here we will also return the latent, this one here. We have one thing we should change here in this function. We will make first time step equal to 0. Okay, here we want the index of the first time step, not the first time step itself. Okay, yes. Now what we will do, we will create these two variables, latent directory variable. This variable will have the directory of the folder that we put it our latents inside it, which is keyframes latents folder. And we have this variable, Kenny directory variable, which represents the path of the folder that we put it our Kenny inputs inside it, which is Kenny inputs folder. And here we will create this function, generating new frames function. This function has 3 or 4 arguments. Latent directory argument, which is by default equal to this directory, and Kenny directory, which is by default equal to this directory, and width equal to the width of our frames, and the height by default it is equal to the height of our original frames. Now what we will do, we will extract the names of the latents from the paths of the latents. So what we will do here, we will add this directory, latent directory, to this part here, and this glob.glob will return all paths of our latents, and we will pass it through each path, and we will extract the name of the latent, and we will convert it into integer, and we will do this thing for all latents paths, and we will put them in this list. And now we have this latents names list. We will sort all the elements inside this list from the first keyframe latent to the last keyframe latent. And we will do the same thing here to get Kenny inputs names. We will use a glob.glob method to return all the Kenny inputs paths, and we will pass it through each path, and we will extract the name of each Kenny input, and we will convert it into integer and add it to this list. So now this list will have the name of each Kenny input in our Kenny inputs folder. Okay, now we have this Kenny inputs names list. We will sort the elements inside this list from the first Kenny input to the last Kenny input. Now what we will do, we will pass it through each latent name in our latent names list. Okay, so now we have this current latent name. We will create the path of this latent by adding our latent directory to this part here, which is a slash, and here we will put the name of our latent.pt. So now we have this complete path for our latent file. we will put this path in this variable current keyframe latent path. And we will also create the path of the current Kenny input. We will add this Kenny directory to this part here, slash current latent name, which is similar to the current Kenny input name dot jpg. And now we will put the path in this variable current keyframe Kenny input path. Now we will load our Kenny input using load image method. So we will type Kenny input equal to load image, and here we will pass current keyframe Kenny input path. And here we will load our latent tensor. So we will type latent input equal to torch.load. As you know, it is PyTorch tensor, so we should use torch.load. And here we will pass the path of our latent file, which is current keyframe latent path. And we will send our tensor to our device like this. And here we will use our useSD function. We will pass our scheduler, and we will pass our latent input and our Kenny input and our text condition, our current latent name, okay, and the width and height that we want, and the guidance scale, and let's make it 7, and our conditioning scale, and let's make it 0.7. It's a good idea to choose a number between 0 and 1 for this argument. And here we will make this first time step equal to, for example, 0. But actually, let's go back to this place here, to this create keyframes. Here we made our T capital equal to scheduler.time steps, and here we open these square brackets and put it 0 between them. We will change this a little bit. Okay, we will make T capital equal to 0, and here we will do the following. We will put scheduler.time steps, and here we will put between these square brackets this T capital. Okay, so now T capital will represent the index of the first time step in our scheduler.time steps list. So here we will copy this and put it here. Okay, so when you change this T capital, you will change the time step that you will start with in reverse diffusion. Now let's run this cell, and here we will call our function generate new frames function. And here we made our guidance scale equal to 9 and conditioning scale equal to 0.8, and here is the result. Here is the first image. It's good image. And let's see the other image. And here is another image. As you can see here, there are a lot of differences between the first and the second image, and that's a problem for us. Let's move to the third image. Here's our third image, which is also different from the previous images, the previous keyframes, and the same thing here. This frame, this new keyframe, it is different from the previous new keyframes, and the same thing with this new keyframe, and this new keyframe, and this one, and this one, etc. When we use these keyframes to create our video-to-video animation, the video that we will generate, it will not be good. We will not see any consistency in our new video. So we need a way to make these new keyframes have the same style and have some kind of consistency between them. In other words, we want to reduce the flickering. We want to fix the background. We want to make these new keyframes share the same global style, okay? And we want to make sure that the person in this frame, for example, in this new keyframe, similar to the person in the other keyframes, in the other new keyframes. In the future lectures, we will learn how to do all these things. Thanks for watching. Hi, in this lecture we will learn how to generate new keyframes that sharing the same global style using a cross-frame attention method. What is the meaning of global style? It is just the general idea behind the image. When your keyframes sharing the same global style, it means that these keyframes will have the same colors and the background will be a little bit similar, which is something important to create our video-to-video animation. Now, what is cross-frame attention? We said previously that inside our U network, there are many attention blocks. And inside each attention block, we have self-attention layers and cross-attention layers. And we talked previously about what is self-attention layer and a cross-attention layer. Let's say, for example, that we passed this latent through our U network, okay? And we reached to this layer here, this place. And let's say that the feature map that we want to pass through this layer here, it is this one here. And here is the size of this feature map, 4 × 4. We didn't put depth dimension here for simplicity, okay? Now this layer here, it is, let's say that this layer here, it is self-attention layer. This layer will do the following. Firstly, it will extract a Q vector for each pixel in this feature map. So we will get Q vector for this pixel and this pixel and this pixel, etc. Okay? And this layer will also find a key vector for each pixel here. K1, K2, K3, etc. And this layer will also give us a value vector for each pixel in our feature map, our input to this self-attention layer. So we will have a value vector for this pixel v1 and a value vector for this pixel, which is v2, and a value vector for this pixel v3. And we will use all these things to find the contribution of all these pixels in this pixel. and the contribution of all these pixels in this pixel, and the contribution of all these pixels in this pixel, etc. Here in cross-frame attention, we will not find the contribution of all pixels of our feature map in each pixel in our feature map, but we will find the contribution of the pixels of different feature map in each pixel in this feature map. To make things more clear, let's say that we have two frames, two latents. Here's the first latent, xt sub 1, and here's the second latent, xt sub I. These latents, they are different from each other. We created this latent from keyframe 1, the first keyframe in our video, and we created this latent from the current keyframe, keyframe I. Now we will pass this latent through our U network, and we reached to this place here. Okay, and now we have this feature map, and now we will pass this keyframe through the same U network. Okay, and we reached also to this place here, and we have also a feature map in this place here. The size of this feature map similar to the size of this feature map, but of course with different values, because here we created this feature map by passing this input, and we created this feature map in this place here by passing this input, and these two inputs, they are different from each other. Now let's say that the feature map in this place here, the input to this self-attention layer, it is this feature map with this size, which is similar to this size. Our self-attention layer in this place will also find a Q value and a key value and a vector value for each pixel in this keyframe. Here I will say that this feature map here, it is the feature map that we will pass through this self-attention layer here, and now we have the Q vectors and key vectors and value vectors that we will get from the self-attention layer here for this feature map. And I will say that this feature map here, it is the input to this self-attention layer here. Our self-attention layer in this place will also create a V vector, Q vector, and key vector for each pixel in our input feature map. But here we will just focus on the key vectors and the value vectors. Our self-attention layer will create this value vector and this key vector. Okay, and it will create this value vector 2, and this key vector 2 for this pixel here, and it will also create this value vector 3 and this key vector 3 for this pixel, etc. As we said previously, we will find the contribution of all these pixels here in this feature map that are created by passing this latent, the latent of the first keyframe, through our U network. Here, to compute the contribution, what we will do actually, we will take the key vector and the value vector for each pixel in this keyframe. Okay? And we will take just the Q vectors from this feature map. We will multiply the Q vector for this pixel with all these key vectors in this feature map to find the attention matrix. And after finding the attention matrix, we will multiply this attention matrix with all these value vectors. Okay? By doing this, you will make all these pixels here contribute in the pixel that we will get from this self-attention layer. And here it's like that we asked about how much each one of these pixels in this feature map is related with the first pixel in this feature map. And we will compute the value of the new pixel by using these relations, or in other words, we will do weighted sum of all these value vectors. And this is our new pixel. And we will do the same process for all these pixels in this feature map. Pixels. And here actually we are trying to transfer the global style inside this keyframe, the first keyframe, to this current keyframe. Okay? And we will do the same thing with this pixel here. We will take the Q value of this pixel and we will multiply it with each key value in this feature map. And we will apply the softmax to find the attention matrix, and we will multiply it with all these value vectors in our feature map, in this feature map, to create a new pixel here. The vector that represents this pixel will be the weighted sum of all value vectors, and as you know, based on the attention matrix. The value vector in this feature map that has strong relationship with this pixel here, it will have large effect on the final vector, or in other words, our new pixel. And that's it. That's what we mean by cross-frame attention. Okay? Here what we will do actually, we will take the key vectors and value vectors from our self-attention layers in the decoder part of our U network. This one we call it decoder part. Okay? So we will take all key vectors and value vectors from all self-attention layers in this decoder part of our U network. These key vectors and value vectors, they created by passing the latent of the first keyframe. And we will take just the Q vectors from each self-attention layer of our U network. These Q vectors, they created by passing the latent of the current keyframe. We will use these Q vectors in the decoder part of our U network that we created by passing the latent of the current keyframe with the key vectors and value vectors that we get after passing the latent of the first frame to do cross-frame attention at each self-attention layer of our decoder part of our U network. We will multiply each Q vector that we created by passing this current latent by each key vector that we created by passing this first latent, and we will apply softmax to find the attention matrix and we will multiply the attention matrix of each self-attention layer with the value vector of the same self-attention layer that we created by passing the first latent. And we will get xt minus 1, which means the latent at time step t minus 1 or time step t minus delta t of the first keyframe. And we will get also xt minus 1 sub I, or the latent at time step t minus delta t of the current keyframe. In the next lecture, we will learn how to do all these things practically. Now let's learn how to do cross-frame attention. Firstly, we should import system package here. Okay, and let's run this cell. Now we will create the hooks that we will put on our U network. We will put a hook on each self-attention layer in our U network, in our encoder part of our U network. When we pass the latent at time step t for our first keyframe through our U network, and when we reach the first self-attention layer, this hook, the first hook, will take the key vectors and the value vectors for each pixel in the input feature map. This self-attention here created all these key vectors and value vectors. For simplicity, let's say that K1 is just one key vector, and V1 it is just one value vector, and K2 it is just one key vector, and V2 it is just one value vector, etc. It's like our feature map, our input feature map has just one pixel. And when we reach self-attention layer 2, our hook that we put it at this layer will take the K2 and V2 from it. And when we reach self-attention 3, our hook that we put it to this layer will take K3 and V3. And when we reach self-attention 4, our hook that we put it at this layer will take K4 and V4, etc. We will use all these vectors to transfer the global style from this latent of the first keyframe to the latent of the current keyframe. Our hooks that we created to take all these K and V vectors, it will replace the K and V vectors at each self-attention layer in our decoder part of our U network that we will get after passing the latent of the current keyframe by the K and V vectors that we took from our hooks previously. These vectors we created by passing the latent of the first keyframe. And when we replace the K and V vectors that we created by passing the latent of the current keyframe by the K and V vectors that we created by passing the latent of the first keyframe and applying the formula of self-attention mechanism after that, this thing we will call it cross-frame attention. Firstly, we will create three variables. The first variable is blocks. In our decoder part of our U network, we have three blocks. Block 1, block 2, and block 3. We created this list that has the ID of each block in our decoder part of our U network. Okay? And inside each block, we have three self-attention layers. So we created this list, attentions list, which is equal to this list here. The first element is 0, which means attention 0. It is the first attention layer in any block. This attention layer will have two layers inside it. we will take just the self-attention layer. And attention 1, which is the second attention layer in any block, and attention 2, which is the third attention layer in any block in our decoder part of our unit work. And here we will create global dictionary. What is the meaning of this? Here we will put all these key and value vectors in a dictionary, and we should be able to reach the values of this dictionary from any place. So it should be global dictionary. It is something similar to what we did to do style transfer previously. So we will make this variable global variables equal to globals. Okay. Now we will pass it through of our decoder part of our unit work. So we will create this loop for block number in blocks, and now we will pass it through each self-attention layer in that block. So we will create this loop here for attention number in attentions list. Now, as you know, we should create a function for each hook. Firstly, we will specify the name of the function. So we will create this variable function name equal to f, and we will put these quotations, and here we will put up block. Why we set up block? Because in the decoder part we call each block up block because it will increase the spatial dimensions of the input. And here we will put the block number. If we are talking about block 1, which is the first block in our decoder, so we will put 1 here. If we are talking about block 2, so we will put 2 here, etc. Underscore, and here we will specify which self-attention layer we are talking about inside this block. We will put attention here, underscore, and here we will put the attention number, which is the number of the self-attention layer that we are talking about. Let's say we are in block 1, and if we are talking about the first self-attention layer, so we will put 0 here. If we are talking about the second self-attention layer, we will put 1 here. If we are talking about the third self-attention layer, we will put 2 here. And here we will use this function to take the key vectors of each pixel in the input feature map to this self-attention layer. So here we will type underscore k, and here we will type underscore hook, and here is the name of the function that we will use to create our hook. Now let's define our function. We will define our function here as a string, and after that we will create to make the generation of the functions that we will use to create the hooks dynamic process. And here is the body of our function. Let's call it function body variable, which is equal. Here we will put f, and we will put all these things here and here. Now we will define our function. We will type define, and we will open these curly brackets, and here we will put the name of our function. Okay, we will put this variable function name variable. For example, if we are talking about up block 1, which means the first block in our decoder part of our unit work, attention 0 k hook. This means that we will create a hook and we will put it on the first self-attention layer and the first block in our decoder part of our unit work. This hook will take the key vectors of each pixel of the input feature map to this self-attention layer. Now let's go back to the function that we will use to create this hook. And here this function will take three arguments: module, input, and output. And we talked about that previously. And here we have also another global variable, which is attGate variable. This variable will specify what is the latent that we passed through our U-network to get the key vectors of each pixel in the input to this self-attention layer. Actually, we don't want to take the key vectors of each pixel in the input to the self-attention layer that we created by passing the latent of the current keyframe. So we change this based on what we want to pass through our U-network. We will not change this variable inside this function, but we will change it from outside. So this variable is a global variable. We will create this variable, key variable. We will use this variable to be able to access to the key vectors of this self-attention layer and extract them from our dictionary or update these key vectors of this self-attention layer in our dictionary. Key equal to system. Here we will use system package.getFrame, and we will open and close these parentheses. .f_code .co name. Here this one will give you the name of your function automatically. It will give it as a string. We will remove the last 5 characters by typing the following: :-5, and here we will add to our string _I1. Now we will check the value of this variable, attGate variable. So if it is equal to I1, it means that we passed the latent of the first keyframe through our U-network, which means that these key vectors at this self-attention layer, they created by passing the latent of the first keyframe. So we will store these key vectors in our dictionary, and we will store it with this name. Okay, in our dictionary. If we passed the latent of the current keyframe, at this case, I want to from you to make the latent. At this case, we will extract the key vectors of the self-attention layer that we created by passing the latent of the first keyframe, and we will replace the key vectors that are created by passing the current latent by these key vectors that are created by the latent of the first keyframe. At this case, we just need to type return, and here we will type the name of our dictionary and the name that we used to store the key vectors that we created by passing the latent of the first keyframe. And now we will use execute method to create this function. Here it is just a string. Now we will create it. So we will type exec, and here we will pass the body of our function body. Now we have our function. Now we will create our hook. So hook, it is equal to unit.addBlocks, and here we will pass the block number, .attentions, and here we will pass the self-attention layer number, .transformer blocks, this is not important, .attention1, it is not important also, .2k, and here we will type register forward hook. Here we will pass our function. We will take the name of our function name, and we will type globals, and we will open and close these parentheses, and between these square brackets we will put the function name. So now we passed our function through our register forward hook method. Now we put it our hook on this specific self-attention layer in this specific block. We will do this thing for all self-attention layers in all blocks in our decoder part of our U network. Each self-attention layer will have its own function, or in other words, its own hook that we will use to take the key vectors from each self-attention layer in our decoder part of our. Now we will create the hooks that we will use to get the value vectors from each self-attention layer in the decoder part of our U network. And these hooks will also replace the value vectors that are created by passing the latent of the current keyframe by the value vectors that are created by passing the latent of the first keyframe. And here we will do the same thing. We will define a function for each self-attention layer in our decoder part of our U network. We will use these functions to create the hooks that we will put on our self-attention layers in our decoder part of our U network. And yes, that's it. We just need to create function name one variable. Let's call it function name one, which is equal to f, and here we will put up block, and here we will put the block number and the attention number, and here we will put v, which means that this hook or this function we will use it to get the value vectors, and here we will put hook. Okay, and here we will create this variable function body1 variable, and here we will define our function as a string. We will type define, and here we will put the name of this function, and here we have 3 inputs, and we have this att gate global variable that we can use to decide if we want to take and store the value vectors or replace them. And here we will specify the name that we will use to store the value vector for each pixel in our input feature map that are created by our self-attention layer. These value vectors, they created by passing the latent of the first keyframe. And now, so here we will take this part, just this part, and we will add to it underscore i1. Now, if attribute gate equal to i1, it means that these value vectors that are created by this self-attention layer, they created by passing the latent of the first keyframe. So we should store them in our dictionary. And here's the name that we will use to get these value vectors in the next time. Now if we passed the latent of the current keyframe, in this case we don't want to save these value vectors, but we should replace them with the value vectors that are created by passing the latent of the first keyframe. So we just need to type return, and here we will put our dictionary, global variables dictionary, and we will put the name that we used to save the value vectors that are created by passing the latent of the first keyframe. And that's it. Now we will execute this function and we will create our hook. We will call it vhook equal to unet.upblocks, and here we will put the number of the block that we are talking about and the number of the self-attention layer that we are talking about right now, and here we will reach to the value layer in our self-attention layer, this self-attention layer. So we will type .attention1.2v, and here we will type register forward hook, and here we will pass our function. So we will type globals, we will open and close these parentheses, and between these square brackets we will put function name 1. okay, which is this one here. And that's it. Now we created our hooks to do cross frame attention. Now what we will do, we will change our use SD function a little bit to make it support cross frame attention. So now we created this function, this new function, use SD with the cross frame attention. We will pass to this function our scheduler, our latent that related with the current keyframe, the Kenny input of the current keyframe, the latent of the first keyframe, and the Kenny input of the first keyframe, and the text condition, which is the same in the first keyframe and the current keyframe. And we have keyframe number, which is the number of the current keyframe. We have the width and height and the guidance scale, conditioning scale, first time step. Now what we'll do, we will make this variable att_gate variable global variable, so we can change it from this place and it will change in all other functions that we created previously. Now we will create this loop. We will pass it through each time step, inside each time step, and at each time step we will do the following. Firstly, we will change our att_gate variable and we will make it I1, which means here we will pass the first keyframe or the latent of the first keyframe through our stable diffusion model. And here we will prepare our input, and it is similar to what we did previously. Okay, but here we will do this thing for the first latent or the latent of the first keyframe, and we will prepare the control net condition 1 like what we did previously. We will use pipe.prepare image and we will pass our Kenny input 1 through it. Okay, and here we will convert it into PyTorch tensor, and here we will use our control net. We will pass all these things through our control net to get down block RES samples and mid block RES samples. And here we will use our U network to get noise prediction 1. Here, by using our U network, by passing latent model 1 through our U network, our hooks will automatically get the key vectors and the value vectors from each self-attention layer in the decoder part of our U network. Now we saved all what we want in our global variables dictionary. Now we want also to move one step backward. Now we will move to the time step t minus delta t. So we will type noise prediction and condition 1 and noise prediction text 1 is equal to noise prediction dot chunk 2, and here we will do classifier free guidance, and here we will get latent 1, or in other words it is the latent of the first keyframe at time step t minus delta t. So now we did our reverse diffusion and we have all what we want about the key vectors and value vectors in our global variable. Now we will change our att_gate variable to I, which means now we will pass the latent of the current keyframe. We will do all these things. We will create latent model input I, and we will create control net condition I. We will pass Kenny input I, the Kenny input of the current keyframe, and we will prepare our control net condition I. We will pass them through our control net to get these two things. Okay, like what we did previously. And here we will use our U network. We will pass our latent model input I, and we will pass our text condition and all these things from our control net. And here our hooks will automatically replace the key vectors and the value vectors that are created by passing the latent of the current keyframe by the key vectors and the value vectors that are created by passing the latent of the first keyframe. And they will do this for each self-attention layer in our decoder part of our U network, which means that we are doing cross-frame attention. And in other words, we are transfer the global style of the first keyframe to the current keyframe. And here we will do reverse diffusion for our current keyframe. We will extract noise prediction and condition I, noise prediction text I, and here we will do classifier free guidance, and here we will move one step backward. And we have now latent I. This latent, it is the latent of the current keyframe at time step t minus delta t. And when we reach the time step 0, at this case we will multiply the latent of the current keyframe at time step 0 by 1 divided by the variational autoencoder scaling factor, and we will pass this new latent through our decoder, and we will convert the range of the values inside our new images to make it between 0 and 1, and we will send it to our CPU, and we will multiply all these values by 255 to make the range between 0 and 255, and we will convert the type into unsigned integer 8, and that's it. Now we have our image, our new keyframe that has the global style of the first keyframe. We will start with this name. So we will type output keyframes, and here we will put keyframe number, which is the number of the current keyframe, and here we will put the extension of that file, which is JPG. And we can also return this latent 0 of our current keyframe. Now we will use this function, use st with the cross frame attention. Inside this function, generate new frames with cross frame attention. Here we have our latent directory, Kenny directory. We will pass them through our function, and the width and height also. And here we will create a list of the latent names, and here we will sort the names in this list, and here we will create a list from Kenny input names, and we will sort the names. We will load our Kenny input 1 and latent input 1. So we will type Kenny input 1 equal to load image, and here we will put Kenny directory, and here we will put the name of the first Kenny input, or the Kenny input of the first keyframe. So we will type Kenny inputs names, and here we will put 0 between these square brackets, and here we will put .jpg. And that's it. Now we have this complete path. We will pass it through our load image, and now we have our Kenny input 1. Now what we will do, we will load our latent. So we will type latent input 1 is equal to torch.load, and here we will put our latent directory, and here we will put the name of the latent of the first keyframe, which is latent names, and here we will put 0 between these square brackets, and here we will put .pt. Now we will send this tensor to our device, our coda, or our CPU, and here we will also specify the torch data type, which is float 16 in this case. And now what we will do, we will create this loop. We will pass it through each latent. For current latent name in latent names, we will do the following. We will create this variable current keyframe latent path and current keyframe Kenny input path. Same as what we did previously, we will get Kenny input for the current keyframe and the latent input for the current keyframe. We will send it to our device, and here what we will do, we will use our use SD with cross frame attention function. We will pass our scheduler, our latent input I, Kenny input I, latent input 1, Kenny input 1, text condition, current latent name, the width and the height, the guidance scale, we will make it 9, conditioning scale is equal to 0.8, and first time step it is equal to T capital. Let's see firstly the keyframes that we generated previously. Here is the first image and the second image. As you can see here, the background here, it is completely different, and the colors also. And here's the third image. As you can see here also, the colors are very different. So these keyframes, they did not share the same global style. And this one here, as you can see, the colors and the background, they are very different from the previous keyframes. And this image here and here. And this one is very different. Now, let's use our cross frame attention method to see our new keyframes. As you can see here, our hooks are taking the key vectors and the value vectors from our first keyframe, and it will put them in our U network during passing our current keyframe or the latent of the current keyframe. Let's see the first image. Here is the first image or the first keyframe. Let's see the global style now of the second keyframe. Now that's good. As you can see here, the background, it is something similar to the first keyframe. As you can see here. And the colors also. And that's good. Now let's move to the next keyframe, the next generated keyframe. Now that's also good. The colors are good and the background also. It is something similar to the previous keyframe and the first keyframe. Okay, let's take another keyframe. This one is also good. The background, the basic idea behind the background, it is something similar to the first keyframe, the first generated keyframe. Okay, and the colors also, as you can see here. This blue color here, it is also available here. And let's take another keyframe. And this one also good. The background is something similar to the first keyframe. And this one also. And this one also. That's great. That's good, but not enough actually. There are some flickering in the background between frames. In the next lecture, we will learn how to create shape-aware module that will make our keyframes even better. Thanks for watching. Hi, in the previous lecture, we talked about cross-frame attention, and we used cross-frame attention to make our generated keyframes sharing the same global style. Now we want from our generated keyframes to share the same textures and local shapes. To do that, we will use shape-aware module. We talked previously about just this part here, okay? We did here cross-frame attention. Here we will pass two things to our U network. We will pass xt subscript 1, which means the latent at time step t that are related with the first keyframe, and the second input is xt subscript I, which is the latent at time step t that related with the current keyframe. When we pass this thing, this latent through our U network, we will get this thing here, which is epsilon at time step t that related with the first keyframe. And when we pass this latent through our U network will give us this thing here, epsilon at time step t that related with the current keyframe. Here we will use our shape-aware module in the first time step in reverse diffusion, or in the first two time steps in reverse diffusion. Let's say now we are at the first time step in reverse diffusion, which means that t here is equal to t capital. Here we will check in this place if t it is greater than t capital sub d, which means that we didn't finish the first two time steps yet. At this case, we are at time step t capital, so we are at the first time step. At this case, we will pass this epsilon t subscript 1 here. We will pass it to this DDIM algorithm. Here what we will do actually, we will use DDIM algorithm to extract the predicted x0 that related with the first keyframe. But how we extracted this latent here? As you know, previously we talked about DDIM, okay? And here is the formula for DDIM. Xt minus 1 equal to the square root of alpha bar t minus 1 times the predicted x0 plus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon at time step t. Now we will move this predicted x at time step 0 to this place here, and we will get the following. The predicted x at time step 0 equal to xt minus 1 minus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon at time step t divided by the square root of alpha bar t minus 1. That's good, but it is not enough. Actually, here we want to apply our shape-aware module in the first time step, at time step t capital. But here in this formula, we are using xt minus 1 or xt minus delta t to find this predicted x0. It's like that we skipped time step t capital. We didn't do shape-aware operation at time step t capital. So what we will do here, we will do the following. We will change this formula a little bit. So now the predicted epsilon at time step 0, it will be equal to xt, the latent at time step t, the current time step, minus the square root of 1 minus alpha bar t. We replaced alpha bar t minus 1 by alpha bar t times epsilon t divided by the square root of alpha bar t. Now you might ask yourself why we used the predicted epsilon at time step t. Here, it should be epsilon at time step t plus 1 or t plus delta t. The answer is easy, because it is not possible to find epsilon t plus delta t, because here we are at the first time step, at time step t capital, and there is nothing before that. And using our predicted epsilon at time step t with our xt to find the predicted x0, it will also give us good results. Actually, we did this thing previously when we talked about style transfer. So now we found this predicted x0 that are related with the first keyframe using DDIM algorithm, using this formula here. Now what we will do, we will wrap this predicted x0 that are related with the first keyframe to make it similar to this predicted x0 that are related with the current keyframe. And by similar, we mean that we will move the pixels of the predicted x0 that are related with the first keyframe to put them in the new positions, the positions in the current keyframe. But we will not change their values, we will just move and change their positions. In this case, we will be able to combine these two things together. How can we do that? And why we need to combine them? We need to combine them in some way to transfer the textures and the local shapes from the first generated keyframe to the current generated keyframe. To do that, firstly, we should pass the first keyframe and the current keyframe through our GM flow model, and here we will extract forward optical flow and backward optical flow. We will use this forward optical flow to wrap this predicted x0 that are related with the first keyframe, and we will get this latent, this new latent, which is x0 dash subscript I. And here we can combine this latent here with this latent here without any problem. But what is this latent here? The predicted x0 that related with the current keyframe. As you can see here, we passed this xt subscript I through our U network, and we got this thing here, epsilon at time step t, that related with the current keyframe. And here we will check if the time step here it is equal to t capital, or we didn't finish the first time step. At this case, we will apply this DDIM algorithm, or to be more specific, we will apply this formula to extract the predicted x0 that related with the current keyframe. This latent, it doesn't have any information about the textures and the local shapes of the first generated keyframe. To transfer all this information to this latent, we will use this latent here. This latent that we will use to generate the first keyframe. Now what we will do, we will create a mask that represents the occluded regions. We will use our forward optical flow and backward optical flow to find this occluded mask. We will use it to combine these two latents together. Firstly, we should resize this mask to make the shape of this mask similar to the shape of any latent. Okay. Why? Because the shape of this mask will be equal to the shape of any one of these keyframes. So we should resize it to be able to apply this mask on these latents. And these latents, they are of course smaller than our keyframes. After resizing our occluded mask, we will do the following. We will multiply this latent by 1 minus the mask. This thing here will represent the unoccluded regions, which means here we will use just the information that related with the unoccluded regions that is available in this x0 subscript I. These informations will have the textures and the local shapes of our first generated keyframe. Why we didn't take the information inside this latent that related with the occluded regions? Because as you know, our GM flow will not be able to find the correct optical flow for these occluded regions. So we will remove these informations from this latent. We don't need to use them. Actually, we will use the information inside this predicted x0 subscript I that are related with the occluded regions because they are good and we can use them. So here what we will do, we will multiply this mask by this predicted x0 subscript I. This mask will specify the occluded regions, and this one will remove the information inside this latent that related with the unoccluded regions, and it will keep the information that related with the occluded regions. Okay, now we will add these two latents together. We will combine them together to get full latent, which is this one here, the predicted x0 subscript I. We will add a noise to it, or we have another way. We can use this formula here to get xt minus 1. We have this one here, and we can find this one and this one, and we have this one, which is this one here, this predicted epsilon at time step t subscript I. So we can find this latent x t minus 1 subscript I, and this one we will make it equal to xt subscript I, because now the time step it is equal to t minus delta t or t minus 1. The current time step now it is t minus 1. So now what we did actually, we transferred the textures and the local shapes that is available in the first generated keyframe to the rest generated keyframes. So now all our generated keyframes will have the same textures and local shapes that is available in the first generated keyframe. Now we will learn how to do all these things practically. Hi, in this lecture we will create our shape aware module. Firstly, we need to download GMFlow repository. So we will type git clone, and here we will put the link of GMFlow repository. And here we will import GMFlow class from gmflow.gmflow.gmflow, and we will import all things inside utils package. So we will type from gmflow.utils import everything. And here we will create our gmflow model like what we did previously. And here we will load the pre-trained weights and we will put them in our gmflow model. And here we will type gmflow.evaluation because here we will use our gmflow model and we will not train it. And here we created this function, getFlow and mask function. This function will take two arguments, first frame argument and current frame argument. This function will return three things. Firstly, it will return the occluded mask, and it will return forward flow, and it will also return wrapped first frame. We put it inside this function all what we learned in the previous lectures about optical flow. Okay, and we created this function use SD with cross frame attention and shape aware module. This function will take many arguments. The first argument is a scheduler, the second argument is the occluded mask, the third argument is forward optical flow, and this argument is the latent at time step t that related with the current keyframe. And here we have the canny input of the current keyframe, and here we have the latent at time step t for the first keyframe, and we have here the canny input of the first keyframe and the text condition and the number of the current keyframe and the width and height and the guidance scale, conditioning scale. And here we made first time steps equal to 0 and TD equal to 2. Actually, we will change this one to TD equal to 1, okay, to apply this shape aware module in the first time step in reverse diffusion. Because when you apply this shape aware module in many time steps in reverse diffusion, the results will not be good. We talked about all these things previously. We will talk here just about what we changed and added to our previous code. And here we found xt-1 that are related with the current keyframe. And here we will find the predicted x0 that are related with the first keyframe by passing our xt that are related with the first keyframe, the predicted epsilon that are related with the first keyframe through our DDIM algorithm. Here we will use this formula to find the predicted x0 that are related with the first keyframe. Here we created this function to time step 0 function. This function will take 4 things: the latent at time step t that are related with the first keyframe, and the scheduler, the name or the number of the current keyframe, and the predicted noise that are related with the first keyframe. Okay, so now we have the latent, the predicted latent at time step 0 that related with the first keyframe, and we will do the same thing to get the predicted latent at time step 0 that related with the current keyframe. So we will type latent I at time step 0 equal to, and here we will use this function to time step 0, and here we will pass the latent at time step t that related with the current keyframe, the scheduler, and the current time step, and the predicted noise that related with the current keyframe. Now let's see what is inside this to time step 0 function. And here's our function. we have four things here: xt, scheduler, I, noise prediction. Here we have this condition. We will check if we didn't reach to the last time step in reverse diffusion. At this case, to get the value of alpha bar t, we should use our scheduler.alpha as cumulative product, and here we should take the alpha bar t that related with our current time step. Actually, here we didn't specify what is the meaning of I here. Here we have t, which is the current time step. Let's make I equal to t, or in other words, we can pass t here and here. And at this case, we don't need to type all these things here. We just need to pass this t, okay, like this. So by doing this, we will get alpha bar t that are related with the current time step. Now we have alpha bar t that are related with the current time step, or in other words, alpha bar at time step t. And if we reach the last time step in reverse diffusion, at this case we will make alpha bar t equal to 1. It is something important actually. Here what we will do, we will find the predicted x0. So we will use this formula here. The predicted x0, it is equal to xt, the latent at time step t, minus the square root of 1 minus alpha bar t times the predicted epsilon divided by the square root of alpha bar t. Let's do it. So now the latent at time step t minus the square root of 1 minus alpha bar t times the predicted noise divided by the square root of alpha bar t. That's good. Now we will type predicted x0 equal to predicted x0.clamp, and here we will put minus scheduler.configuration.clip sample range, comma, scheduler.configuration.clip sample range. So at this case, anything inside this predicted x0 greater than this thing here, scheduler.configuration.clip sample range, at this case we will make it equal to scheduler.configuration.clip sample range value. And if anything is smaller than this minus scheduler.configuration.clip sample range, we will make it equal to minus scheduler.configuration.clip sample range value. Okay, and here we will return this predicted x0. And here we will change this thing here to t. Okay, and that's it. This is our function that will move us to the predicted x0. Okay, now we have all these things, and now we will wrap this predicted x0 that related with the first keyframe by using this forward optical flow. So here what we will do, firstly we will type wrapped latent 1 at time step 0 equal to f.grid sample, and here we will pass latent 1 at time step 0 and our forward optical flow, and here we will multiply our wrapped latent 1 at time step 0 by 1 minus the occluded mask, and we will multiply our latent I at time step 0 by the occluded mask, and here we will add them together. So latent I at time step 0, it will be equal to latent I at time step 0 plus wrapped latent 1 at time step 0. Now to get xt minus 1 that are related with the current keyframe, here we have this alpha bar t minus 1, and we have the predicted x0 that are related with the current keyframe, and we have this one and we have this one. So that's easy. And here we will find xt minus 1 that are related with the current keyframe, which is equal to the latent I at time step 0 times the square root of alpha bar t minus 1 plus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon that are related with the current keyframe. And here we extracted alpha bar t minus 1 from our scheduler.alpha's cumulative product. Here we created this condition. Here k, it means the index of the next time step in reverse diffusion. And here it means the index of the current time step in reverse diffusion. And a plus 1, it means the index of the next time step in reverse diffusion. We will use it to extract this next time step in reverse diffusion if we didn't reach the final time step in reverse diffusion. Okay, at this case we will make alpha bar t minus 1 equal to scheduler.alpha's cumulative product, and here we will put the index of the next time step in reverse diffusion, which is k. So now we extracted alpha bar t minus 1 that are related with the current keyframe. And here, if we reached the final time step, or if t minus delta t time step, it is the final time step in reverse diffusion. At this case, we will make alpha bar t minus 1 equal to 1. And here we have another mistake in this condition. Here we should type scheduler.time steps, and we should put this k between square brackets, not equal to. We should also put here scheduler.time steps, and we should put minus 1 between these two brackets. And we have another mistake here. Here we should pass the next time step in reverse diffusion, not the index of the next time step in reverse diffusion. So here, rather than passing k, we will type scheduler.time steps, and we will open square brackets, and we will put k between them, and we will put the result between these two square brackets here. Now you should change these two things that I talked about previously before running the code. Now here we will use our formula that we talked about previously, this one here, to find xt minus 1 that are related with the current keyframe. And finally here we will make latent I equal to this xt minus I, and we will make latent 1 equal to xt minus 1 underscore I1, and that's it. And we also changed many things inside our generate new frames with cross frame attention. We added here and shape aware module. Here we have all these arguments: latent directory, Kenny directory, and here we put it frames directory, which is the directory of our frames, and the width and height. Let's just talk about what we changed here, what we added here. Now here we downloaded our first keyframe. Here what we did actually, we put it our frames directory, and here we added this thing here, and here we put it F, and we put it these two quotations, and we put it slash curly brackets, and between these two curly brackets we put it Kenny input names, and between these square brackets we put it 0, which means the first element in this Kenny inputs names, which is the name of the first keyframe, also colon 04, okay, which means that we should have 4 digits. Firstly, we will put the name of our first keyframe, and we will put zeros and the rest digits to the left. And here we will put the extension .png. Now we have our first image. What we will do now, we will download our current keyframe. We will pass them through our getFlow and mask function. Here we will get the width and height of any latent, and here we took the width and height of the first latent, which is related with the first keyframe, and here we created Y and X locations. Here Y it is just an array, two-dimensional array, which has all Y locations. And here X it is just a two-dimensional array which has all X locations. Here we have our forward optical flow. We will change its size to make it similar to the size of any latent in our latents. We will use interpolate to do that. We will pass the desired width and height. And here what we will do, we will combine these two arrays together to create a grid. And we will add our forward optical flow to this grid to get wrapped grid using FWD. Now we will take the shape of this grid, this wrapped grid using FWD, and we will normalize the locations inside this wrapped grid using FWD. We will make the X locations and Y locations between -1 and 1. So we will do the following. Normalized wrapped X grid FWD, it is equal to 2 times wrapped grid using FWD. Here we will put colon, comma, 0, which means that we took the X locations, we multiplied them by 2, and we divided them by the width -1, and finally we subtracted 1 from the resulted tensor, and the same thing here. And now here what we will do, we will combine them together again to get normalized wrapped grid FWD. We use torch.stack to do that, and here we will pass our normalized wrapped X grid FWD and normalized wrapped Y grid FWD, and here we specified the location of the new dimension that we will use to put these two things along it. So now we have the batch size, the width and height, and finally our new dimension with length 2, which has these two things here. And here we also have our occluded mask. Okay, we will convert it into NumPy array. This M matrix, it has also batch dimension, so we should put 0 here. Okay, to get just the mask, and we will resize it using our OpenCV library, and we will put the desired size, which is the size of any latent, because as you know, we won't use this occluded matrix with our latents. We want to multiply it with our latents, so the shape of it should be similar to the shape of any latent that we have. And here what we will do, we will convert it into PyTorch tensor again, and we will send it to our device. And here we will add a new dimension with length 1, okay, which represents the batch dimension. And here we will add another dimension with length 1 also. Here we will repeat the second dimension, the second dimension that we put it here with length 1. Now we will repeat it 4 times, and we will keep the rest dimensions as they are. Why we did that? Because in any latent, in the second dimension of any latent, we have 4 feature maps. So when we want to multiply our occluded mask, we should multiply it with each feature map in our latent. So we should repeat this mask 4 times. And we talked about all these things previously. And finally, what we will do, we will use this function, use SD with cross frame attention and shape aware module. Here we will pass our scheduler, our occluded matrix, our occluded mask, our normalized wrapped grid FWD, our latent input I, our canny input I, our latent input 1, canny input 1, and our current latent name, and the width and height that we want, the guidance scale, and the conditioning scale. Let's make the guidance scale equal to 0.7. Let's make TD equal to, for example, 1, and that's it. And we put this condition here, as you can see, to apply our